Hi there, and welcome to this Amazon Web Services Fundamentals course. Throughout this course, you will learn why and when to implement many of the services and features offered by Amazon Web Services. We will cover topics like distributed computing, multi-tier architectures, virtual machines, storage, databases, analytics, high availability, and much more. We will see just how simple and cost-effective it is to achieve a superior level of high availability, fault tolerance, security, and reduced operational burden in our infrastructure and our applications. We will review a number of use cases designed to spark your imagination and exemplify well-architected solutions within the rich and varied ecosystem that is Amazon Web Services. In the nearly 2 years since I published the first edition, AWS has added many new services to their offerings, as well as many new features to existing services. In some cases, existing services function differently and for the better. The AWS Web-based Management Console has also seen significant updates and improvements. In this second edition, I've included many of those new services and features and provided all new diagrams that are more clear and easier to follow and more accurately represent diagrams you would see in a real-world scenario. I've also recorded entirely new demos to account for changes in the console user interface. Just a little about myself and my background. I've been developing web and mobile applications for the past 15 years and started using Amazon Web Services in early 2009. In the last 9 years, Amazon Web Services has greatly outpaced other cloud providers, and I have continually strived to deepen my knowledge and experience with their services by working with startups to build cloud-native applications, as well as helping established companies migrate to AWS. As of this video, I have a total of 7 certifications, including the Solutions Architect and the DevOps Engineer professional levels, and have delivered AWS training to Fortune 500 companies around the world. Before we get into the technical details of various services, let's first look at the big picture. In this lesson, we will look at AWS global infrastructure and review some very foundational terms and concepts that apply to everything we will cover from here on. In this lesson, we will explore AWS data centers and their locations around the world, as well as a high-level overview of the kinds of services offered. Let's first review the definition of cloud computing. So the National Institute of Standards and Technology here in the US, otherwise known as NIST, got together with industry leaders some years ago and came up with an official definition of cloud computing. And through a number of different drafts, they were able to simplify it and distill it down to its real core essence. And first, we have characteristics. The characteristics of cloud computing would be, one, that services or features or resources are retrieved via on-demand, that they are available to us by us asking for them directly. So I can go to a service and ask for a virtual machine or a storage volume or some other type of resource and get it when I ask for it. I get it at the time I make that demand or request. And so on-demand really is one of the core pieces of cloud computing that gives rise to a level of automation and flexibility and agility that we've never had before, and a level of automation that we perhaps have never had before. The other characteristic would be broad network access, meaning that the resources that we have within the cloud can communicate with each other across the network, that we can get to them across the network, that we have access to the internet. The third characteristic would be resource pooling. In some cases, we have multi-tenant environments, right? There may be many cases that we have a multi-tenant environment, and there are some cases where we can actually have a single-tenant environment. But if you were to zoom out and look at the big picture, and you would see that even though our virtual machine or our physical server might be a single tenant environment, the rack is shared with other machines that are powering or providing services to other customers. And then, of course, the data center itself is shared by numerous customers. The power, the cooling, the network, and so on are all shared. So resource pooling is really the way that cloud computing can offer the services that it does at the prices that it offers them at. The fourth characteristic would be rapid elasticity. So elasticity speaks to the idea that resources can grow and shrink. They can grow vertically, they can grow horizontally, but rapid elasticity means that if we need more storage now than we needed, an hour ago, if we suddenly need more capacity in our API or our database today than we needed yesterday, that we can get that capacity quickly and easily. And the on-demand nature allows for that. So rapid elasticity, the ability to scale when we need to scale. And then lastly, we have a measured service. And that's just a fancy way of saying pay as you go. So when we take the Elastic Compute Cloud, or EC2 for example, if we ran a machine, a virtual instance, for let's say an hour, then we pay for an hour. If we run it for 2 hours, we pay for 2 hours. So we pay for what we use. And within AWS, the trick to really achieving the most cost savings or the most cost-effective solutions is to use what we really need, right? So we pay for what we use. It's our job to use what we really need and no more. And we'll talk more about that later on. Now, in terms of service models, many of these we've heard before, I'm sure, starting with Infrastructure as a Service, or IaaS. Infrastructure as a Service is essentially those fundamental, lower-level sort of raw building blocks, such as raw computing or storage volumes, right? So we can build our application on top of Amazon's compute power and storage and networking tools. Then we have Platform as a Service. In many cases within AWS, we can offload the operational burdens of tools such as databases, for example, to AWS. And so when certain things like that, databases, the management of databases like relational databases, NoSQL and graph databases and other services, when those are kind of abstracted away, that's when it crosses into Platform as a Service. And we are leveraging that platform to run our applications. And then lastly, as far as service models go, we have Software as a Service. And that's generally what most of us are building. We are leveraging the infrastructure and platforms that AWS provides to build our own software. So that's the definition of cloud computing, that we can go to Amazon, to the API, to the management console, and we can ask for a virtual machine, and we can get a virtual machine on demand. And that virtual machine has access to a network. We can communicate with the internet. And we can get that virtual machine at a low price because, millions of customers are pooling their resources and allowing AWS to offer those things at those low prices. And if we need to go from one EC2 instance to 100 to 1,000, we can do that. We can scale rapidly, very easily. If we need our underlying storage volumes to go from 1 gig to 1 terabyte to a petabyte, in a short period of time, we can do that as well. And no matter how we make use of AWS, we pay for what we use. So that's the definition of cloud computing, and we will be talking more about this and putting all of this into context throughout this course. Now let's talk about regions. Within AWS, we have a number of different regions all over the world. And regions are sort of the primary building block of AWS. It's the first thing that we start with. It's the first decision that we make. Before we start launching EC2 instances or storage volumes or whatever else, we first have to decide which region will these go into. From which region will we run our applications and serve our audience. And so let's take a look at the regions that are currently available. If we look here on the map, starting from the west coast of the US, we have the Oregon region, the California region, those are US West 1 and 2. We also have GovCloud West. Moving towards the East Coast, we have US East 2 in Ohio, US East 1 in Northern Virginia. We have Canada Central up in Montreal. Down into South America, we have Sao Paulo. Moving into Europe, we have Ireland, London, Paris, Frankfurt, Germany. And then moving farther east into Asia Pacific, we have Mumbai, Singapore, Sydney, Australia, Nishing, China, Beijing, China, Seoul, South Korea, and Tokyo, Japan. Now, these 18 regions are currently available for use, but there are a few more regions that are on the way. As of the time of this video, these regions are not yet online, but they will be soon. We have GovCloud East on the east coast of the US. We have Sweden, Bahrain, there in the Middle East, and then Hong Kong, right? So at some point here in the near future, if not already by the time of this video, we will have 22 regions available to run our applications and workloads. So a common question is, well, why do I choose one region over another? And it mainly comes down to several key things. One may be due to cost, right? Different services cost different amounts in different regions. So if the other reason might be that you want to serve that application to a particular audience, and you want that application to run close to that audience so that you can deliver the lowest latency. If you don't have an audience that you're worried about, if you're not really worried about latency, then you may look at it from a purely cost savings perspective. Another reason we might choose one region is because we need to consider data sovereignty and laws and compliance around data sovereignty. Certain countries and certain regions like the EU, for example, have certain laws regarding, certain types of data, whether it can leave that particular geographic region or not. So you may choose a region that satisfies security and compliance, right? So those are the regions that are available, and those are some of the reasons why we might choose one region over another. Now let's talk about availability zones. Within any particular region, before we can start deploying virtual machines and whatnot, we first choose a region. Within a region, we have multiple data centers to choose from, and those are called availability zones. Availability zones are analogous to a collection of data centers. AWS doesn't really go into a whole lot of detail about exactly how these are built, but from the little bit of documentation online that is available, we know that availability zones are collections of data centers, and you'll usually see within Amazon documentation of services, you will usually see them use the word facility, right? So they don't often talk about them in terms of data centers. They talk about them a lot of times by calling them facilities. And so each availability zone is a separate and independent collection of data centers. It could be one, it could be two or three, we don't really know. But the idea with availability zones, as we see here in this diagram, if we take a look at Oregon, US West 2 region, there are 3 availability zones within that region. And those could be tens of miles apart, right? They could be 10, 20, 30 miles apart. We don't really know, but we know that they're far enough apart so that if there's a natural disaster, then as few availability zones will be affected as possible. When Amazon builds availability zones, they take into consideration things like floodplains, fault lines, different power grids, those kinds of things, so that severe faults at the data center level can be isolated to that one group of data centers. And we still have our application running in other availability zones. So as we can see here, again, the US West 2 region has these 3 availability zones, US West 2A, 2B, and 2C, and each of these, they're all connected with private fiber. We have an incredible amount of bandwidth, very low latency bandwidth across that private fiber, Amazon-owned fiber that links these availability zones together. Our servers and applications can communicate between availability zones on the same private network. So we can load balance across multiple data centers. We can replicate data across multiple data centers. So by taking advantage of these multiple availability zones, thereby taking advantage of multiple data centers, we can be resilient not only to the loss of a device, but also resilient to the loss of a data center, right? So again, we can replicate data across these availability zones, we can load balance across these availability zones, and take advantage of that high-speed private fiber in order to greatly increase the fault tolerance, durability, and availability of our own applications. Now let's talk about edge locations. So edge locations within AWS powers several different services, namely Amazon CloudFront, which gives us a content delivery network, Route 53, which gives us a global DNS service, and API Gateway, which gives us serverless REST APIs. And so with edge locations, you can see here on the map we have a number of different edge locations. Not all of them are actually drawn, but we do have currently, at the time of this video, more than 100 edge locations worldwide. Many of them actually exist outside of a region. They could be just like a co-location or a small data center that AWS has and runs in that area specifically for an edge location. Now, we don't necessarily have direct access to the edge location itself. They're more passive. So if we were to use CloudFront, for example, and leverage the content delivery network, then we could have our application run in, say, US East in Virginia. And instead of making our European audience cross the Atlantic for every single request, we can use DNS to forward our European audience to an edge location in Europe so that they can download content that is cached on a server closest to them, right? So the first person who asks for a piece of content would have the latency of crossing the Atlantic, but then everyone else, perhaps the next million people who ask for that same URL, would benefit from having it cached closest to them. And then, of course, the same thing works with DNS. When we need to fulfill a DNS query, we want to fulfill that as quickly as possible with the lowest latency. And so by having DNS servers running in edge locations all over the world, this allows us to respond to DNS queries with the lowest latency as well. And all of these things, regions, availability zones, and edge locations, we will be referring back to as the course progresses. Now let's talk about the scope of services. Within AWS, we have several different scopes that we need to be aware of. That some services could be global, meaning that a change to a resource that's global happens across every region. Some other services could be regional, meaning that when we create, for example, an S3 bucket, then that bucket exists within a particular region, and it makes use of all of the availability zones in that region. And then lastly, we could have certain resources that are limited to a particular availability zone, like an EC2 instance, for example. When we launch an EC2 instance, a virtual machine, we choose which availability zone we want it to run in. And that one resource exists in that one availability zone. So some examples of this would be, for global services, these would be AWS IAM, the Identity and Access Management Service. When we create users and groups and roles and permission policies, when we create those within the Identity and Access Management Service, those are available to us across every region almost instantaneously. We also have Amazon CloudFront, which is, again, the content delivery network. When we make changes to that, the changes propagate globally across all of the edge locations, or at least the groups of edge locations that we choose to use. And then we also have Amazon Route 53, which is the global DNS service. When we make changes to our public DNS zones, those changes are propagated across the globe. For regional services, for example, we have Amazon DynamoDB. When we create a table within DynamoDB, that table and the data and the requests that we make against that table are handled within one particular region, whichever region we happen to choose. And of course, as we will talk about later, the underlying infrastructure and the durability and the replication happens across all of the availability zones within that one region. And the same is true for Amazon Simple Storage Service, or S3. When we create a bucket, that bucket exists within one region. We also have elastic load balancing and Amazon Virtual Private Cloud. So when we create load balancers, they allow us to load balance across numerous availability zones. So a load balancer exists within one region, allowing us to load balance across the data centers that are in that region. And Amazon Virtual Private Cloud, or VPC, gives us the ability to create isolated networks. And we design that network, we create subnets and use other tools to allow that, to form that network in a way that allows us to make use of multiple availability zones. And we'll talk more about that in an upcoming lesson. And then lastly, we have availability zone limited services. Services that when we create certain resources, those resources exist within a single availability zone. So Amazon Elastic Block Store, or EBS, when we create EBS storage volumes, those exist in a single availability zone, as does Amazon Elastic Compute Cloud, or EC2. When we launch EC2 instances, those exist in a single availability zone. When we divide our VPCs, our networks, into subnets, each subnet will also exist in a single availability zone. And like I said, we will talk more about that in an upcoming lesson. So in terms of moving forward with AWS and beginning to learn about the various services, it's important to keep in mind, what is the scope of this service? When we talk about a service, what's the scope? Is this a global, a regional, or an availability zone limited service? And again, we will keep all of this in context as we continue to discuss other services throughout this course. Securing our accounts and credentials and ensuring proper access to resources is a vital first step in securing our infrastructure, applications, and our data. In this lesson, we will review the Identity and Access Management Service and discuss the features and options we can leverage to secure access to our AWS environments. Now let's review an introduction to the Identity and Access Management Service. The IAM service is concerned with authentication and authorization to the AWS API. And within that service, we can create users, we can create groups of users, we can also create a number of other mechanisms. We can enforce a password policy, we can enable and enforce multi-factor authentication using a 6-digit PIN. And within the IAM service, again, all of these credentials, the users that we create, the policies that we create that govern permissions, all of this again applies to the AWS API. And so when we think about the things that we authenticate with, the different realms of authentication, we have the AWS API, and we also have operating systems. You know, when we launch an EC2 instance, then that EC2 instance will have its own operating system. And that is its own realm of authentication. It has its own set of credentials, a username and a password, or a username and a key pair, potentially. We also have things like our own application, which is, again, its own realm of authentication. It has some type of authentication, such as username and password being the most common. And so when we talk about the identity and access management service, and when we deal with the credentials that we get from that service, those credentials are used for the API and not for our own operating systems or our own applications. So when we think about leveraging AWS and authenticating against AWS in order to create resources and manage resources within our environments, we have a number of tools that we can use. And so here we have the CLI tools, the command line interface tools, and those leverage the API. They make calls to the API. We have the SDKs, right? The Python SDK, the Java SDK, which makes calls to the API. And then, of course, we also have the web-based management console, which makes calls to the API. So AWS is entirely API-driven. In fact, if you want to be even more technical about this particular slide, we could say that the CLI tools actually leverage the SDKs. So that there are really only two tools that communicate directly to AWS, and that would be the management console and the SDKs. The CLI tools leverage the SDKs. And so either way, whatever tool that we're using, whether it be the CLI tools, the SDKs for our own, writing our own applications, or leveraging the web-based management console, all of them make use of the API. Now, in terms of users and groups, of course, we have the ability to create users within the IAM service, and in some cases that might be appropriate. In other cases, it might be more appropriate to leverage federated users, which we will talk about in a later lesson. But if we do decide to create users within the IAM service, we can also create groups. Here on this slide, we have a number of different users. Geordie LaForge and Lieutenant Barkley, for example, would, of course, both be engineers, and we can assign those to the engineers group. Picard and Riker, of course, would be captains and commanders. We could put both of those into an admin group. Perhaps Picard might have super admin privileges or the ability to temporarily escalate to admin privileges, right? And then, of course, LaForge, for example, being a higher level user, perhaps being a team lead or a senior member of a team, may have the ability to be a member of multiple groups, right? So one user can be a member of multiple groups. Or we could create a way using roles that we'll talk about later to allow a user to temporarily escalate their privileges. And so users within the IAM service, they are created and they exist within the IAM service. We can give them the ability to log into the management console. We can also create and manage for each user what we call long-term access keys. And access keys are credentials that are used for the SDKs or the CLI tools. And generally, when we create long-term access keys for a user, that user will generally use those locally on their local machine so that they can manage AWS resources from their local machine. We would never embed those access keys within our code or environment variables that are deployed to production on EC2. We'll talk about that scenario more later on. Users can also each have a per user MFA device, right? So you can order a physical key fob from AWS. You can also, the easiest thing to do is leverage a virtual MFA device on your smartphone. There's Google Authenticator. There's another one that I prefer called Authy, A-U-T-H-Y, and a number of others. There's plenty of virtual authenticators that are available. We also, again, have groups. Groups are groups just like they are anywhere else. There's really not a whole lot to say about groups other than they cannot be nested. So you can create users, you can put them into groups. Another thing that we should be aware of within the Identity and Access Management Service would be the types of credentials. So looking here, we have a table of credential types, and I want to point out that here the most important one to keep in mind here would be the email and password, right? So if you find yourself logging in to the management console with an email address, you are logging in to the master account, and that master account has root access, right? Root access cannot be limited. So if your master credentials were compromised, someone could do some very serious damage to your production environments. I want to take a minute to slow down here and really kind of hound on this, because companies have gone out of business, right? Companies have gone out of business as a result of allowing these master credentials to be compromised. So we really want to take those seriously, take the protection, the security of those credentials very seriously. And so if you were just logging into the console with a username, not an email address, but a username, then we are logging into the console as an IAM user. And we're going to talk a little bit more about the differences between the root and an IAM user here in just a moment. For the access keys and secret key, these would be long-term, right? So this one here would be long-term credentials. Again, those are used to configure the CLI tools and the SDKs generally locally, so that we can use our local machine to communicate to the Amazon API in order to, create, update, delete, and otherwise manage our Amazon resources. Now, the last one here would be temporary credentials. So when we have the access and secret keys plus a session token and an expiration, then we are using temporary credentials, and we generally derive temporary credentials for role-based access. And role-based access can be used to delegate permissions to a user, to allow a user access temporarily into something they don't normally have access to. We could use role-based access to delegate permissions to an EC2 instance, for example, so that our applications that are running on that EC2 instance have the ability to retrieve temporary credentials. And again, we'll talk more about role-based access coming up. Right? So that's the overview of the identity and access management. Again, we will talk about all of these things in more detail as we go along. Now let's take a look at a demo for creating a user and a group.
Okay, so we are in the AWS Management Console, and we need to go to the Identity and Access Management Service. So there are a couple of ways we could go about that. If we scroll down the list underneath all services, then Identity and Access Management Service would be down here under Security, Identity, and Compliance. So here it is, the first one. We could click on that, or what I find to be easier is to, if you know the name of the service, you could just type it in here under the search bar and you can go right to it. We can also find it under here, and you can see that I've been there recently, so it's in my history. Of course, I could also scroll down here to Security, Identity, and Compliance. Or again, we could search there as well. The other way that we could find a particular service is that if we don't know the name of the service, then we could just type, what it is, the kind of functionality that we're looking for. So identity and access management would, of course, be related to users and groups and access, right? So we could type in users and scroll down, and there's IAM. We could type in access, and we could find IAM under there as well. So let's go ahead and go to the IAM service. And so here we're going to create a user and a couple of groups for that user to belong to. First, you can see that we have a dashboard for this particular service. Most services will have a dashboard that kind of summarizes what's going on in that service and then gives you ways of drilling down into the details. Okay, so you can see here our summary says that we have, one user and one group. So if we take a look at our current users, you'll see that in this particular account, I only have one user. I have mine. So here's the Richard user, and then my user account belongs to the admin group. And then we can see a number of other details like how old the access key is and how old the password is, those kinds of things. So that's a good way of highlighting, users who need to rotate their access keys or update their password. And we can also see that I have an MFA device, a virtual MFA device registered to that user. And we'll talk about that later on, as well as access keys. And so you can also see up here in the top that I am currently logged in as the Richard user. So let's go ahead and before we create a user, let's first create a couple of groups. So you can see we do have an admin group, and the admin group has basically the permissions to do everything. It's like a super admin or a super user. So I'm going to create a new group, and let's call this one developers. So maybe I'm going to add a few users that will be a part of a development team, and they will need certain level of access into AWS. And I might create another group for DBAs, another group for leads, and of course users could be members of multiple groups, right? So a member of the developers group, but could also be a member of the leads group or power user group and so on. There's all kinds of ways you could go about organizing that. So we'll go to next, and then now it's asking us to attach a policy, but we're going to come back to that, and we'll talk about policies later on. But for now, let's just go ahead and skip that, and we'll go ahead and create the group. And so we're going to do create one more group. We're going to call this one everyone. And the reason I do this is because there are certain types of permissions that I like to give everyone, and instead of adding those permissions to each individual user, I can add those kinds of permissions, those global universal permissions, to one group and then just put users into that group. And then if any one user needs to be a little bit different, I can always address that one user later on, right? So let's do the same thing. We'll create this everyone group. For now, we will skip the policy and we will come back to that. All right, we're going to revisit that point about policies here later on. So we'll go ahead and create the group, and now you can see we have our developers group, our everyone group. So now let's go ahead and create a user. And this user will be, let's say, a developer. So we can add a user. Let's just call this user A.Fowler for Amy Fowler. And so they have a username. And then down below, you'll see here what kind of access type. How will they be accessing AWS? Will they be accessing AWS resources programmatically, or will they be using the console, or will they be doing both? And so as a developer, they will probably be doing both. But if I were to select programmatic access, then you can see here it enables an access key and a secret key. We're going to talk about those later on, right? For now, I'm going to leave that off because ultimately, I don't want to have to find some secure way of transferring that sensitive information to the Amy Fowler user. Email is not appropriate for that kind of thing. You might trust email, you might trust things like Slack and other messaging tools, but when it comes to transferring credentials that could be used in dangerous ways, I would prefer that these users download these kinds of credentials directly from AWS rather than me downloading them and then transferring them to them. So I am going to enable management console access, and now I could do an auto-generated password, but I do like to check that the user must create a new password on next sign-in. That way they are forced to create a unique password that only they know. I can do the auto-generated password and then next go to permissions. And from here, we could add them to a group, which we will do. We could copy permissions from an existing user if you wanted to essentially duplicate another developer, right? If I finish with the A. Fowler user and I want to add, some other user, then I could copy permissions from the A. Fowler user. Or I could attach policies directly to the user. In some cases, that's appropriate. But for now, we are simply going to add the A. Fowler user to the developers and the everyone groups. Then we can go ahead and tag. The next one allows us to add tags to that user. And so we could use tags to organize our environment, right? So maybe this user, we could say name, Amy, Fowler, and we could, what department do they work in? And maybe she works in engineering and so on. So again, tags are pretty well our arbitrary key value pairs that we can use to organize our environment. So if we wanted to find certain resources based on a tag, it makes it a whole lot easier. And of course, when we get into other types of resources like EC2 and S3 and other things, we will talk about how tagging can also contribute to automation and cost attribution. So we'll go ahead and review, and you can see here we are creating the A. Fowler user with an auto-generated password, and they are parts of the developers and everyone group. All right. So let's go ahead and create that user. All right. So there we go. We've created the A. Fowler user, and from here we could download the user and the password in a CSV file. Or we could just show the password, copy it, and then send that to them over Slack or some other messaging system, and then ensure that they go and immediately log in and set their own unique password. All right, so we will continue to explore these kinds of things as the course goes on. So I'm going to go ahead and copy that, close that, and there you go. We've created the A. Fowler user and the developers and everyone groups, and like I said, we will continue to explore these things like access keys and policies more as we move forward.
Now let's talk about authorization via policies. Within the Identity and Access Management Service, we control authorization via policies. So we grant the permissions that our users need through writing policies. And these policies are written in JSON. And so we have a JSON template that describes the actions that are allowed to be performed on the resources that they're allowed to be performed, right? So again, we write these in JSON, and we have a couple of different types of policies. We have first managed policies. Managed policies are like first-class entities that exist on their own. A managed policy exists on its own, independent of any other entity. And so we have managed policies that are created and given to us by AWS. There's a whole long catalog of all kinds of different policies that provide different types of permissions depending on the use case. Some of those we will see in later demos. We also have customer-managed policies, policies that we can create that exist independently of anything else, and then because they are a managed policy, we can then apply that managed policy to numerous users, numerous groups, numerous roles, and so on. And then, of course, we have inline policies. Inline policies, as the name suggests, exist as an intrinsic part of some other entity like a user or a group. So, for example, if you had a user that had several different managed policies attached, you may have the need to create perhaps a very special policy that either allows or denies that one user a particular thing. So in cases where you are only applying a particular policy to one entity, it might make sense to make that as an inline policy. Now, when it comes to creating policies, we have a number of choices. We can create policies with the generator. Within the management console, the generator gives us a UI that we can use to select different services and different actions and different resources, and the generator will write the JSON for us. I generally like to start there because JSON is fairly syntax heavy. It relies on a lot of curly braces and commas and quotation marks and colons, and it can be rather easy to miss one. And so by allowing the generator to give me the JSON to begin with, then I can come back and modify that by hand. And then, of course, we can write those policies by hand if we want to or need to. So here's an example policy. In this example, first, let's take a look at the version. The version here, this date-based version, this date here in this example, the 2012-1017, this is a date-based version that represents when that policy standard was published by AWS. And we would pull this value, this 2012-1017, this particular value, we would pull from the documentation. So again, this represents the date that Amazon published that policy standard. It does not represent our version. And then next we have a list of statements. So here, even though it's singular, it is a list of multiple statements, right? So this is just a list of permissions that are being either allowed or denied. Next, we have the effect. Now, in this example, we are allowing, but there are really only two values. There's either allow or deny, right? So effect is specifying I'm either allowing this set of actions or denying this set of actions. And then we have the actions, and you can see here that these actions are namespaced according to service. So in this particular example, we are talking about the S3 get object action and the S3 put object action. If we were dealing with another service like EC2, then those actions would be namespaced with EC2. And the same would be true for Lambda and DynamoDB and other services. And so in this particular example, we are specifically talking about the ability to upload and download objects from S3. And then lastly, here we have the resource or a list of resources. Again, even though this particular key is spelled in the singular, it is a list of multiple resources, right? So this specifies the resources on which those actions may or may not be performed. And so in this particular example, we are actually talking about, notice here that we have the name of the bucket, and then we have /star. So in this particular example, we're talking about the ability to upload and download any object in this bucket. So there is a difference here between the bucket and objects in the bucket. So moving on to another example policy to show you what's possible, we can also apply conditions to our policies. We can create very, very fine-grained control over not only the actions and resources, but also the conditions under which those requests happen, right? So in this particular example, we're saying that we're going to allow the request, right? And we're talking about uploading and downloading, but we're going to take this a step further and apply conditions. So this particular block right here would apply conditions. And again, those give us more granular control over, when or from where the request is allowed or denied. So here what we're saying is that the IP address that's being evaluated needs to match the source IP address. And in this particular case, it should come from a particular range, right? In this case, a /30 would be a range of, I believe, 4 IP addresses. And so if, for example, if your on-premises had, a small range of static IP addresses, and you wanted to say, well, our employees are allowed to perform these actions, but only from the office. They can't do these things from home. They can't do them from Starbucks down the street. They can only do them from the office. You could use a policy like this that limits it according to IP address. And so this particular piece right here, the AWS : source IP, this is a global context key. There are a lot of different context keys that we can look to in order to create, again, very fine-grained control over the conditions under which these requests are happening. So here, essentially what we're saying, again, just to review that real quick, is to say that this particular action, the get object or put object actions, are allowed on objects in this bucket so long as they originated from a particular range of IP addresses. Another example that we can look to here says that we are going to deny. You'll see here that we're using the deny action or the deny effect, and we're saying we're going to deny the ability to upload or download when the XAMZ server-side encryption header does not equal AES 256, right? So under the condition that that particular header is not set or does not equal that particular value, then those requests will be denied. So a common question that I hear is, if permissions have to be explicitly allowed, then why would we ever need an explicit deny? And this is one of those examples where in one statement or policy we say that you're allowed to perform these, but another statement might say we're just going to deny certain things under certain conditions, right? In this case, we're denying if you are not leveraging server-side encryption. Another thing that we can make use of within policies are policy variables. Now in this example, again, what we're saying is that we want to allow, you'll notice here that we are allowing the ability to perform, and you'll notice that we have asterisks here, so there are a number of actions that contain the words access key, right? It could be delete access key, change access key, those kinds of things, delete access key. And so this particular action actually represents, in shorthand, represents a number of different actions because of the asterisks that we have there. And then we also have change password. So what we're saying here is that we want to allow users to perform these actions, changing access keys and changing passwords, but we want to limit that to their own user, right? I want the users within my organization to be able to change their own password or to change and update, rotate their own access keys, but I don't want users modifying the passwords or access keys of other users. And so in this particular policy, these policy variables that we have here allow us to generalize policies and still maintain a secure policy, right? So in the case where we want to restrict users to their own user, without these variables, we would have to write a policy for every single user. But by using this particular variable, you'll notice here this variable is kind of, for anyone who has ever written templating, this might look fairly familiar, where we have $ curly brace, and then here AWS username. So this becomes a variable. During the evaluation of this policy, this particular variable will be replaced by the particular user who was making the request. So in my case, my username is Richard. And so during the evaluation, it will say user/Richard. And so by applying this one policy to a group of users, it allows each individual user to modify their own access keys or password. And so once we have those policies in place, it's important, in order for us to really understand policies and permissions, we also need to understand the evaluation logic, right? So let's take a look here at this diagram that describes the evaluation logic. So we start with the API request. And again, the API request could have been originated through the management console, through the CLI tools, through the SDKs. There's any time any resource is created, updated, deleted, or otherwise managed, it starts with an API request. And so then the very first step is to take all of the statements across all of the policies. Remember that any one entity within the IAM service, like a user, for example, or a group, any one entity can have multiple policies attached to it. And as we saw in those examples, any one policy can have multiple statements. And so the very first step in the evaluation is to merge all of those statements from all of the attached policies. And then the evaluation starts looking through each one of those statements. Then the very first question is, does the policy explicitly deny? Is this particular action on this particular resource under these conditions, is that explicitly denied? And so if the answer is yes, if it finds an explicit deny, then of course the request will be denied. And so you'll see here that by looking for an explicit deny first, it allows us to create more secure control over our permissions. So there could be scenarios where you may want to provide one policy that gives a user broad access, but then another policy that denies certain levels of access that might be more dangerous. And so by writing it this way, it allows us to be not only more secure, but also more flexible in how we write our policies. And then if an explicit deny is not found, we then look for an explicit allow. So if there is no explicit allow, then the policy would, or the request would be denied. And so the only way for a request to be allowed is for there to be no explicit denies and an explicit allow, right? So it's a safety first kind of mechanism. So remember that when it comes to granting permissions to your users on particular resources within AWS, we achieve that by writing policies. Now let's review a demo of creating and attaching policies.
All right, so from the IAM dashboard, let's go back to our users. And here is the A. Fowler user, and then you can see that we added her to the developers and everyone groups. So at this point, if we were to look at that user and see the permissions, it actually says this user doesn't have any permissions. And so for a user to be able to do anything, we have to explicitly allow those permissions. So a user is denied everything by default. And the only way that you can do anything is to have those permissions explicitly allowed. And so let's take a look at the groups. So the developers group should be allowed to perform certain things in this example. And then the everyone group will be allowed certain things. Let's just start with the developers group. We can click on it here, and that will take us to the details for the developers group. So if we go to permissions, you can see there are no policies applied, no inline policies. So this group is not providing any permissions right now. So let's go ahead and attach a couple of policies. So we can see here that AWS, if we filter by AWS managed policies, we can see that AWS gives us a very long list of policies that we can use for various features. There are more than 400 policies that AWS provides. So as far as the developers group go, I imagine that for this particular example, I'm imagining a scenario where we have a group of developers that are writing code for Lambda and using S3 and perhaps DynamoDB, right? So let's just keep it simple. And so let's just say we need access to Lambda. So I can type in Lambda, and let's go down here to Lambda full access. So if we go ahead and add that one, then that would give our developers full access to Lambda. They can create functions, they can manage them, they can delete them if they need to. So let's do the same thing for S3. And we can say, let's give them S3 full access, and let's do the same thing for DynamoDB. I believe it's this first one. If we hover over it there, you can see the little pop-up says Amazon DynamoDB full access. So if we attach those policies, now, because the developers group has those policies applied, and the Amy Fowler user is a part of that group, now Amy has those permissions. She has full access to Lambda, S3, and DynamoDB. Now, we may not want them to have absolute full access. There could be certain actions that we find to be dangerous, right? And so maybe we want to limit that access to some degree. So there are a number of ways that we could go about this. We could write our own policy that only gives them the certain actions. Or we could, like we just did, we could give them full access and then take some of that access away. Let's go back to, so let's go ahead and do it as an inline, mainly just to show you how an inline policy applies. So generally, I use an inline policy when it only applies to one entity. So in this case, we could say, in this example, we could say that the policy that we're going to create in order to limit certain access only applies to this one group, that this kind of policy would not apply to admins or DBAs or what have you. So we can use the policy generator, and the policy generator, as you can see, gives us the ability to choose different kinds of, we can either allow or deny. In this case, we're going to deny certain abilities. And so let's just start with DynamoDB. Again, we're going to keep it simple and scroll down here in the list to, it's not AWS, it's Amazon DynamoDB. All right, so let's choose Amazon DynamoDB. And I'm going to come down here to delete table. And so what we're saying is we want to deny the ability to perform the DynamoDB delete table action, and we could say we can use an asterisk here to say on any resource, right? You can't delete any table. So an Amazon resource name or an ARN is a way of uniquely identifying any one resource across all accounts, across all services, and across all regions, right? So any one of the literally trillions of resources within AWS can be uniquely identified using an ARN, right? So then we add that statement, and then we can go next, and now you'll see that the generator created the JSON for us. So we're saying that we are going to deny. So let's just call this one deny dangerous. So certain actions you might feel are just dangerous, and you don't want them to be able to perform those actions, right? And so what we're saying deny the ability to delete table. They can create tables, they can modify attributes of the table, they can write data, read data, but they can't delete a table. And perhaps we save that kind of thing for an admin or a team lead or something else. That way we can ensure that or help ensure that tables aren't being deleted by accident. So let's go ahead and apply that policy. And so now you can see that we have these three managed policies. These policies are created and managed by AWS. They are first-class objects. They exist on their own, and they are applied, in this case, to the group. They could be applied to users or roles. And then down here we have an inline policy, and as the name suggests, inline simply means that this policy is embedded, right? It doesn't exist on its own. It exists as an intrinsic part of this group. And so another thing that you might notice here is that we actually have two policies that give conflicting information. The DynamoDB full access, if we were to go there and take a look at the permissions, you can see that it's allowing all of these actions. There's a lot of different kinds of things in here, actually. There are a lot of different things besides DynamoDB. And so one of them here is DynamoDB asterisk, right? So this one here and DAX, which is DynamoDB accelerator. So DynamoDB, we're saying that they are allowed to perform all actions, right? So if we go back, so the DynamoDB full access says, well, you're allowed to do everything, and then down here it says you're not allowed to do delete table. So when you have conflicting policies like that, when you have one policy that says you're allowed to do something and another policy that says you are not allowed to do something, the deny will always win. The deny rule will always take precedence, right? So it doesn't matter what order these policies are listed in. They all get kind of merged together into one list, and the algorithm looks for this deny first, right? So the fact that we have a deny in there means that if they try to delete a table, they will be denied, even though some other policy says that they're allowed to, right? So that's just one possibility, one way of going about things. Okay, so now our developers, and we could apply the similar things to Lambda and S3, right? We might not want, we could edit that policy to prevent this group from deleting S3 buckets, and, from maybe there's certain things about Lambda that we don't want them to do, like deleting functions. If when it comes to EC2, we may want to prevent people from terminating EC2 instances. Another way to go about this is to say, well, you're allowed to do what you want, but only under certain conditions. So we can create policies that say, well, deny those actions if they don't conform to a certain set of policies or a certain set of rules. Like the instance size should be a particular size. You should be doing this from a particular IP address, those kinds of things. So anyway, the IAM policy language is very flexible. It allows us to grant very granular control over what our users are allowed to do. Okay, so we've satisfied the requirements for developers, but there is one more group, the everyone group, and we want to apply a couple of policies and create one more that will apply specifically to everyone. So those would be, one, let's go ahead and attach a policy, and again, this is going to be an AWS managed policy, and we are searching for IAM, and there are a couple here. One is the IAM read-only, so we want when this user logs into, when the Amy Fowler user logs into the console, we want her to be able to see her own user record and be able to manage her own password and manage her own access keys. And that's true for every user, right? So by giving them IAM read-only, it allows them to essentially see a list of users in the console and then get details about their own user. And then another one here is called IAM user change password. So this policy allows any user to change their own password, right? Let's go ahead and attach those, and then we can take a look at that. So the IAM user change password, let's take a look at that policy. And you can see that it's saying it's allowing the IAM change password action for this particular resource. And notice what's going on. It's an ARN, an Amazon resource name, and we are specifying, instead of specifying a unique user, we're using a variable. You'll notice this $ curly brace AWS : username, and that is an IAM variable. And so at the time authorization is performed, at the time these policies are evaluated, that variable is replaced with a.fowler. And so the beautiful thing about this policy is that it's a generalized policy that we can attach to multiple users, and it still only affects the user that's actually trying to do something. All right? And so now we have allowed everyone to change their password and read information from IAM. So let's create one more policy that would apply to everyone. And we could do it as an inline policy, but just to show how we could go about creating a managed policy, let's do it that way. So we can go here again to policies, and here this is where these are all managed policies. They exist on their own. So let's create one. And again, we get into the visual editor. And when we think about the purpose of this policy, the purpose of this policy is to allow users to manage their own access keys. We're going to talk about access keys more later on, but for now, let's just focus on the permissions that are required to do that. And so those would be under the IAM service, so I can search for IAM and say, all right, we are going to specify the actions that are allowed. And generally, I want to find all of the ones that are related to access keys. So I do see one here, but I'm going to go ahead and hit Control F and search for access key. That way, I can have my browser highlight all of the places where access keys show up. So there's list access keys, and if we go under read, we should see there's get access key last used. Let's find the next one, list access keys, and then under write, we should have a few more. Create access key and delete access key and update access key. Right, so those are the ones that we're going to provide. So you can see that we essentially chose the IAM actions, or we chose the IAM service, then we chose specific actions. And now, if we scroll down here, it says here that you chose actions that require the user resource type. So we need to specify a particular user. And here we can say any, and we don't really need any conditions right now. And now if we go back to the JSON, you can see that it is writing the JSON for us, right? And so we're going to modify this, and this is pretty common. I find myself doing this a lot, where I'll use the editor to select a number of different things and then use the JSON to make minor modifications to the syntax. And so here, again, the asterisk here means every user, which means if I were to apply this policy to the everyone group, then everyone would be allowed to change everyone else's access keys, and we don't want that. We only want each user to be able to modify their own access keys. So instead of using an asterisk there, we can use that variable, AWS username. And so again, during the authorization evaluation, this variable will be replaced by, for example, a dot Fowler. Okay, so one last thing that I want to point out is you'll notice that every one of these actions include the term access key, right? So that pattern, access key, is present within each one of these actions. So one thing that we can do within policies is we can make policies shorter and more succinct by using asterisks. So we can replace all of these lines we can get rid of and use asterisks. So if we go asterisk, access key, asterisk, then that one line will include all the necessary access key related actions. So now we are essentially, this policy will allow each user to modify their own access keys. All right, so let's go ahead and review that. Let's name this one user self-manage access keys. And we'll say allows each user to manage their own access keys. All right, and then it also shows you, a number of different details down here as well. So let's go ahead and create that policy. And then let's go back to groups, go back to everyone, and attach that policy. All right, so then we can filter by customer managed, and we can search for self. There it is, user self manage access keys. Let's go ahead and attach that one. So there we go. A user can change their own password. A user can read information from IAM, and a user can modify their own access keys. And so if we go back to users and take a look at the A.Fowler user, then we can see that Amy is inheriting all the permissions from both groups, right? From the developers group and from the everyone group. And then here's that inline policy denying those dangerous things like delete tables. Right, so that's how we can apply permissions and control authorization by creating and applying access policies.
Now let's take a look at a demo of creating access keys.
From the Identity and Access Management console, let's go ahead and click on Users. And here, because I'm logged in as an admin, you can see my Richard user is a part of the admin group, and that's who I'm logged in as. As an admin, I would have permissions to manage the access keys for other people, right? So I could go to the Amy Fowler's user, and I could go to the Security Credentials tab, scroll down, and see that she currently has no access keys. And again, access keys are a way of configuring things like your command line interface tools, the SDKs, third-party tools, and most often I would say that we end up doing that locally so that we can develop against or manage AWS resources from our local machines. And we can see that Amy does not have any yet, and I could create them for her, right? So if I clicked on this button and created those access keys, then I would have to find a secure way of transferring those credentials to her. And in my opinion, I don't really think that there is such a thing, unless you want to do some kind of a, SSH thing and use a FIFO, right? On SSH. That might be secure. But I don't think that email is secure, and because it could leave those credentials exposed to being used in ways that they weren't intended or being used maliciously. And the same is true for just about any messaging app, right? If you send that message, then those credentials are there to be found by someone, right? So I prefer to allow or empower my users, in this case Amy, to go to AWS and manage her own access keys herself, right? So I'm not going to do it for her. So I'm going to go ahead and log out, and I'm going to sign in as that user, right? So I'm going to go here to the management console, and I'm going to log in as A.Fowler, and we're going to use the auto-generated password that we got earlier when we created that user. Right, so I'm going to paste that password. So now that we've logged in, you can see here it says you must change your password to continue, and that way Amy, by forcing our users to do that, in this case, only Amy would know what that password is. Right, so I'm going to go ahead and paste that old one again and create a new one. Go ahead and confirm that one. And now you can see we're logged in as Amy. And of course she should have, being a member of the everyone group, she would have access to IAM, or at least read access to IAM. And so a lot of these resources here, users, roles, policies, groups, this particular user has the ability to view those things, but they don't have the ability to modify those except for their own password and their own access keys. We could either go here and click on the Amy Fowler user, or you could go to my security credentials. So either way, Amy could get to those things in either of those two ways. So the password is fresh. We don't need to worry about that. Let's go down here to the access keys, and we will go ahead and create access key. And that's all we have to do. Just like that, we've created an access key. And what I do want to point out is this note right here. It says this is the only time that the secret access key can be viewed or downloaded. So this is sort of like a public-private key pair. The way that these access keys work is that when the Amazon SDKs or the CLI tools or third-party tools access the API, the metadata about that particular request, along with the access key ID and the secret, we can go ahead and show the secret here. So both of these values are used to create a signature, but only the access key is delivered in the request. And so that the secret is kept secret because it's kept locally. AWS has a copy of the secret. And so we create a signature based on a combination of the access metadata, the access key, and the secret access key. We pass along the access key in that request, and then on Amazon's side, they essentially replay that signature. They recreate it from the secret key that they have stored on their side. And so if the signature matches, then it's authenticated. Right. So again, the secret key never actually is delivered anywhere. It's meant to remain local and it's meant to remain secret. Only the access key. That's why, like if we could download the CSV file, or I could copy and paste all of this. I'm going to go ahead and copy that and then paste that into my text editor, and then I can close this, and you can see that now we've created that access key. And we have no ability to see the secret again. Amazon will not reveal that. Even though they have it and they can use it to verify the signature and validate the request or authenticate and authorize, they won't reveal it. But so the access key is essentially the public part, and it's meant to be included in those requests. And it's also not really a big deal that Amazon is displaying that access key in plain text, because you need both. You need both the access and the secret, right? And we keep the secret local, and we keep it hidden, right? So I can use these two keys now to configure the CLI tools, the local SDKs, so that when I'm using those tools or third-party tools that I might have installed locally, I can use those to gain access to AWS resources. So we have this one key. And ideally, right, you can see here that it hasn't been used yet. And ideally, we rotate these keys, at least every 90 days. And so you can actually see, if we go back to users, you can see that this particular key has not been used, but mine is 40 days old, right? So it's still considered to be, a secure key. After 90 days, then you'll start to get a warning. This check mark will go to an exclamation point, and then after 365 days, once a key is a year old, you'll get a red warning. Let's just go back there to my security credentials, and if you need to rotate those keys, then of course we have the ability, we could create two keys, right? We could create a second one, copy all of that information, and then you can see that one was created earlier. So if we wanted to rotate those keys, then we could start to use the new one and then come back and delete the old one. So we could either make it inactive, which means it still exists, but it's just not able to be used to authenticate against the API, or we could just delete it, right? So I could go ahead and delete the old one. And here the console wants us to confirm that, yes, we do intend to do that. You'll see that the console does this kind of thing a lot as a way to help prevent accidental deletion of resources. So we'll go ahead and delete that. And so just like that, we've actually rotated the key, right? So you've seen that we've created two access keys. We've deleted one, so which is essentially the process of rotating keys. And so that's how we would go about managing access keys.
Now let's take some time to understand roles. Within AWS, a really powerful mechanism for delegating permissions are roles. And before we can understand roles, let's first take a moment to understand why we want to use them. Let's talk about anti-patterns, credential anti-patterns. And so some of the things that we don't want to do, the things that we would like to avoid, would be things like embedding access keys in our code. Remember, we talked about how users can create access keys, and then we can use those access keys to configure our local development environments so that we can manage AWS from our local machines. Those long-term access keys should never be embedded within code, because by doing so, there's a number of issues with that. By embedding them in code or even within environment variables, now we run the risk of those credentials being exposed and being seen by other people. I've heard of scenarios of read reports and even have friends of mine where this has happened, where credentials have been committed into repos and into public repos, like on GitHub. And as a result, people out there, who knows who, found those credentials. In fact, there are bots out there that are designed to scan public repositories looking for credentials, right? And so I've read stories of developers exposing credentials within public repos and then being surprised by an Amazon bill at the end of the month that's thousands of dollars beyond what they normally pay, because people use those credentials to create very expensive resources. And so the other aspect is that people have used credentials to delete resources, right? Another perspective on that is that it could be that members of your team find those credentials that are embedded and end up using them in ways that they weren't intended. Even if it's not malicious, they're just being used for purposes that they shouldn't be used for, right? So we really want to avoid embedding our code or embedding our credentials within code or within environment variables. The other logistical challenge with embedding credentials within our code is that now if we want to rotate those credentials like we should be doing regularly, we have to recommit, repush, remerge, retest, rebuild, redeploy code just to rotate credentials. And that's not really a good reason to go through all of that. We have a better mechanism. And so another thing that we don't want to do is share credentials. If you have an organization, then and members of your organization need to access Amazon, then each member should have their own credentials, right? So we don't want to share credentials with third parties. We don't want to have to create, dummy users in order to share credentials. We certainly don't want to share one set of credentials with hundreds of enterprise users. And we don't want to share credentials with potentially millions of web or application users, right? So imagine deploying a web or mobile application. By embedding credentials in that application, you are essentially sharing those credentials across millions, potentially millions of users. We have other mechanisms to handle that. And so the best practices for credentials in this regard to avoid those things would be to use temporary credentials. And we can delegate permissions to, for example, an EC2 instance. So instead of embedding our credentials in our code and then deploying code to that instance, if we instead give the instance a way to retrieve permission or retrieve credentials, then we can provide our application a way to automatically retrieve credentials that automatically expire and then get automatically renewed. And so we can delegate permissions to EC2 instances, to other Amazon services. We can grant users within our own account the ability to temporarily elevate their privileges, or we can grant permissions to a separate account. And that separate account could be one that you own, or it could be a third party. It's really common for organizations within AWS to have multiple accounts. And it could be that you have an account dedicated for development, and it could be that you have an account dedicated for production, or different business departments or business units may have their own accounts in order to achieve, some type of isolation, secure isolation between different things, right? And so using cross-account roles allows us to log into one account and then temporarily gain access into another account. That also works really well for client-vendor relationships, right? So you take myself, for an example, when I'm not teaching classes or not recording videos, I'm consulting. And when I work with clients, I tell them, hey, you don't need to create a user for me. I already have a user. And the least secure thing you can do is create a user and then email me the username and password. That's exactly the kind of thing we want to avoid. Instead, create a role for me and then email me the ID of that role. And then that way I can assume that role and gain access into your account. And we will talk about how to do those things in upcoming lessons. Now let's talk about roles for EC2. Earlier we talked about how we don't want to embed credentials within our code. But oftentimes within the ecosystem of AWS, it's very common for applications that are running on EC2 to need to talk to other Amazon services. And in order to do that, they need to make API calls. To make API calls, you need credentials, right? So how do we allow our application those kinds of credentials without embedding credentials? We can do that with roles. So taking a look at this diagram, here we have an application that leverages the SDK running on EC2. And that application needs to authenticate against the API in order to access other services such as S3 or DynamoDB or Kinesis or Simple Queue Service. The list goes on. Any other service would require permission to access that through the API. And so we can apply a role to the instance. In this example, we create a role specifically for the job that this instance will perform. And we apply that role to the instance, and that gives us a way to apply permissions and retrieve temporary credentials. Next, we apply a policy to that role, right? So remember that we talked about policies as a way of defining and describing the permissions that a particular entity has. In this case, a role for EC2. And so we would specify all of the actions and resources that this particular application needs. And generally, we want to follow the principle of least privilege, right? Not every application needs to talk to every service. And if an application needs to talk to DynamoDB, it doesn't need to talk to every table. If an application needs to communicate with S3, it doesn't need to download or access every bucket. So we give the application exactly what it needs and nothing more. If the application at some point needs more, we can provide that elevated privilege later on. And so now that we have the role applied to the instance, we have a policy applied to the role, then the next step in this process would be that the hypervisor for EC2, the hypervisor would make a call to the security token service to retrieve temporary credentials based on that role. And those temporary credentials generally expire every 15 minutes or so. And 5 minutes prior to expiration, the hypervisor will again make a call, retrieve fresh credentials, and make those available. And those are made available through what we call the instance metadata service. And so if you're writing your application leveraging the Amazon SDKs, the SDKs are written in a way where they look for credentials in certain places in a certain order. And so if you're running your application locally, then you can embed credentials locally in configuration files, in environment variables, and that's fine, and that's normal if you're running locally. when you deploy that application to production, you won't have credentials embedded in configuration files or in environment variables. And so in those cases, the SDK will automatically then look to the instance metadata service. And so the instance metadata service, again, is a way for an instance to retrieve information about itself. And we'll talk more in more detail about the instance metadata service later on. And so the SDK, again, retrieves credentials from the metadata service and then uses those temporary credentials to authenticate against the API for the purpose of accessing other services, right? So that allows us to avoid embedding credentials within our code. Now let's talk about roles for cross-account access. So it's very common for organizations to have multiple accounts. A common pattern might be that you have an admin account that is used to manage users and groups. And then you have other accounts for perhaps different environments or different business units. And so a common pattern that I've followed quite a bit of across numerous production workloads and in different clients is to have an admin account that I have my users and my groups of users, and I have other mechanisms for centralizing the publication or collection of logs and different things like that for governance. And then development, testing, and production environments are each in their own account. And by doing that, we gain isolation between those different accounts. And so in this particular example, we're going to take a look at how we can leverage roles to allow a user that belongs to one account to gain access to resources that belongs to another account. And so in this example here, again, we have two different accounts. One we call admin and one we call production, right? So remember that within Amazon, there's nothing that Amazon would have that would mark an account as being admin or production or development. These are just labels that we give our accounts in order to know how we are using them. But otherwise, accounts are all functionally the same. And so here, the first thing that we're going to start with is a role. You'll notice that we have the user in the admin account. We have a role in the production account. And here, cross-account roles give us a secure way to allow access to resources in one account from another account. When we create that role, what we're also creating is what we call a trust relationship. And so a trust relationship tells AWS that the production account is trusting or delegating permissions to the admin account. And then the admin account can then further delegate those permissions to its users or groups of users. Keep in mind that in this particular example, or any example for that matter, the trusted account, in this case the admin account, cannot delegate any more than what it's given, right? And so we have a trust relationship that says, well, the production account, through this role, the production account is trusting the admin account. And so we have the admin role, and now we apply a policy to that role that grants all of the necessary permissions, whatever permissions are needed by this role. And perhaps in some cases, it could be a super admin that's allowed to do everything. In other cases, it may be just a DBA or someone dedicated to networking or someone dedicated to deployments, right? They get the permission that they need through this role and through the policies that are applied to this role. And then for the user in the admin account, the critical permission that user needs is what we call allow assume role, right? So that's the critical permission that would allow that user in the admin account to assume the role in another account, in the production account. And so by having that put in place and having that policy applied to our user, that user then makes a call to the security token service to assume that role and retrieve temporary credentials. They can then use those temporary credentials to access resources in that other account. And that is how we can make use of cross-account roles in order to allow users in one account to access resources in another account. Now let's take a look at a demo of creating roles.
From the AWS Management Console dashboard, in order to create roles, those are found under the IAM service. So since we've been there recently, we can go here, just follow that link. And you can see that we already have a number of roles. It shows us that I have 25 different roles in this particular account. These are things that I've done in the past. So if we click on that, there's a number of different roles that some of these were created for me by Amazon services. Some of these I created myself. And so we're going to create a couple of different roles here. And again, you can see I am logged in as my admin user. So whatever user is in the console trying to do this would, of course, need the permissions to create roles and permissions to assign policies to those roles. So let's first create a role for EC2, right? So there are several different types of roles. You can see that we have roles for AWS services that allows the service to do things on your behalf, such as EC2, Lambda, and so on. We have another AWS account, either belonging to you or a third party. And then, of course, we have web identity, right? So we're going to talk a lot about that kind of thing much more later on. Throughout the course, we'll talk more about different ways we can use web identity so that our users can log in with things like Facebook, Google, Twitter, and so on. And then, of course, we could create a role that's specifically meant for federation. So in this particular case, let's just create a role for EC2. So let's say that we've chosen EC2, and let's say that we have an application that will be deployed directly to an EC2 instance, and that application needs to communicate to S3 or DynamoDB or whatever. Then the better way of going about giving that application permissions is to give the instance permission, and then or attach a role to the instance. Then the application can retrieve temporary credentials based on that role. All right, so now it's saying attach permissions. So let's do a search for S3 and see. We could say S3 full access or read-only access. Let's just do that one for now, right? Whatever permissions you apply, the really important thing here is that whatever permissions you apply to this role are then available from that instance, right? So for example, if we were to give S3 full access, then S3 full access would allow this role to create buckets, create objects, and delete objects and delete buckets. So the important thing to realize is that anyone or any person or any application that has access to that instance would then have access to the temporary credentials, and they could then use those temporary credentials to perform the actions that are allowed by these policies, right? So if I grant this role S3 full access and someone is able to somehow compromise that instance and gain remote access to it, they could find those temporary credentials and then on that instance use them to potentially delete S3 resources, right? So we want to be very careful about the permissions that we give to these kinds of roles. We should be following the principle of least privilege and giving our applications the permissions that they need and no more, right? So just for example, if we wanted an application to be able to read everything from S3 but not delete, not create new things, then we could, just as a quick example, say S3 read-only access. Or we could create a policy specifically for that application, which is the ideal thing to do, right? But we're going to keep it simple for now. Ideally, I would normally, in a production scenario, I would create a policy specifically for the way in which those credentials would be used, specifically for that application on that instance. But for now, let's just keep it simple for now and attach this existing read-only policy. All right, we can go next to tags. And again, tags can help us organize our environment. We could say what environment this is for. Maybe it's for dev. We can say what application, right? And maybe we call this our fundamentals application. And we could add, any kind of key value pair that helps us make sense and help us organize the resources in our environment. All right, so let's go and review that. We're going to call this one fundamentals application. And then it says, here we're going to say allows fundamentals application, our imaginary fundamentals application, to read everything from S3. And again, just going back to a point I made earlier, I want to reiterate it because it's so important that I've given this instance, read access across all of S3. And so if I have sensitive data stored in a bucket somewhere, be it personally identifiable information, protected health information, any kind of credential stores or classified information if you're working in GovCloud, then by applying this policy to this role, we are essentially granting that instance access to that data, right? So again, we want to be really careful about the permissions that we are giving to our applications and to our EC2 instances. And especially in the case of EC2 instances, when we are granting permissions to them via roles like this, we want to, take extra precaution to, really prevent unwarranted or unauthorized remote access. All right, so let's go ahead and create that role. And if we scroll down here, here's our fundamentals role, right? And you can see here that it has a specific role ARN, and it also has an instance profile. So the instance profile is what is actually applied directly to the instances. The role is applied to the profile is applied to the instances. And so it's through that mechanism that the instance can retrieve temporary credentials and then use those credentials to access whatever resources were granted access to, in this case S3. All right, that's creating roles for EC2. Let's take a look at creating a role for another account. This is a very common pattern and a very powerful pattern, right? And so we need to find our account ID, right? So we need the identifier of the account, and it could be an account that you own or an account belonging to a third party. Okay, so we're going to do here, I'm going to paste the account number of another account that I have. And for you, if you have multiple accounts, then you could use one of your other accounts. So I'm going to paste that account number. Okay, so we've pasted our account ID, and then we have a couple of options. If it's our own account, then we don't necessarily have to do either of these other two things. But if we are sharing, if we're creating this role that is meant to be assumed by someone in a third party, like a vendor or a client, then we might require an external ID. That's just an extra level of validation. So if I do that, it says here you can increase the security of your role by requiring an optional external identifier, right, which prevents confused deputy attacks. So we could apply that external ID for that other resource or for that third party. In this case, since it's an account I own, I don't need to worry about it. I could also require MFA or multi-factor authentication. And so I generally like that one. It just makes me feel better that if they are assuming this account or assuming this role, then they are going to gain access to resources in this account, right? And so this could be a production account. That's a common practice where users are in, let's say, like an admin account, but then we give them cross-account access by way of a cross-account role and into the production account or, some other account, right? So again, by allowing them to assume this cross-account role, we we give them access to all of the resources in that account, or at least what they are permitted to access based on this role. And so let's go ahead and say next permissions. And again, we need to attach a policy that grants, some type of permission. And again, we could create a policy specifically for what this role will be used for. In this case, again, let's just, as a quick example, do S3 read-only. We could also do EC2 read-only access, for example, and say next tags. And again, we could apply tags to this role if we needed to. We'll go ahead and skip that for now and review that, and we'll call this one prod account read access, right? So this will say allows users who assume this role to read S3 and EC2 in production account. Okay, so now that we've got all of that in place, we can say create role. And if we search for prod, here it is. Here's our prod account role. And so now, in order for a user within the current account to assume that one, or for a user to assume that, we would give them this ARN, right? So we could, and this value is safe to email because it's not really secret, and just having this information doesn't really allow you to do anything with it. Anyone trying to use this would have to be allowed to use it, right? And the only person allowed to use it is the person in this account, right? Someone who has been explicitly an IAM user who has explicitly been granted the ability to assume this particular role. So that's how we can create roles for both EC2 and cross account.
Now let's talk about federated users. Earlier, we talked about creating users within the identity and access management service. And for small teams, that works really well. But for larger teams, when you're in, especially an enterprise that has perhaps hundreds or maybe even thousands of users that already exist, that also need access to AWS, then we want to ideally leverage our existing directories. So there are plenty of existing directories available. So a lot of organizations already use things like LDAP or Microsoft Active Directory or some other type of directory, right? And we want to enable the ability to essentially reuse those accounts. We don't want to have to duplicate those accounts between an on-premise directory and within the identity and access management service, because there's a lot of issues with that. One, it's kind of a pain to do, and two, if they leave the company, we have to remember to remove them from two places. And so by leveraging federation, we can leverage that existing user base that we already have. And of course, the same thing applies to web and mobile application users, right? We have users out there that want to authenticate against our web or mobile application, but we don't want to necessarily force them to go through the process of account creation. They already have an account somewhere, and we can leverage that existing account by allowing them to log in with Facebook, log in with Google or Twitter, or basically any other OpenID provider. And so in terms of federation, we have a lot of options that are available to us. First, we have the SAML. And SAML 2.0 allows us to grant access to the AWS Management Console. It allows us to gain access to temporary access keys that can be used to configure the CLI and other API access. And so with SAML, the nice benefit of SAML is that we can enable this kind of federation with no coding whatsoever. We simply configure our on-premises directories and the AWS Identity and Access Management Service to communicate to one another using SAML. And when our enterprise users authenticate against that on-premises directory, through the communication of SAML, they're able to retrieve those temporary credentials that they can use to access AWS. We also have the AWS Directory Services, and this allows AWS Management Console access by allowing the user, the on-premises user, to authenticate against Active Directory using their Active Directory username and password. We also have Cognito. Amazon Cognito gives us a programmatic access to the API that allows our web and mobile applications to create user pools, right? So we create a user pool within Cognito, and using OpenID Connect, such as login with Facebook or Twitter or so on, our web and mobile application users can authenticate against that existing account, and that can be correlated and stored within a Cognito user identity pool. And from there, we can use that to grant temporary credentials that can be used to communicate with other Amazon services. So through authenticating with Cognito, we can create a system that allows our web or mobile applications to communicate with Amazon services directly. And we'll see some examples of that later on. And the last option that I want to talk about here would be the AWS single sign-on. So single sign-on gives us access to multiple AWS accounts and business applications. We've talked about earlier how it's common for organizations to leverage multiple accounts for their different environments, right? You may have an account for production, an account for development, or account for different business units. And so that's a very powerful pattern in order to create isolation between different types of resources. And AWS single sign-on allows you to essentially create one place for users to authenticate and gain access into multiple accounts, right? So keep that in mind for those of us who are a part of larger organizations, for teams that may have hundreds or even thousands of users that already exist, keep these federation options in mind. Now let's review a demo of managing an MFA device.
Okay, so once again, from the Management Console dashboard, in order to manage MFA devices for particular users, we would need to be in the IAM service. So since we've been there recently, we can find it here. And we're going to, first, let's take a look at our users. So my user, the admin user that I'm currently logged in with, already has an MFA device present. You can see that I have a virtual MFA device, but the Amy Fowler user does not. And so very much like access keys, I could create one for her. Now, so I could go here to her user, go to the security credentials tab, and it says here an MFA device is not assigned. Now, if we worked in the same office where I could say, hey, Amy, come over here to my desk, then I could say, go through this process and create a QR code that she could then scan with her virtual MFA application, be it Authy or Google Authenticator or whatever. If Amy is remote and I'm remote and we're not in the same office, then of course that's not possible. I would have to, if I created the device for her, then I would have to somehow transfer specific information about that MFA device to her. And I don't really like doing that. Now, you may have a way, a transfer method that you trust to be secure, and that's fine. But again, for users managing things like this, access keys and MFA devices, I prefer to empower them to do it themselves. So just like I want users to manage their own password, I want them to manage their own access keys. I generally want them to manage their own MFA device as well. And so I'm not going to do it for her. I'm going to make sure that she has the ability to do that. So this is true for every user, right? Not just developers, but everyone. So I want to take a look at the everyone group. So if we were to take a look here at the everyone group, and we look at the permissions. Just like a user needs permission to change their password, they need permission to manage their access keys, they also need permissions to manage their MFA device. So I've taken the liberty to create and attach this new policy here called user self-managed MFA device. Right, so let's take a look at that policy and see what kind of permissions that is granting. So you can see here that we are allowing several different actions that all relate to the management of MFA devices. And some of these require the user type, some of them require the MFA type. So within the IAM service, there are different types of resources: users, groups, roles, policies, and of course MFA devices. And so if we did not include the MFA type resource, then several of these actions, like create virtual MFA device, would give us an error. It would tell us we don't have that permission, because some actions require specific types of resources to be defined. So now that we've given our everyone group the ability to manage their MFA device, we can also, what we want to do is enforce MFA. Now this is up to you. You don't have to do this, but it's just something that you can do to add an extra layer of security. Okay, so let's take a look at another policy that I created called force MFA. So actually, if we search for MFA, you'll see the two different policies here, the self-managed and then another one called force MFA. Right, so I'm going to take a look at force MFA and let's just take a look at this policy down here. You'll see that we are using a deny, an explicit deny. And remember that deny rules will take precedence over allow rules. Right, so if you have two conflicting statements, the deny will win. Now, what I really want to draw your attention to here is the not action. Right? So all of the other policies that we've created and made use of have leveraged the action key, where we here are using the not action key. So what this essentially means is we are denying all actions other than IAM actions, under the condition that the multi-factor auth age header in the request, or the parameter in the request, is null. So essentially what this means is that under the condition that multi-factor authentication was not used, deny the request for actions other than IAM actions. Right, so user information, and create an MFA device and enable and activate that device. And then otherwise, if they try to do something with EC2 or Lambda or S3, they could only do those actions if their multi-factor authentication was used during their login. So again, an extra layer of security. All right, and we are going to apply this. Let's go back to groups and take a look at the developers group, and you can see that I've already applied the force MFA to the developers group. Right? We don't want to force MFA necessarily for everyone, but maybe only certain users. Okay, so I've done all of that under my admin user. I'm going to go ahead and sign out, and I'm going to log back in as the A Fowler user. Okay, so now that we're logged in as A Fowler, let's go. We could find the MFA management under IAM. We could go there and then find the user, or we could just go here to my security credentials. And of course, for A Fowler, we've already done a password. We've created access keys. So here we can say assign MFA device, and according to those permissions, we can only manage one for our current user. Before we do that, though, I want to point out that because we logged in without MFA, we should not be able to do anything in an EC2 or Lambda, for example. Let's just experiment here, and let's go to Lambda and it should give us an error. Yep, you are not authorized to perform Lambda get account settings, right? And if we were to try to DynamoDB, it should also give us an error, right? Let's say create table. If we just say test, test, and create, it should give us an error. There we go, not authorized, right? And that's because we did not log in with MFA, right? So let's go back to IAM, or again, we could go back to security credentials. We're going to say assign MFA device. And here you can see that we have our choice of virtual MFA device, which is some type of application on your mobile device or your computer. My favorite two are Authy, A-U-T-H-Y, and Google Authenticator. There are others, but those two I've used over the years, and they've never failed me. We could also use a U2F security key or a Gemalto hardware. So you can order Gemalto hardware key fobs from Amazon. So in this case, we're going to use a virtual MFA device. We'll say continue. And now we have a couple of options. We could either get a QR code and we could scan that into our phone, or we could show the secret key and then copy and paste that. So if you are using an MFA application on your local machine, then you could just show the secret key and then we could copy and paste that into the application. For our mobile device, we could go show QR code, and then what I would want to do is open the device on or open the application on my phone, and we would add a new account and say scan QR code, and we would hold our phone up to the screen, and very quickly it would grab that QR code and all of the information that it needs, the account name, the secret key, all of that would be included in the QR code, right? And so once we have that in our virtual device, then we need to add two different codes, right? So, and of course, these are generated about every 30 seconds. So the first one here, 849-983-931. All right, and so now that we've gotten those two MFA codes, two consecutive MFA codes, now we can say assign MFA device. Amazon will verify those codes, and then we can say close, right? So now that we have that, you can see that the A Fowler user has the assigned MFA device enabled, but she still hasn't logged in with it. We have to actually log in with it for it to enable us to do things with Lambda or DynamoDB, right? So let's log out and log back in and see the difference. So we'll go log right back in as A Fowler, and there you go. It's asking for an MFA code, and I will just enter one, and now we are authenticated. And so now that MFA is present, we should be able to go to Lambda and see everything we need to see without, there you go, you can see we have a couple of functions in here, and we did not get that same error. And that's because of the force MFA policy that we applied, right? So again, you can find those MFA information and manage MFA devices from the security credentials tab underneath the user. And so now this user is fairly secure, right? They have a strong password. They have access keys that they've downloaded directly themselves, and they've enabled their own MFA device. And MFA is enforced on a number of things that they are doing in their day-to-day operations.
Now let's review first steps and best practices in regards to the Identity and Access Management Service. First, for new accounts, if you are new to AWS, if you've just created an AWS account, then there are some critical first steps that you really need to take. The very first thing that you should do, and remember that these first steps are going to be done by logging in with that email address and password. And remember that by logging in with the email address, you're logging in with the root account, and so, or the master credentials. And so the very first thing that we want to do is enable AWS CloudTrail. We're going to talk about this service more in detail later, but for now, keep in mind that CloudTrail is the service that records all API calls, so that by enabling CloudTrail first, everything else that you do will be recorded. And this is critical for satisfying change management and compliance for those of us who need to. The second thing that we would want to do is create an admin user as an IAM user, right? You could also optionally add conditions like we talked about earlier. If you want to have an admin user but not allow them to be an admin from home or from their local cafe, but force them to, come through the office, then you can apply that condition. Then we would want to enable multi-factor authentication on the root account. That is so incredibly important that we protect the root account credentials. Again, companies have gone out of business as a result of those credentials being compromised. So adding multi-factor authentication adds that extra layer of security. Then we would want to enable the cost and usage report. We'll talk more about this later on as well, but the cost and usage report is basically a way of us getting very detailed information about our costs within AWS. Cost and usage report allows us to attribute costs down to the penny across services, regions, and even arbitrary tags. And again, we'll talk more about that later on. But the reason I list it here is because for these steps, doing these particular steps with the master credentials, remember that generally anytime we do something with billing, such as enabling the cost and usage report, updating our billing information, those kinds of things generally need to be done with the master credentials. Then we would log out. Once those things are done, we log out of the root account and then log back in as the IAM user, the admin user, and then we go on to create additional users, groups, and so on. And so in terms of best practices, first, again, for those master account credentials, the root user, that email address and password, we want to protect those at all costs, right? Take the security of those very seriously. If you find that the master credentials or that master user has access keys associated with it, you will want to delete those access keys because you will never use them. Sometimes accounts may come with those keys by default, but generally the best practice is that we don't use the access keys for the root user. And like I mentioned, we don't use the root credentials for day-to-day operations. Generally speaking, for our other users and for our groups of users, for creating policies, we want to follow the principle of least privilege, giving users the permissions that they need to do their job. Not every member of your organization needs to be a super admin, right? And so another best practice is to rotate access keys. If you do have users created within the identity and access management service, and those users have long-term access keys that they're using locally on their local machine, then they should be rotating those credentials regularly. And how often you do that is up to you. Some organizations, might prefer 30 days, every 60 days, or so on. And then lastly, for every user, it's a good idea to enable and even through policies enforce multi-factor authentication. So again, multi-factor authentication is a way of providing a one-time use password in the form of a 6-digit PIN. And so you can order a physical key fob from Amazon. Those are manufactured by a company called Gemalto. Or you can leverage a virtual MFA device on your smartphone, such as Google Authenticator or Authy. right? But either way, it's really important to make use of that, because if you have a password saved on your local machine and someone plays the football attack and they grab the machine and run off with it, by having a multi-factor authentication in place, it makes it that much more difficult for them to actually get into your account, right? So keep those first steps and best practices in mind as you move forward using your Amazon account. Networking in Amazon Web Services is perhaps one of the most important aspects to learn and become proficient at, because it fundamentally affects everything you work with, from virtual machines to databases, high availability, security, and more. To a seasoned IT professional, many things in AWS will be familiar, yet many things will also be new concepts or work in significantly different ways. So in this lesson, we will cover creating isolated networks with Amazon Virtual Private Cloud, subnets, routing, firewalls, and more. Now let's review an introduction to Amazon Virtual Private Cloud, or VPC. With Amazon VPC, we have the ability to create logically isolated networks, right? So on premises, you have your network. The internet is its own network, and those two networks by default are isolated from one another until you put something in place that allows them to communicate. And VPCs are the same way. So if I create my VPC and you create your VPC, those are two completely different networks that remain completely isolated from one another. A VPC is inherently, by default, isolated from every other network, including the internet. And so there's a security mechanism in that the only way for a VPC to communicate with any other network, another VPC, on premises, the internet, we have to explicitly put that in place and allow that kind of communication. So VPCs are created per account, per region. So keep in mind that we don't really approach Amazon VPC thinking that we're going to put everything into one VPC. We generally approach it understanding that we will probably have numerous VPCs. If we operate across multiple regions, we will have multiple VPCs. If we operate across multiple accounts, we will have multiple VPCs. So really embrace the idea of creating multiple networks and then allowing those networks to communicate with one another if they need to. When we create a VPC, it does exist and it spans a single region. So keep that in mind, that one VPC exists within the region that it's created in. It is possible to allow VPCs in different regions to communicate, but they still exist in their respective regions. Now, when you create a VPC, that VPC, again, it spans the entire region, but it can make use of all of the availability zones in that region. So if we were to create a VPC in Oregon, in the US West 2 region, for example, then we would have 3 availability zones for us to use, and that VPC can leverage all 3 of those availability zones. VPCs can also peer with other VPCs. So when you allow 2 VPCs to communicate directly, that's called peering. And you can peer between VPCs in a single region. You can peer between VPCs in multiple regions. There are a number of security mechanisms that are available to us, different firewalls that are applied at different points in the network path. And so one of the recommendations on security from AWS is to apply security to your network at key external and internal boundaries. And we will talk about some of those mechanisms as the course progresses. We also have the ability to create gateways. Gateways are a device that allows one network to communicate with another network. And so if we wanted to communicate with the internet, then we would create and attach an internet gateway. If we wanted to communicate with on-premises through a VPN, then we would create a VPN gateway. Now, keep in mind that with most Amazon services, there are limits. There are hard limits, which are due to a limitation with the technology itself, and then there are soft limits. Soft limits are really put there by AWS to help control resource consumption. In the case where perhaps a customer doesn't really know what they're doing, or perhaps a customer has some type of an automation script that runs away and starts creating more resources than it really needs. So in this example for VPCs, we have a default soft limit of 5 VPCs per region and a default limit of 200 subnets per VPC. So keep that in mind, that as we continue talking about different services, most services will have some type of a limit around them. Soft limits we can raise by submitting a ticket to AWS support and giving them a reason why we need more than 5 VPCs per region, for example. So when we create VPCs, there are a number of ways that we could go about designating VPCs for different types of environments. We could create VPCs per environment. So in this diagram, you'll notice that we have a VPC specifically for development. So here we might put development servers and development environments, specifically so our software teams or engineering teams can have something to code against and try out new features. And then we may decide to put testing resources in their own VPC and production resources in their own VPC. That way, even if everything is in the same account and in the same region, at least we have isolation at the networking level, so that if any one VPC were somehow compromised, it would be very difficult, if not impossible, to also compromise the other VPCs. And we can take this a step further. We can organize our VPCs in pretty much any way we want. When Amazon creates services in different types of resources, they generally do so in a way that's generic enough to be flexible for just about any use case. So there's nothing within AWS that says we have to organize our VPCs in any particular way. They are totally flexible, and we can do it however we want. And so another common pattern might be that we divide VPCs per function. And so here we might put shared services in one VPC and various applications in their own VPCs. And then we could allow these VPCs to peer with one another so that our applications can communicate with these shared services. So application 2 may very well talk to shared services, and application 1 talks to shared services, but the applications may not necessarily talk to one another directly. We could divide VPCs up between different departments, right? We could put finance, all of finance applications in their VPC. Engineering and other business units would get their own VPC as well. So these are just some examples of how we might go about it. The idea here is that when you approach designing networks with AWS, you take a look at the different environments that you have, the different departments of your organization, the security needs of your organization, and you determine what makes the most sense for your application in your business. And so when we think about running applications on EC2, the architecture for those applications generally begins with the network. It begins with Amazon VPC, because in order for us to really achieve security, high availability, fault tolerance, durability, for us to achieve those kinds of things, we have to design a network that allows us to make use of different Amazon features like multiple availability zones and different security protocols or security mechanisms. And so here we have a region with 2 availability zones. And first, we would create a VPC, and of course you can see that that VPC exists within that one region, and it spans or makes use of multiple availability zones. And so the next thing that we need to do is to divide that VPC into subnets. Subnets are, as the name suggests, a subdivision of a network. And so it's a way of isolating different parts of our network to create perhaps functional placement of different devices for different purposes, and to create isolation for security. And so subnets within Amazon VPC perform two primary, very important functions. One is to create isolation between tiers. So if you're designing a multi-tier system, then every subnet would, perhaps every tier, would get its own subnet so that you can have that isolation between tiers. And so here, we might have a subnet that can be routed to the internet, and we might have a second subnet in a second availability zone, also routed to the internet. And so the other thing that a subnet does is to map, give us a physical mapping to an availability zone. When we create subnets, they are created specifically one-to-one with an availability zone. And so we have isolation between tiers and a mapping to an availability zone. And so now, because we have, in this example, a mapping between two availability zones, by launching EC2 instances into those subnets, we become resilient not only to the loss of a device, but also to the loss of a data center. If we lose an availability zone, we still have another one, or two if we've designed it that way. And so again, here we may also add additional subnets. Now these two subnets, here you'll see the lock icon, and when we notice the lock icon, that generally signifies that these subnets are private, right? So we may have some subnets that have access to the internet, other subnets that do not have access to the internet. That way we can put publicly available devices in our public subnets, and private devices or private application servers or private databases in private subnets, right? So isolation between tiers and mapping to a physical availability zone are what subnets are all about, right? So that's our introduction to Amazon VPC, and we will continue to talk about a number of different mechanisms and techniques and principles as this lesson continues. Now let's take a look at a demo of creating a VPC and subnets.
Okay, from the Management Console dashboard, we can find VPC down below underneath Networking and Content Delivery. So here's VPC. We'll go there, and here in the Ohio region, you can see that we currently have, according to our summary, we currently have 2 VPCs and 9 subnets. So let's take a look at the current VPCs that we have. We have one called Microservices Network. This is something that I created some time ago for a particular use case. And we also have this one here, which is currently unnamed. And this one, the 172.3.1 VPC, if we scroll all the way over, you can see that that one is the default VPC. So many accounts in many regions may include a default VPC. And the default VPC is there to give you quick and easy access to an internet-enabled VPC. I generally ignore those. I don't typically use them unless I want to run a quick experiment with something that's publicly available. But for running my production workloads, I generally like to create my own VPC with my own CIDR ranges and my own security mechanisms and my own route tables. So let's go ahead and create a new VPC. And let's just say that we have a use case where we might launch a number of different web applications. Some of them may be a collection of microservices, and we may have a few old monoliths that we are migrating as well. But all of these are essentially web applications, and we can put them all into the same VPC. We don't necessarily need a VPC per application, right? So let's just call this one web apps. We might have other applications that are not meant for, access from the internet. Other applications that are doing more background processing, and we might put those in another VPC. It's all up to us. So now that we've named it, we need to choose a CIDR block. And so a CIDR block is just a way of specifying a range of IP addresses, some number of IP addresses. It could be a few hundred. It could be, 65,000 addresses, right? And we generally choose a range from a private range, such as 192.168. We could choose 171. We could choose 10 dot, right? So typically ranges that are considered to be private. So let's just keep it simple and go with 10.000/16. Now, we may not need 65,000 addresses, so I always encourage folks to really give a lot of forethought to this range, because if you use too large of a range, then you could end up preventing yourself from using some of that range somewhere else for another purpose. So always consider the fact that you may have multiple VPCs in one region for different uses. You may have VPCs across different regions. And you also have a network on premises, potentially, that you want to create a VPN connection. And so when you want to connect two different networks, this range of IP addresses cannot overlap. All right, so do give a lot of forethought to this particular range. Now, we could choose IP version 6 if we needed to. In this case, we don't necessarily. And then, of course, the tenancy, we'll save that. We'll talk about that later in another more advanced class. It's not really all that important for now. Let's go ahead and create that. And just like that, it's pretty easy. I mean, all we did was name it and give it a range of IP addresses. And so now we have our web apps VPC. So from here, we can't really do anything with it yet, because in order to really use a VPC, we have to have at least one subnet. In order to launch an EC2 instance or an RDS instance or Elasticache, Redshift, Elasticsearch, anything that uses instances, then we need a place for them to live in the network. And we choose subnets. And so let's go over here to subnets. And you can see that we have a number of subnets in use across already. But let's just clear all of that out and filter by VPC. Let's see here. Let's go to VPC and filter. It's not going to let us filter by. All right, so we'll go over here to subnets. And you can see that we have a number of subnets related to existing VPCs, but we haven't created any for our web apps VPC. So let's go ahead and create a subnet. And let's say that in our web apps VPC, we will have two tiers. We might have a public tier for load balancers. We might have a private tier for applications. And so let's go ahead and create the public tier first. And we could call that one load balancing. And I'm going to call this one load balancing A. Because remember that subnets are specific to an availability zone. And the idea behind this naming scheme, and of course you are free to adopt whatever naming scheme works for you, but what generally works well for me is to, one, name it according to the functional use. In this case, I'm going to create a subnet for use specifically by load balancers. It's not for application servers. It's not for database servers. It's not for caches or proxies or anything else. It's specifically for load balancers so that I can tailor the firewalls for the ports needed by the load balancer. And then the A here will represent the availability zone that it will be assigned to. In this particular case, I'm going to use US East 2A, right? So we have load balancing A in the availability zone A, all right? I'm going to also choose the web apps VPC, and then we also need, just like the VPC has a CIDR block, the subnet needs a CIDR block as well. Now, the CIDR block for the subnet needs to be, as the name suggests, a sub-range of the VPC. And it could, technically, we could do this, /16, we could create one subnet that is as large as the VPC, right? We could use all of the available IP addresses in that one subnet, and maybe there's a use case for that we could talk about at another time. But for now, what that would mean is that we could no longer create any more subnets, right? So typically, we want to, if what we want is high availability and fault tolerance, we want to leverage multiple availability zones, then we need to create subnets in multiple availability zones, right? So here, I'm going to choose a common, this is a pretty common pattern, a /24. Mathematically speaking, a /24 would give us 256 possibilities. But in reality, after Amazon reserves some of those IP addresses, then we will only get about 251 usable IP addresses. All right, so let's go ahead and create that subnet. And there we go. We can close that, and now let's come up here and let's see here. Let's filter by web, or let's filter by VPC. Is it this one here? Yeah, there we go. All right, so we can filter subnets by the particular VPC. And we should be able to do it over here. This one's not, it should show up here as well. Let me refresh this particular page real quick and see if our VPC shows up. There it is. Now that's what we want. So if you could also filter everything, right? So by filtering based on the VPC here, then we no longer need this particular filter here, right? So now everywhere we go in here, we will only see that one VPC, right? If we go to route tables, internet gateways, and all of these other things, they will all be related to this one VPC. So that's an easy way of drilling down into specific resources, right? So let's go back to subnets. And so now we have that one. And let's go ahead and create a private subnet. We'll call this one applications A. And again, the idea behind this is that we intend this subnet to be used by applications, and this subnet will be in the A availability zone. We could choose another one. So let's go ahead and choose A. We'll choose another CIDR block. Now, we've already chosen 000/24, so we can't choose that one again, right? We need to choose another one that does not overlap. So if we wanted these two subnets to be what we would call contiguous, meaning that one picks up where the other one left off, then we would go with 10.0.1.0. The next one would be 10.0.2.0, right? So we'll go ahead and create that one, close that, and just like that, pretty straightforward, pretty simple. We've created a VPC for our applications. We've created two different subnets, one for load balancing, one for private application tiers, and we will pick up with this and continue to add to this as we move through other demos in the course.
Now let's talk about routing within Amazon VPC. Routing is concerned with the flow of traffic, whether or not any and all traffic is allowed to move between two different ranges of IP addresses. Routing is not at all concerned with protocols and ports. Routing is not concerned with TCP versus UDP, port 22 versus port 443. It's only concerned about whether or not any and all traffic can move, right? And so once we have routing in place, then we can start to filter the traffic based on protocol and port and so on. And so looking at this diagram, we can understand routing by talking about how do we get traffic from one place to another. And within AWS, every VPC has an implicit router. It already exists and it's already fully managed by AWS. We don't need to create or manage the router, but we can configure routing by creating route tables. So you'll notice here that we have a couple of different route tables, right? So here's a route table and here's a route table. And we configure the router by adding routes to those route tables. You'll see that both route tables have the default route. So this local route says that for traffic that is destined for, you'll notice this range here, 10.2.00.16, for traffic that is destined for that range, it remains inside the VPC. So you'll notice that this default range here, 10.2.00.16, matches the range here of the VPC itself. So all route tables that we create will ensure that traffic destined for the VPC remains local. And what that means is that every subnet in that VPC is inherently allowed to route traffic to other subnets, right? So all of these subnets are inherently allowed to communicate with one another based on that local route. And without any other routes in place, that's the only communication that would be allowed. And so if we wanted to communicate with the internet, then first we would need an internet gateway. Again, a gateway is a device that allows two networks to communicate with one another. And so by creating and attaching this internet gateway, and then by creating a route, you'll notice here that we have a route. We're saying with all zeros, we are essentially saying for every other range of IPs aside from 10.2.00.16, we want to route those packets to the internet gateway. And so if we then associate this route table with this subnet, that would then allow devices in that subnet to communicate to the internet by going through the internet gateway. And then the same thing applies to a VPN connection. Over here, if we wanted to create a VPN between our VPC and on-premises, then we would need a VPN gateway. And we would also need a route. You'll notice here what we're saying is that for any network traffic that is destined for 192.168.00/16, essentially our corporate range, then we want to route that traffic from our, say, databases or what have you, through the VPN gateway and back to on-premises. And so again, routing is concerned with whether or not traffic can flow. And I always liken routing to the plumbing at your kitchen sink, right? It's the plumbing at your sink that allows water to be delivered to your sink. And it's only once that plumbing is there that you can then filter the water. And the same thing applies here. It's once routing is in place and traffic can flow, then we start worrying about filtering that traffic based on ports and protocols. So routing is the first place that we start, and then we can start applying firewalls and different security mechanisms that we will talk about later. Now let's talk about public, private, and hybrid subnets within Amazon VPC. So earlier we talked about routing and how routing allows the flow of traffic between different ranges of IP addresses. And so within Amazon VPC, earlier we talked about using an internet gateway and a route to the internet gateway to allow communication from a device in a subnet through the internet gateway and to the internet. And so by doing that, by creating that route, we then essentially create a subnet here. This particular subnet would then be considered public because the devices in that network have both direct access to and from the internet. Any device within this particular subnet, so long as it has a public IP address, it would be reachable from the internet. And so we could then again call this subnet public. And so generally when we're talking with other folks working with AWS, if we talk with Amazon solution architects and we describe to them that we have a public subnet, you are essentially implying that that subnet has a route to the internet through an internet gateway. we also, in many cases, have application servers. Like here, for example, we have this EC2 instance that has an application running on it, and perhaps for some reason that instance needs to reach the internet in order to perhaps download code from GitHub or make calls to a logging service like Loggly or call to some third-party configuration management service. Whatever the case may be, it's very often that we have application servers that need to reach out to the internet and get their responses back, but at the same time, we want them to remain private. We don't want someone on the internet reaching in. We kind of want one-way internet access. And in order to do that, we can use network address translation. And you'll notice here that we have a second route table, and this route table being associated with this particular subnet, we have a route that says for every other IP address aside from 10.2.0.0.16, we want to route those through the network address translation gateway, or the NAT gateway. And so what that would do is, so if this instance were communicating with the database, then the traffic would simply talk to the database because of the local route. But if this instance needed to call out to the internet in order to, like I mentioned, to download code from GitHub or what have you, the request would first go through the NAT gateway. And the NAT gateway would then translate. The reason we call it network address translation is because it would translate the private IP of this instance into a public IP that would allow the NAT gateway to talk to the internet. And then when those responses come back from the internet, the NAT gateway then forwards those responses back to the instance. So that way, the instance has the ability to reach out to the internet, get its responses, but it also remains protected from host potentially malicious activity on the internet trying to get in. There's no way, in this particular diagram, there's no way for someone on the internet to actually get into the instance directly. So these two networks would be, we would have this subnet again would be public, and then using these mechanisms that we just talked about, the NAT gateway and the routing table, this particular subnet we could call hybrid. It has some limited access to the internet while also remaining private, right? So again, if you were talking with an Amazon Solutions architect and you described having a hybrid subnet, you would be implying that that subnet communicates to the internet through network address translation. And then, of course, back here we have our database in a private subnet. It is truly private. According to this diagram, this particular subnet over here can only communicate with other subnets in the VPC. There's no way, according to this diagram, there is no way for this particular subnet to communicate to the internet, not through the gateway directly, not through network address translation. It is truly private. And so for databases and for perhaps sensitive information, that's exactly what we want. We don't want any way for these particular servers to be compromised, right? And so when we think about running networks within Amazon VPC, we need to keep in mind that there are ways for us to reach the internet directly. There are ways to reach the internet in a protected kind of way through network address translation. And then, of course, we also have the ability to keep certain subnets and certain parts of our network completely private. Now let's take a look at a demo of configuring routing to the internet within Amazon VPC.
Now from the VPC dashboard, again, we're back in the Ohio region. We have the 3 VPCs that we saw earlier. If we go back here and take a look at these VPCs, we're going to enable routing to the internet for this web apps VPC. So let's go ahead and filter over here by that VPC, and we'll come down here to route tables. and you'll see that we have one route table, which is considered what we call the main route table, and it is not explicitly associated with any subnets, but it is being used. If we look at the routes, you'll see that we have a route called 10.0.0/16. That's where the destination is, and the target is local. So what this means is that if any EC2 instance tries to send network packets to any other IP address in this range, then the local router of the VPC will keep those within the VPC, right? It will keep it local to the VPC. So we're going to come back and revisit that routing here in just a minute. Now, in order for our VPC to communicate with the internet, we first need an internet gateway. And it says we don't have any yet, so let's go ahead and create one. We'll call this one Web Apps Internet Access. All right, so now that it was created, you'll notice it was created, but it's still not showing up in the list, and that's because we're filtering by our VPC, but the internet gateway is not associated with that VPC. So if we clear this filter, then now you can see here's that internet gateway, and it is currently detached. And so not only do we have to create it, we also have to associate it or attach it to a VPC. All right, so let's go ahead and attach it to our Web Apps VPC. And we'll go ahead and click Attach. And now if we go back and turn this filter back on, we can still see it, because now this internet gateway is intrinsically associated with our Web Apps VPC. So now that we have an internet gateway, now we can enable routing. So let's go back to route tables. Now again, we do have an existing one. This is the default route table. We did not create this. It was created for us when we created the VPC. So my approach is to leave the main route table as it is. So if we go back to these routes, you'll see that these routes keep traffic local. They don't enable routes to the internet. And so I like to create a new route table specifically for this kind of routing. I'm going to go ahead and click Create Route Table. We'll call this one Public Traffic. Again, this will belong to the Web Apps VPC. Go ahead and create that. And now, just like that, that route table was created. And if we go back up here in the list, you can see we could change the name if we wanted to, just like by clicking on that little pencil. We could then come down here and add our routes, right? So again, all route tables will include the local route. You cannot remove it and you cannot overwrite it. All route tables include that local route. So let's go ahead and click on Edit Routes, and we will add a route. And here what we're going to say is that for any traffic that is destined for this particular range, we of course want it to remain local. Any other IP address should be routed to the internet gateway. So we're assuming that if you aren't talking to another EC2 instance in that VPC, then you must be talking to the internet. So we're going to say all zeros. And in essence, what this accomplishes is that all other IP addresses will be routed to the internet gateway. And here we're going to choose the internet gateway that we just created. And we'll go ahead and save those routes. We'll close that, and now you can see that we have again, that local route, and then here all other IP addresses. The all zeros is, in essence, that's what it means. And it's being routed to the internet through the internet gateway. All right, so that's we've done a lot, but we still haven't done enough. There's still one more key thing that we need to do. We need to associate this route table with a subnet. All right, so if we go back up here, it says this is not associated yet. So let's edit those. And we're going to, if we remember what we did earlier when we created the two subnets. We had our load balancing, which we said was meant to be public, and where we would put load balancers, publicly accessible load balancers, and then our applications would remain private. All right, so we don't want our application servers, at least in this example, we don't want them directly accessible from the internet. We only want our load balancers directly accessible from the internet. So I'm going to associate this route table with the load balancing A subnet. And then I'll save that. And now you can see we have that subnet association. And we can verify that by if we go to subnets, and if we click on load balancing A, if we scroll down here and look at the route table, you can see that now the subnet itself is aware that it has a route to the internet gateway, right? And so that's all there is to it. In order to, that took us, about 5 minutes or so to create an internet gateway and create a route in a new route table and associate that route table with our subnets, right? So that's how we can configure routing to the internet.
Now let's talk about network access control lists, or NACLs. Within Amazon VPC, again, one of the recommendations from AWS is to apply firewalls or security at key internal and external boundaries of our network. And so the VPC itself would be an external boundary, and then subnets within the VPC would provide key internal boundaries. And then, of course, the instances or devices would also be a boundary. And so we'll talk about security groups for those later on. But for now, in terms of a firewall for subnets, we have network access control lists. And so here in this diagram, we are looking at, we have two different subnets. You'll notice that we have a public subnet here and a private subnet over here. The public subnet is intended to allow our load balancer to communicate directly with the internet and to allow, more specifically, to allow hosts on the internet to reach in and initiate new connections to our load balancer. Our private subnet is intended to keep our private application servers private, but you'll notice that they can communicate with the load balancer, but they don't communicate to the internet directly. And so we want to provide a firewall for our public subnet, for the subnet as a whole, no matter what devices might be in use, no matter what security groups are in use within that subnet. We want to protect the subnet as a whole. And so we can do that by applying a network access control list. So we create the network access control list, and then we associate it with that particular subnet. And so if we take a look at a table of rules, we can see exactly how we might secure this particular subnet for this particular use case. So here, I'll draw your attention to the first couple of rules. You'll see here rule number 100 and rule number 110. We are allowing, you'll notice here that we are allowing ports 80 and 443 to come in to this subnet from anywhere. You'll see here that the source is all zeros. That means any IP address whatsoever. And so by doing that, we allow our end users out there on the internet to initiate new connections coming in on port 80 and 443. And then anything else, if someone tries to be malicious and come into that subnet on port 22, those requests would be denied, or those packets would be rejected by the firewall, by the network access control list, acting as the firewall for the subnet. And so the subnet, in this regard, can create a sort of guardrails around your instances. So if someone were to inadvertently open port 22 on an instance inside that subnet, it would still gain some protection by the fact that port 22 is blocked by the network access control list. And so the next set of rules here says that we're going to allow, let's take a look at the egress rules. And what we're saying here is that for traffic that is leaving this subnet, right? So we have to consider not only traffic that is coming in, but also traffic that is going out, right? So egress rules affect traffic that's going out. And so this particular rule says that we want to allow, you'll notice here that we are allowing port 1024 through 65535. If you read the AWS documentation, it describes that the load balancers, elastic load balancers, use ports 1024 through 65535 as the ephemeral port range. And so for those of us who might not be familiar with how networking works in this way, when the load balancer receives traffic on 80 or 443, it will send the response back on a different port. And that port is generally chosen at random from a particular range. In the case of elastic load balancers, that range is 1024 through 65535. It's a very large range relative to other uses of ephemeral ports. And so by setting this rule here and setting these rules up here, port 80 and 443, we allow the load balancer to receive on the appropriate ports, and we allow it to send responses back on the appropriate ports. So it's one thing, for network access control lists, it's necessary to specify both inbound and outbound traffic. Without this rule here at the bottom, we would receive requests, but our end users would never receive their responses, right? So we have to have both the ingress and the egress rules in place. And so you'll see here that by specifying 1024 through 65535, which are essentially non-privileged ports, we could allow those ephemeral responses to go out, but also block privileged ports. Any port less than 1024 is considered privileged. So ports 22, ports 21, and so on, those ports would not be able to go out. So part of security in networking says that just as important as preventing malicious activity from getting in, if it does get in, it's also important to prevent them from getting out, right? So imagine breaking into a museum. They didn't want you to be in there to begin with, but now that a robber is in the museum, they want to lock the doors and prevent them from getting out with the valuable art, right? So the same thing applies to networking. And so by creating egress rules like this, we can ideally prevent those malicious activity from getting out if it were to get in. The last rule here that I want to point to is generally one common practice, at least the practice that I follow, says that I prefer back-end services to listen on a non-privileged port so that I don't have to run applications with a privileged user. If I can run applications with a non-privileged user and have them listen on a non-privileged port, that generally adds to the security of the application, right? So in this particular case, if we have our back-end application listening on a non-privileged port, such as port 8080, then we also need to allow our back-end to send responses to the load balancer on ephemeral ports as well. And so that's what this rule here would be for. So the back-end would send a response on an ephemeral port, and we would need this particular rule, right? So you'll see here that the load balancer is able to send requests to the backend on port 8080, which is satisfied by this egress rule here. And the backend instances are able to send their responses back to the load balancer on some ephemeral port, which is satisfied by this rule here, okay? And so to summarize NACLs, we could say that NACLs, again, are a firewall for the subnet as a whole. They are stateless. A firewall does not recognize responses as being responses. Stateless means that it just sees a network packet either coming in or going out, and it doesn't correlate responses with requests. And so that's the reason why we have to specify both ingress and egress. And rules are applied in order. You'll notice that in those tables, we had rules specified at Rule 100, Rule 110, and so on. And rules are matched in the order that they're specified in that table. And like I mentioned, we have to specify both ingress and egress traffic for NACLs. Now, you can specify allow rules, you can specify deny rules. And this behavior is slightly different with security groups, and we'll discuss that in an upcoming lesson. It is worth noting that the default NACL, when you create a VPC, several other things are also created for you. So when you create a VPC, there's also a default NACL, a default security group, and a default route table that are all created for you. The default NACL that comes with every VPC allows all ingress and egress traffic. And of course you can change that, but just keep that in mind that the default behavior for the default NACL is to allow all traffic inbound and outbound. So again, keep in mind that NACLs are firewalls for the subnet as a whole. Okay, so now let's take a look at a demo of creating and applying a network access control list.
Here in the VPC console, we're taking a look at the subnets that we created earlier. And these are the two subnets that belong to our web applications VPC. And earlier, we enabled routing to the internet for our load balancing subnet. And again, if we take a look at that route table, we'll see here that this is the subnet that is routed to the internet. And so we're going to build on that by creating and applying a network access control list as a firewall for the subnet. So let's go down below here under security, and we'll take a look at network access control lists. And you'll see that we do have one, and it is currently associated with two subnets, and this one is the default network access control list, or NACL. And if we look at the inbound rules, you can see that it allows all traffic from everywhere, right? So we're allowing all traffic on all protocols on all ports from everywhere. And if we look at the outbound rules, we will see the same thing. All traffic is allowed on all protocols, all ports from going to anywhere within our VPC. So we want to tighten the security around that, and we're going to create a NACL specifically for the load balancing subnet. Now there are different ways that you could go about it. If you have network engineers on your team and they have a particular way of doing things, that's fine. What I'm showing you is the typical way that I go about applying security at the network level. So we're going to create a new one. And here, I'm going to call this one public traffic. Actually, let's call it load balancing public traffic. Because we might end up creating other public subnets for other purposes. We may create another public subnet specifically for bastion hosts, and then that would get its own NACL to tailor the firewalls for those ports. And you may have another public subnet specifically for proxies or some other purpose. But here, my approach, and it's not the approach that you have to use, but my approach is to create a subnet for a functional purpose. And in this particular purpose is load balancing. And then, of course, we will choose the VPC, and that one will go web apps. We'll go ahead and create that network ACL. And here you can see that it is currently not associated with any subnets, but we will do that here momentarily. Let's first take a look at the rules. You'll notice here that the only rules we have so far is the deny rule. So creating a new NACL is completely closed by default, both inbound and outbound. It's only the default NACL that allows all inbound and all outbound. So the default NACL you could think of as being insecure by default. And Amazon does that because they realize that a lot of users of VPC are perhaps not at a level where they understand enough to go and make modifications to the NACL, where they can more easily make those modifications at the security group. But Amazon does recommend that we make use of NACLs and security groups. And so it just takes a little more education. So for our load balancing, inbound rules are really easy. If we think about what our load balancer is doing, what ports really need to be open inbound from the internet? So if we remember what we talked about earlier, then for our load balancer receiving traffic from the internet, we really only receiving on port 80 and 443. Our load balancer, unless you're doing something, with some other kind of proxy or whatever, the load for web applications, the load balancer really has no business. It has no real need to listen on any other port, right? If you're doing traditional, web applications where your client is expecting to be able to connect on port 80 and 443, then that's what our load balancer will listen on. It doesn't need to listen on port 22, so we don't need port 22 to be open. It's not going to listen on port 3306, so we don't need that port to be open, right? And so we're going to say, let's start with rule 100, and rules are evaluated in order, starting from the lowest rule. So you can always override a previous rule by creating a new rule at a higher level. So we're going to say we're going to listen on HTTP, and we can scroll down here, HTTP from everywhere. We want to be open to the entire internet if we are offering some type of a web application available to the public at large. And then we could add rule 110, and the reason that I go to 110 is so that I have room to place other sort of custom rules between rule 100 and 110 in order to make, if I need to make any kind of modifications to block certain traffic. And so there, we're going to go down here and choose HTTPS. Again, coming from anywhere. So we're allowing port 80 and 443 to come inbound from anywhere on the internet. We'll go ahead and save that. And so now you can see, if we follow these rules, the first rule says that we allow port 80 from anywhere, TCP, not UDP, not ICMP, but TCP port 80, TCP port 443, and then the fallback rule here, this asterisk, if you were to look under the hood, then the number for that would be 32768, right? So that's as high as they go. And so that just means if it didn't match one of these two rules, then everything else is denied, right? So that means port 22, port 3306, port 3389, 5432, port 21, all of these things will be automatically denied. So we've already closed the surface attack area. And then, of course, now we need to open outbound rules. With NACLs, if we don't have any, because NACLs are stateless, they don't recognize responses as being responses, then we have to explicitly open outbound rules. So we'll go ahead and edit the outbound rules. And if you remember what we talked about earlier in a previous discussion, the load balancer will receive a request on, say, port 80 or 443, and then it will send a response back on what we call an ephemeral port. And if you read the documentation on load balancers, elastic load balancers, the documentation will tell you that the ephemeral range for the load balancer is 1024 through 65535. Now, for anyone who may have a background in networking and understand a bit more about ephemeral ports, then you will know that there are different ranges for different, there are different standard ranges depending on what operating system that you're using, right? Windows may have a particular range, Ubuntu might have a particular range, but none of that applies here. The load balancer itself has its own range, and it will send those responses out on any one of these ports, 1024 through 65535. And I suspect that Amazon opens such a wide range of ports mainly to give the load balancer the ability to open a larger number of simultaneous connections. And so we are allowing outbound TCP traffic on any of these ephemeral ports to anywhere on the internet. And we'll go ahead and save that. And so this destination here, all zeros, means all IP addresses, including the 10.000, which is the range of our VPC. So this rule actually satisfies two things. It satisfies the need for the load balancer to send responses back to our end user, and it also satisfies the need for our load balancer to initiate connections to our backend instances. And so if you remember what we talked about earlier, a common pattern is to have your backend instance listen on a non-privileged port, which is anything above 1023, right? So anything below 1024 would be considered a privileged port that would require root level access to open, right? So a common pattern is to have applications listen on, say, port 8080 or port 3000 or whatever. And so by doing that, this one rule satisfies both of those needs. And so now we've opened just the ports that need to be opened on the load balancing subnet. So we'll go to subnet associations. This is the last very important critical step in enabling the protection of this NACL. Right now, that particular subnet has no protection. So let's go ahead and do that, and we're going to choose this one here, the load balancing subnet. We'll go ahead and choose that. And there you go. And so now, if we could go back and verify that from the subnet's perspective. If we go back to our subnets and we click on load balancing A and then take a look at the network access control list, we can see that the subnet does recognize that network ACL and that we're allowing port 80 and 443 inbound from anywhere. We're allowing ports 1024 through 655 from anywhere, outbound, right? So we can send responses and we can make connections. But we forgot one thing, right? For those of us who might be familiar with networking, you probably recognize that we're missing one here in our inbound rules. So if you remember what we talked about earlier, if our load balancer is sending initiating connections to our backend instance on, say, port 8080, our backend instance will return a response on an ephemeral port, right? And so what that means is that our load balancing network ACL needs to allow those ephemeral ports inbound as well, but only from the VPC, not from the internet, but only from within the VPC. Let's go back to that network ACL and click on inbound rules, right? So again, just to clarify that, make sure that we understand what's happening here. Because of this outbound rule, the load balancer can initiate a new connection to our backend instances on, say, port 8080 or port 3000, whatever non-privileged port your applications happen to be running on. And again, our backend instance will send a response back to the load balancer on an ephemeral port. And so we need to open those, right? So let's go ahead and edit the inbound rules one more time. We're going to add rule number 120, TCP, ports 1024 through 65535. Now, in this particular case, your application on that particular operating system would determine the range of ephemeral ports. So that range could be much smaller than this. If you're using, depending on whether you're using Ubuntu or Debian or Windows or whatever, there could be a different range. And so it could be a range like 32768 through 60,000, right? I would point you to the documentation for that particular operating system. But as a general rule of thumb, we could assume that 1024 through 65535 are valid ephemeral ports, right? And so here, we don't want these to be open from the internet. We only expect this to receive inbound from our VPC, because the only ephemeral ports that we should be receiving are coming from our backend instances, which are inside our VPC. And so we will put 10.000/16. So what we're saying is these ephemeral ports are allowed to come inbound into the subnet only if they originated from within the VPC. So if somebody out there on the internet tries to get in on one of these ephemeral ports, those packets will be rejected. All right, so we'll go ahead and save that. All right, so again, let's go back to the subnet and take a look at our load balancing subnet. Go to our network ACL, and here we go. You can see that we have 80 and 443 from the internet, ephemeral ports coming in from the VPC, meaning our backend instances, and down here we have ephemeral ports going outbound to anywhere, which it means the internet and our VPC. All zeros mean every IP address, including our VPC. All right, so that's how we can create and apply a network access control list as a firewall for a subnet.
Now let's talk about security groups within Amazon VPC. Security groups are firewalls that are applied to individual instances or other devices, like load balancers. So we've already talked about network access control lists that are firewalls for the subnets, but now let's take a look at how we might use security groups to further secure our individual devices. So here, again, we have a public subnet and a private subnet. And we've already secured these at the subnet level with network access control list, but now we want to secure the individual devices within those subnets. And so the first thing that we might do is create a security group specifically for the load balancer. And we do that because the load balancer is its own functional tier. It has its own functional purpose that requires a certain set of ports to be open. We would also apply a security group to the application servers. And again, the application servers are their own functional tier. They have their own functional needs, their own ports. And so here, if we take a look at the rules for our load balancer security group, you can see that again, we're going to open, just like we did on the NACL, we're going to open ports 80 and 443. And that would allow those ports to actually come into the actual instance. And then if we take a look at the egress rules, we will see that egress rules function a little bit differently for security groups. You'll remember that when we talked about network access control lists were stateless. They did not recognize responses as being responses. And so we had to open ports for every port that needed to go out. But security groups are the opposite. Security groups are stateful. They do recognize responses as being responses. So you'll notice here in our egress rules, we are not specifying the ephemeral port range because we don't need to. If something comes in on port 80 and then a response goes out in response, the security group will recognize that as being a response, which means that we don't need to open the ephemeral port range. But here, I want to draw your attention to the fact that egress rules apply to initiating new connections. So when we think about the relationship between the load balancer and our private application servers, our load balancer only needs to initiate new connections to one thing. That would be our private application servers. The load balancer has no need whatsoever to establish a new connection to any other host on any other port. So with this particular rule, what we're doing, there's several things happening here. One, we're saying that you are allowed to initiate a new connection on port 8080 so long as the destination instance is a member of this particular security group. We're not necessarily concerned with IP addresses because we could have different load balancers in the public subnet. We could have different application servers in the private subnet. And so what we're saying here is that this particular load balancer is only allowed to talk to this particular application or group of application servers. And we can enforce that kind of tight coupling at a networking layer. We can enforce that kind of tight association with security group references, right? You'll notice that instead of using an IP address, we are using the security group ID. So security group references provide a way to tighten security based on functional tiers. So we could have multiple load balancers share the public subnet. We could have multiple applications share the private subnet, but using security group references allows us to tighten security based on a per application basis. We don't necessarily need a different subnet for every single application that we launch. The other great thing about security group references like this is that they could potentially replace thousands of security or firewall rules that you would have on premises with a single rule using a reference in security groups within Amazon VPC. So if we were to now take a look at the security group for the private application server, we will see here that we are allowing inbound port 8080 so long as it originated from a member of the load balancer security group. So again, by doing this, we have these sort of complementary converse security groups that are pointing to one another. One says I can only send outbound to you, and the other says I can only receive inbound from you, right? And so now we have a very tightly controlled security that the application server can only receive port 8080 from one specific group of machines. And then we could take this a step further. We could also apply this to our database. And we could say, again, using security group references, that our private application server is only allowed to initiate new connections on port 3306 so long as they are destined for a member of a particular database security group. So to summarize security groups, we could say that security groups are applied to devices such as instances or load balancers or network interfaces. And security groups are stateful, which means that they do recognize responses as being responses to a request that was allowed to come in to begin with. And so what that means is that we can specify ingress or egress. We don't have to specify both, right? Now let's keep in mind that for the default security group, remember earlier that I mentioned that when you create a VPC, several things are also created at the same time, such as a default security group. With a default security group, all ingress traffic is denied, but all egress traffic is allowed. So again, the takeaway from this lesson is that security groups are firewalls applied to individual devices, such as instances or load balancers. Now let's take a look at another demo of creating a security group within Amazon VPC.
Okay, so back in the VPC dashboard, again, we have our Web Apps VPC, and we've already done routing to the internet. We've done network access control lists for our public subnet. And so if we go back to our subnets, again, like we've talked about earlier, the idea behind this VPC in this subnet is that we will place load balancers in the load balancing subnets and applications or private application servers in the applications subnets. And so we also, each device gets its own security group. Just like each subnet, or each functional tier gets a network access control list for that subnet. Each functional tier gets a security group for the devices in that tier. And so we might have different load balancers here in that load balancing subnet for different applications. Each one may get its own unique security group. And then we have different application servers for running different applications. And each application may get its own security group. And then you may reuse that security group across a number of different instances that are all related to that application. So for our load balancing, what we're going to create here, a security group, doesn't really have anything directly to do with the subnets. It has to do with the devices that will be in that subnet. All right, so let's create a security group for our load balancer. And so here we are in the security groups dashboard, and you can see that we have a default security group. We did not create this. It was created for us at the time we created the VPC. All right, so remember that when you create a VPC, in order for a VPC to operate, it has to have a route table, a network access control list, and a security group. And so by creating a VPC, those three things are created for you in the background. All right, but I typically ignore those default things. All right, so we're going to create a security group, and let's call this one load balancer. You can name it whatever you want. It's pretty well arbitrary. I mean, there are, you can see that there are some limitations around the characters that you can use, and you have a length limit, but it's totally arbitrary, right? I just encourage you to choose a name that makes sense to you. And remember that, the names and descriptions they do two really important things for your team. They remind you of what this is for 6 months from now when you've forgotten all about it. And they also they serve as a communication between you and a future engineer or architect of unknown skill, right? It's just like comments in code. Somebody at some point will come behind you, right? So you ideally, we are choosing names and descriptions that help them understand what you did and why you did it when you are not available. All right, and so this one says we'll just say SG for load balancer. Now, if we were going to have numerous load balancers for different applications or different purposes, then we may give it more semantic names, right? We may choose more specific naming and descriptions, right? Right now, for this example, we're just being a little general. So we'll choose the web apps. All right, so now we've created the security group. We'll go ahead and click this button, and now it's created. Now let's go back and take a look at this. The inbound rules, you'll notice it has no rules, which means every port is closed by default. Right now, if we were to apply this security group to a load balancer, the load balancer could not receive anything, right? So we have to open ports to begin with. We'll come back to that. You'll notice here that it does allow all traffic across all protocols, all ports to everywhere, right? So all traffic is allowed to go everywhere. We're going to come back to that in just a minute, so hold that thought. With inbound rules, let's go ahead and edit these, and there are really only two, right? We're only going to add HTTP and HTTPS, right? And we'll say allow non-SSL and allow TLS, because SSL is pretty well dead, right? Allow non-TLS connections on port 80, allow TLS connections on port 443. And here, we're saying we're going to allow all IP4 ranges, IP addresses, and this one back here, the :/0 means all IP version 6, right? We don't necessarily need that one because we're not really we haven't even enabled IP version 6 on this, but that's why that's there. It's just a default that Amazon puts in there. So we can go ahead and save that. All right. So now when we look at the inbound rules, we're allowing inbound on IP version 4 on 80, IP version 6 on 80, and the same for 443, right? Now, if you felt like you don't need those, right, we could edit those and we could remove the IP version 6, right? Perhaps we don't really need that because we haven't even enabled support for IP version 6, right? So we could just as easily remove those, right? So at this point, if you remember what we did in the previous demo, when we created and applied the network access control list, you'll remember that for the NACL, we also opened inbound ephemeral ports, but that was because the NACL was stateless. It did not recognize responses as being responses. And so the security group is stateful. It does recognize responses as being responses. So that means that when our load balancer initiates a new connection to a backend instance on port 8080 or port 3000, whatever, and then receives a response on an ephemeral port, the security group will recognize that incoming response as being a response to what went out earlier. And because what went out was allowed, the incoming response is then allowed, which means that we don't have to open the ephemeral ports on the inbound rules, right? The stateful nature of security groups will cover that. Now let's take a look at outbound rules. Outbound rules really apply to, because of the stateful nature of security groups, outbound rules apply to initiating new connections, right? So let's go ahead and edit these, and let's think about this for a second. What ports, what protocol, what ports, and what destinations will the load balancer initiate new connections to? There's only one answer to that. Clearly, we don't want the load balancer initiating connections to our database, so we rolled that one out. We don't want the load balancer initiating new connections out to the internet. The load balancer will only initiate new connections to our backend instances, and those will be done on ephemeral ports, right? So we don't need to allow the load balancer. Right now, it's a pretty wide open rule. It's a very lenient rule for our load balancer. So we can remove this one, and we'll add another rule that says custom TCP, ephemeral ports, and the destination will be to within our VPC. Or we could even use a security group reference, right? We could reference the security group of our application servers, but we haven't created that one yet, right? So let's just go ahead, 10.000/16, which is the range of our VPC. And we'll say allow the load balancer to initiate new connections to backend instances in this VPC, right? Not to the internet, not to another VPC, but to backend instances in this VPC. All right, we'll go ahead and save that. Close that. All right. So let's go ahead and create one more security group. We're going to create this one. Let's just call this one, let's just call it web app. It's a generic web application, right? And if you have multiple applications, then you would give, them security groups that and name them in a way that makes sense to you for your application in your situation, right? Web application SG. All right, we're going to again choose our web apps VPC. We'll create that security group. All right, so let's take a look at our web app. You'll see again, no inbound rules by default, and outbound allows all traffic everywhere, right? So let's take a look at the inbound rules. And again, our web app is would be running on private application servers. They are not directly available from the internet. They will be behind the load balancer. So we don't need to open ports from the internet. So let's do this. We're only going to open, again, those ephemeral ports, right? Our backend instances will be listening on some ephemeral port, 3000, 8000, 8080, whatever. If you're using containers, if you're deploying containers to Docker and using bridge mode and using dynamic port mapping, then it could be any one of a randomly chosen ephemeral port, right? So we're going to open 1024 through 65535, but this is where we're going to do something different. We're going to choose the load balancer security group. So instead of specifying an IP address, we're going to say that our backend instances are allowed to receive on these ephemeral ports only if the traffic originated from a member of that security group. And we know that that security group is only applied to our load balancer, right? So now we've tightened the security, all right? We'll go ahead and save that rule. And then we could go down here. We're going to leave this one as is for now, but we could take that a step further and say, well, it's only allowed to initiate new outbound to a database, right? We don't actually even need this. We could technically remove this rule, and due to the stateful nature of security groups, responses to requests that came in on one of these ports would be allowed to go out, right? So we could go back here. Let's just go back to our load balancer and to those outbound rules, and let's modify this destination. Now that we have a web app security group, let's modify this destination here and to be the web app security group, right? So let's modify this this description to allow backend instances that are members of the web app security group, and go ahead and save that. So essentially what we've done is we've created sort of these complementary converse security groups where the outbound of one is pointing at the other, and on the other, the inbound is pointing to backward, toward the first one, right? So again, there you go. Where the web app is allowing inbound from the load balancer is allowing inbound from the internet and outbound to our web app. All right, so that's one way that we can go about really tightening security between those tiers. All right, so that's how we can create and apply security groups.
Now let's talk about VPC peering. VPC peering allows us to connect two VPCs. So a VPC peering connection is a connection that exists between any two VPCs, right? So it allows us to segregate our networks. You'll remember that earlier we talked about how there may be a number of reasons why we want to have separate networks. It could be that we want different departments in different networks, or different environments, or different types of resources in different networks. But oftentimes when we do that, we may also need those different networks to communicate, and we can use VPC peering to do that. Now, the connection that exists between those VPCs is fully managed by AWS. There's no bottleneck, there's no single point of failure. It's all very solid and in high throughput. It is important that our IP ranges not overlap. It is possible to create multiple VPCs with the same exact IP range. And even though that's possible, doing so would prevent us from peering those VPCs. And so even if those VPCs were to overlap by even one address, we could not peer them, right? So they have to have completely unique IP ranges in order for us to actually peer any two VPCs. Now, we can peer between accounts, which is very powerful. Again, we may have, different types of things in different accounts, and we might need a way, we might have a need to peer those VPCs. We could have a, client-vendor relationship of some kind, that exists between two different accounts that we need to peer. Keep in mind that VPC peering is always one-to-one, meaning that the connection that exists is always between any two VPCs. And so that means that there's no transitive peering and there's no edge-to-edge routing. And so what that means is that you cannot go from one VPC to another to another. You cannot go from one VPC through a second VPC to the internet, right? We're going to see a diagram of that here in just a moment. Also keep in mind that there is a charge for bandwidth. So the bandwidth that we incur through that VPC peering connection, we do pay for, right? So if we take a look at a diagram here, you'll see that we have 3 different VPCs. And so a connection is always one-to-one. So if we wanted to communicate with VPC A and B, then we would have a single peering connection between those 2 VPCs. If we wanted to communicate between B and C, we would have a second separate peering connection between B and C. And so again, Amazon VPC does not support transitive peering. Now, transitive peering happens all the time out there in the world. A lot of networks like Equinix and other providers that have very large networks, peering happens all the time. Different companies allow other companies to transit their network in order to get to another network. But those kinds of things can become complex. The routing and the firewall rules and the management of traffic can become complex in that regard. Within Amazon VPC, Amazon prevents this kind of thing in order to prevent us from creating inadvertent network paths that could lead to poor security or poor performance. And in doing so, we could end up creating network paths unintentionally that would be either very insecure or could negatively impact, from a performance perspective, could negatively impact other customers within AWS. And so what this means is that because there's no transitive peering, VPC A cannot get to VPC C by going through B. Right? Now again, that kind of thing happens all the time out there in the real world, but it's not possible within Amazon VPC. If we had a legitimate need for VPC A to communicate with C, we would have to create an explicit peering connection between those 2 VPCs. Right? So let's take a look at another diagram here and we'll see how this actually works. And so here, you'll see here that we have 2 different VPCs and each one has its own range. We have one at 10.2.0.0.16. We have another over here at 10.6.0.0.16. So 2 different unique IP ranges. We also have a VPC peering connection. This in itself, this is a resource that we would create in and of itself. And when we create this resource, we specify the 2 VPCs that we want to peer. And then we also would need route tables. You'll notice that over here, we have a route table associated with perhaps these subnets that says that for any network packets destined for 10.6, we want to route those through the peering connection. And 10.2 remains local. On the other VPC, we have the converse complementary route. We're saying over here, 10.6 remains local, but 10.2 routes through the peering connection. So these 2 VPCs are pointing towards one another via the peering connection. And so we could, using those kinds of routes, we could route the entire VPC. Or we could choose to route specific subnets. We don't necessarily have to route the entire VPC range. We might say, I only want to communicate to 10.6.1, and over here I only want to communicate to 10.2.1, right? So we have our choice. But either way, once we have that routing in place, then we have bidirectional communication between those 2 VPCs. Right? So that gives us VPC peering. And keep in mind, again, like I mentioned, we can peer VPCs that are in the same region, or we can peer VPCs that are in different regions. We can peer VPCs in the same account or across different accounts. Now let's take a look at a few VPC peering scenarios. there could be a number of reasons why we might want to peer different VPCs. Right? Again, keep in mind that within AWS, there is nothing that says we have to do anything in any particular way. VPC is created in a generic way, generic enough that we can create things and put things together in a way that meets our needs. And so one way that we might go about peering VPCs, we might put our publicly available web applications in one VPC. We could put our backend services in their own VPC, and we could put our databases, yet again, in their own VPC. And then, of course, we could peer these. We could allow the web to talk to the backend VPC. We could allow the backend VPC to talk to the database, right? But, of course, web and databases would not be allowed to talk to one another directly. So here's an example whereby separating these out into multiple VPCs, where we have the ability to control routing between VPCs. We have, of course, the ability to control firewalls with network access control list and security groups. Doing this kind of diagram could provide a really solid a foundation for security, but the trade-off is that we have these two peering connections with potentially a lot of data moving through them. And so cost would be the trade-off. If you find that a diagram or a solution like this provides you with the security you need, the trade-off is that you're going to pay for that in terms of the VPC peering connection, charging that bandwidth, right? So that's one thing to keep in mind as we move forward using AWS, and especially once we get into solutions architecture, where we start making architectural decisions. We have to keep in mind the trade-off. A lot of times there's a trade-off to be made between security and cost, or security and performance, or cost and performance, and so on. Another way that we can separate might be, again, between different departments. And so, again, we might have, like we mentioned earlier, we might put different departments in different VPCs. Finance has their servers and applications. Accounting has theirs. But we might peer these two VPCs so that accounting and finance can communicate with one another. We might want to centralize certain resources. We might want to put certain types of intranet or file sharing applications and services in one VPC, and we might want to provide a way for different departments to access those that are centrally located while preventing those departments from communicating to one another directly. Again, we might have third-party access. We could have customers. We could have vendors, right? And our customers may need to access our shared resources, right? But we don't want our customers communicating directly. We may have a vendor that is providing perhaps some kind of monitoring service, and they need to reach our VPC, but we don't want our customers and vendors communicating directly. So there's all kinds of ways that we could go about isolating services within different VPCs and creating these kinds of peering connections. And again, it's all according to what your applications need within your business. Now let's take a look at another demo of peering two VPCs.
Okay, from the VPC dashboard, let's go ahead and before we peer VPCs, let's just take a look at the ones that we have. You can see here's the web apps VPC that we've worked with so far, and I've taken the time to create another one here called data stores. So one pattern could be that you separate your VPCs according to some kind of common functionality. It's totally arbitrary. It's up to you how you separate them. You could put data stores in the same VPC as applications, but you could also see a greater degree of security by putting them into their own VPC. And so let's go ahead and peer these two. We'll go down towards the bottom over here and go to peering connections. And we'll go ahead and say create peering connection. And here we could say web apps to data stores. Again, pretty well arbitrary. It's just something to help you make sense of this peering connection later. And we'll say the VPC requester could be the web apps. Doesn't really matter which one you choose first. If the two VPCs are in the same account, then it doesn't really matter which one you choose first. And so coming down here to another VPC, you can see that we can peer VPCs with another account if you have that account number and the VPC ID, or we could also peer to another region. And that's a fairly recent, sometime that was given to us sometime in mid to late 2018, the ability to peer VPCs between regions. And so here we're going to just say my account and this region, because both of those VPCs are in the current account in the current region. And so we'll choose data stores. And you can see here the important thing to keep in mind is that the CIDR blocks cannot overlap. And so for our web apps, we have 10.0.0/16, and then for the data stores VPC, we have 10.1.00/16. And so even if they were to overlap by, two addresses, even one address, they would not be able to be peered. So that's all we have to do. We'll go ahead and create peering connection. And you can see just like that, we've created a peering connection. And it goes to, you'll see the status here says pending acceptance. So we still have one more step to go through. We have to say accept the request. And this makes more sense when you are peering with a different account, but we still have to do it. All right, so we'll say, yes, I do indeed want to peer these two VPCs. Right? And so now that peering connection is active. And if we go down here, we can see we have information about DNS resolution between VPCs. We have route tables that are not showing up yet, so we need to edit those route tables. And so what this is saying is that essentially this is saying that this VPC peering connection is not being used by any route tables. So in order for traffic to flow between the VPCs, we have to tell routing to make that happen. We have plumbing in place, but we need to actually make it work. So let's go up here to your VPCs. Let's go ahead and choose web apps. And let's go to route tables. Let's go ahead and filter this by web apps. And we'll see that we had we created a route for public traffic when we routed to the internet, right? And so that route table is associated with subnets that are meant to be public. And so we might want to create a route table for traffic that is meant to be private between this VPC and our data stores VPC. All right, so let's create a new route table and call this one private traffic. It will belong to the web apps route table, and we're going to do the same exact thing we're going to do the converse of this in the other VPC. So we're going to end up doing these things twice. All right, we'll go ahead and close that, and now we have our private traffic. Let's go to, you'll see here that we have no routes other than the local route. So let's edit that, and we'll say that the destination will be 10.1.00/16. So what we're saying is that any network packets that are destined for an IP address within this range will be routed to the peering connection web apps to data stores. And we'll go ahead and save those routes. And now you can see that we have a route that remains local and a route to 10.1 going through our peering connection. Now we need to associate this route table with our private subnets. So let's go ahead and edit that, and we'll go ahead and click the application subnets. So in this, remember that in this particular example scenario, we have two subnets, one that is publicly accessible to the internet that we are using for load balancers, and then one that is private, not accessible from the internet, and that we are using for our application servers. And so it's the application servers that will communicate with data stores, not the load balancers. In fact, if we think about the routing that we did, we allowed the entire VPC to route to the data stores, but we could limit it just to the subnet, right? We could say 10.0.10/24 if we wanted to exclude the load balancer subnet from that routing, right? So let's go ahead and make sure that we are associating this private traffic route with our application server subnet. And we'll go ahead and save that. And if we go back to our subnets and take a look at applications, take a look at the route table there. Now, from the subnets perspective, you can see that it is indeed associated with that new route table that we created, and it has a route to the peering connection. But that's only in one direction. We need to tell the other VPC how to route, right? It's not enough to just do one side of it. We have to do both sides. So let's go ahead and filter this. Let's refresh this page here. And then let's filter this by data stores. It doesn't have any subnets yet, but that's okay. We can always create subnets later. We don't necessarily need subnets in place before we peer a VPC. So if we take a look at our route tables, again, we have the main route table, which is, again, the default route table that was created at the time this VPC was created. I generally don't like to use that for custom routes. I'll go ahead and create a new route table. Again, I'm going to call this one, again, private traffic. And the reason I can do this is partly because it's in a different VPC. So we might have two route tables with the same name, but they belong to two different VPCs. So this one, private traffic for the data stores, and then we also have private traffic for the web apps. All right, so we've created that, and now let's go to our routes. And again, here's that local route that's always there. You can't remove that. Whoops. Select the right one. So again, the local route, let's go ahead and edit that. And so 10.1 is local, which means that 10.0.0 is going to be the remote VPC, the one that we've peered with, the web apps, right? So again, we're going to choose down here a peering connection, web apps to data stores. Go ahead and save that. And then, of course, we would, if we had subnets in this VPC, we would associate this route table with those subnets. And so by doing that, again, I just want to point out that for the 10.1 VPC, where 10.1 is local, 10.0.0.1 is going through the peering connection. And if we go back and look at web apps, you'll see that the converse is true. That if we look at those routes, 10.0.0.0 is local, 10.1 goes through the peering connection. So essentially you have these complementary routes for two VPCs pointing towards each other by way of this peering connection. And so now that we have the peering connection created as a resource, remember that the peering connection is itself its own resource that was created, and then we created routes within route tables. And so now, if you take a look at the route tables tab here, you'll see that we have these two route tables are essentially associated with this peering connection because they reference the peering connection. And by doing that, now we gain bidirectional communication between those two VPCs.
Now let's talk about VPN access into Amazon VPC. There are plenty of times when we have applications running within an Amazon VPC and perhaps applications running on premises, and perhaps different applications need to communicate to one another. Or maybe all of our applications are running within Amazon VPC, but we have administrators on premises that need to reach those in a secure way. And we can enable that kind of secure communication through VPNs. Okay, so you'll notice here that we have a VPC here at 10.2.00.16. We have perhaps a database here in a private subnet. And in order to enable VPN access, we first need this VPN gateway. Again, a gateway is a device that allows two networks to communicate with one another. And the VPN gateway is specific to VPNs because it provides IPsec encryption. And even though it appears to us as one device, under the hood, behind the scenes, we know that according to Amazon documentation, we know that that is actually powered by multiple physical devices. That what appears to us as one device is actually at least two different routers in two different facilities. And so when we create a VPC tunnel with this VPN gateway, we actually get, for every VPN connection, we actually get two tunnels, right? And so we have our VPN gateway on the Amazon side. We have our customer gateway on premises or in a remote location somewhere. And so the customer gateway could be a physical device like a Cisco ASA or a Palo Alto, or it could be a virtual device. It could be something like StrongSwan running in a Linux container. And so either way, we have the two gateways that are capable of IPsec encryption, and between those two, we get this VPN connection. And between these two gateways, we get another VPN connection. And again, each VPN connection receives two tunnels. So on the Amazon side, it's already highly available, it's fault tolerant. And so if we wanted fault tolerance in this connection, then for each VPN connection, we would need two customer gateways in order to satisfy fault tolerance and high availability of that VPN connection. Once we have our gateways in place and once we have our VPN connection, we then have a route table. And once the routes are in place, here what we're looking at is what we call a propagated route. We can configure routing on the actual VPN connections, and whatever routing we configure here, whether it be dynamic or static, those routes can be what we call propagated to the route table for us. And so once that route, you'll see here perhaps, for example, routing 192.168.00.16, that would then allow bidirectional communication between our VPC and some remote location over IPsec encrypted communication, right? So it's very easy to set up a tunnel, a VPN tunnel with Amazon hardware VPN using a VPN gateway. So keep that in mind. If you have a need for communication between on-premises or something outside of AWS, and you need that encryption to remain private and encrypted, then AWS hardware VPN may very well be the answer. Now let's talk about AWS Direct Connect. With Direct Connect, we have the ability to gain a dedicated private fiber connection into AWS. And these come in either 1 gigabit per second or 10 gigabit per second options. Those are the two most common. It is possible to get a Direct Connect connection that is lower than 1 gigabits per second, but those are actually the most common. And we can use this to establish private connectivity into one or more VPCs within that region, or to gain access to Amazon services such as S3 or DynamoDB in that particular region. Keep in mind that any bandwidth that leaves an Amazon region that goes over the internet, we will pay bandwidth for. And so if you're doing a lot of transfer between Amazon services like S3, for example, if you're using the internet, then you're going to pay a particular fee. But with Direct Connect, we get lower data transfer rates than using the internet. So if we have a very significant volumes of data, it could be cheaper for us to leverage Direct Connect in order to gain access to those lower bandwidth charges. Direct Connect also gives us a significant increase in bandwidth and throughput as opposed to accessing Amazon services through the internet. It gives us more consistent network performance. And in order to use this, in order to set up the routers between on-premises and AWS, it does require us to leverage External Border Gateway Protocol, or eBGP. There are a number of AWS Direct Connect providers. We generally work with some type of a provider within the Amazon Partner Network that can help us run that fiber line between our location and AWS. And some of those providers, depending on where you are, could be Equinix, Intergion, Cologix, Digital Realty. There's a number of different providers that we might look to, again, depending on the region that you're in or the country that you're operating in. And so we have our location, wherever that is. It could be on premises, it could be a co-location somewhere, some remote facility. And we generally work with an AWS partner, some service provider. They would run a line between our location and AWS Direct Connect facility or point of presence. From there, AWS already has lines going into that particular region. Once we have our Direct Connect connection into that region, we can then divide that Direct Connect connection into multiple VLANs. So let's start at the top here and take a look at this diagram. You'll notice here that I have several different AWS services, such as Simple Queue Service, Simple Notification Service, S3, and DynamoDB. AWS services exist within a public address space. So if you were to communicate to these services directly, apart from Direct Connect, you would reach those services over public IP addresses. And so it is possible to still reach those services, still using public IP addresses over Direct Connect, and we can achieve that through routing. We can route Amazon's public IP space through our Direct Connect. And so in order to do that, we would have to divide this Direct Connect connection into multiple VLANs, and we would assign one VLAN to that public address space, right? And that would allow us to reach those Amazon services. If we also wanted to use that same Direct Connect connection to reach multiple VPCs, then we would divide that connection again into VLANs. Each VPC would get its own VLAN, right? And so that would enable us to access services running within these VPCs. So if we had instances here, we could reach those instances on private IP addresses. It is worth noting that even though this is a dedicated private connection using a VLAN, it is not encrypted by default. So a VPN and a VLAN through Direct Connect are two different things, right? So keep that in mind, that just because you have a VLAN over Direct Connect does not mean that this traffic is encrypted. So if you have a regulatory need to encrypt that traffic end to end, then you would have to do something in addition to this VLAN in order to make that happen, right? So keep that in mind, that Direct Connect gives us a dedicated private fiber connection, generally in 1 or 10 gigabit per second options. Applications need compute power, and AWS offers an extensive collection of options geared toward every possible use case, from simple low-traffic websites to APIs handling billions of requests, to machine learning and real-time data processing. In this lesson, we will cover the compute options offered by Amazon Elastic Compute Cloud, serverless computing, container-based applications, as well as several great demos. Now let's review an introduction to Amazon Elastic Compute Cloud, or EC2. With EC2, we have the ability to create virtual machines. We call them instances. And we have our choice of Linux or Windows, very many flavors of either one. And of course, these are powered by either the Zen or the Nitro hypervisor. Up until recently, Zen was the hypervisor for everything. But with some of the later generations of EC2 families, such as the C5 series, M5, R5 series, some of these are now using the Nitro hypervisor, which is more heavily borrowed from KVM and moving away from the Zen hypervisor. The benefit of the Nitro hypervisor is that it gives us very close to bare metal performance. The overhead of the virtualization is very, very low compared to that with Zen or other hypervisors. Bare metal is also available. So if you have workloads that could benefit from having access to bare metal without the overhead of a hypervisor, that is an option. Generally, when we choose instances within EC2, we don't really get to say, well, I want, this much CPU and this much memory. We choose from sort of a price-fixed menu, and we do our best to choose a machine that gives us a certain, blend of CPU, memory, network I/O, and so on that will match that particular workload. And of course, the beautiful thing about EC2 is that, as we talked about in the very beginning, the on-demand nature of EC2 and the lack of long-term commitments, the pay-as-you-go pricing, allows us to change our minds, right? And that's one of the big benefits of cloud computing, is that we are not locked into our decisions for a long period of time. So if we try one of these instances and we find that after monitoring our application for a while, we find that that particular combination of CPU and memory doesn't really work that well, that perhaps we need more CPU or we need more memory, we can throw that machine away and create a new one very easily. And that really, right there, that ability is, gives us a level of flexibility and agility that we've never had before. And that concept, that ability, is really the number one driver for enterprise adoption of AWS, even above cost savings. Because through these kinds of things, we have access to technology and a way of doing things, a way of approaching our infrastructure that we've never had before. And so with EC2, we also have the ability to launch virtually any number of instances. We can launch one, we can launch 1,000. Of course, within our current account limit. Remember that Amazon services have sometimes hard limits and sometimes soft limits, and the initial soft limit for EC2 instances is somewhere around 20 instances, at least at the time of this video. And so if you need 1,000 instances, you can get that by submitting a ticket to AWS support and asking for an increase in that limit. There are different billing models we're going to go into in detail here momentarily. Depending on the operating system, most operating systems like Windows and Red Hat and so on will charge by the hour. So the hourly fee in those cases will include the license for the operating system, right? So if you were to compare something like Fedora with Red Hat, you would see that the same instance would cost more with Red Hat or Windows than it would with Fedora, simply because the hourly fee includes a license for the operating system. Now, for at least at the time of this video, for Amazon, Linux, and Ubuntu, we actually have per second billing, right? So again, per second billing is available for certain operating systems. Not every operating system qualifies for per second billing. But either way, if you're using an hourly billing model, then if it's billed hour forward. So what that means is that if you run a machine for 5 minutes, you pay for the whole hour. If you run it for 61 minutes, you pay for 2 hours. With a per second fee, it's essentially rounded up to the next second, but there's always a 60-second minimum that you have to pay for. We also have the AWS Marketplace, which offers what we might call canned solutions. So if you're looking for a particular type of software, say a virtual networking device, like some type of a virtual Cisco or virtual Palo Alto device, or perhaps some type of big data solution. There's are a lot of different solutions available that are already packaged as a machine image and already available for us to choose. And in those cases, the hourly cost of the machine also includes a license for that particular piece of software, right? So the takeaway from this lesson is that with EC2, we gain access to either virtual machines or bare metal. We have the ability to launch one machine or 1,000 machines or more, and we have a lot of flexibility in terms of which operating systems to use and the different billing models that we'll use. And of course, throughout this lesson, we will take a closer look at a lot of details regarding EC2 and how we might deploy applications to those instances. Now let's talk about the Amazon Machine Image, or the AMI. Within EC2, when we create a virtual machine, we have to have something to begin with. We have to have a way for that machine to boot into some kind of an environment. We have to have an operating system and perhaps even applications or other configurations already done. And so that's what the machine image is for. The machine image is essentially a bit-for-bit copy of the root volume. It contains the operating system and anything else that was installed. And so we generally have our choice of Windows, Linux, FreeBSD, and many different flavors of those operating systems. At this time, we don't have access to Solaris, but we should be able to choose and make use of those other three. Now, we can find machine images in a number of different places. We have machine images that are provided by AWS, such as Amazon Linux, different flavors of Ubuntu or Red Hat or Microsoft Windows. And then we also have trusted publishers like Canonical or Red Hat or Microsoft for other flavor or specialized flavors of those operating systems. We also have community AMIs. Community AMIs are publicly available, being provided by other AWS customers. So I could shell into a machine, a virtual machine, an instance, and I could install whatever I wanted. I can install, perhaps Nginx or, certain flavors of Node.js or Python or what have you, and configure a machine in a certain way that might be useful for myself as a developer, and then realize, this is useful for a lot of developers. So let's make this publicly available as a community AMI. Now, generally the way I approach community AMIs, considering that they are published by who knows who, is that if I wanted to, experiment with something, then I might look to the community to see if somebody has already compiled or installed a particular, configuration of different pieces of software, so that I have a fresh place to start. And then once I run that prototype and check it out and feel satisfied that, that does work, I think I do want to invest more time into that particular, configuration of software, then my policy is, well, I don't know who created that. I don't know what else they may have put on that machine. And Amazon will also tell you, if you read the documentation, Amazon says that AWS will not vouch for the security or the integrity of community-based images. So it is our responsibility as a customer to ensure that we are using things that are secure, right? So in terms of the community images, I would just leave you with the warning that you don't really know what went into them. They might be fine to try and experiment a little prototype or something in a sandboxed environment, but when it comes to production, I would always start with a machine image from Amazon or another trusted provider, and then whatever software I needed, I would install and configure myself so I know exactly what is on that instance. And then lastly, like we mentioned earlier, we have the AWS Marketplace where we can find those canned solutions. So in terms of launching an instance, we first choose the machine image. whatever that is, right? Again, it's going to be the operating system and any software that's installed, any configuration that was put in place, any users or groups that were put in place within the realm of authentication that is the operating system. And once we choose the AMI, we then launch the instance by choosing, what type instance do we want? Do we want, like a T2 small? Do we want a C4 large, an M5 extra large, right? We choose the family and the type of instance. And once we launch that instance, we could stop there and we could have that machine running, doing its job, using the software that was installed as a part of the image. We could go further and install different applications, configure what have you, and then go on to create our own private machine image. When we create images of instances, those images default to being private, only accessible by the account in which they were created. But you could go on to share that image with another account. You could share it to the public by making it a community AMI. And any instances that are launched from that private AMI will all essentially be clones of one another, right? So creating custom machine images is a really good way to give yourself a known state, right? So when a machine comes to life, you know exactly what is installed and what is available on that machine. Now let's talk about key pairs within Amazon EC2. Key pairs here, how we're talking about these, are public and private keys. So these types of key pairs means that we have a private key that we keep locally that we generally don't go giving out, and then we have a public key that is safe to give to other systems, right? And so this enables public-private key authentication and encryption. And these are 2048-bit SSH2 RSA keys. Now, we can create these key pairs either directly within AWS, so we could make a call to the AWS API, either with our CLI tools or in the console. If we allow Amazon to create it, we essentially download the private key pair from AWS. Or we could create it locally and import the public key half to AWS, right? So either way, AWS will keep the public key and AWS does not keep the private key. Now, for those of us who might be overly, security-minded and want to be as careful as possible, then it might be a good practice for you to create the keys locally and use the import method rather than having AWS create it. By doing a local creation and import, you know for a fact that AWS does not have that public key. And then when we launch an EC2 instance, we generally choose a key pair. And by choosing a key pair, that would allow us to gain remote access to that instance later if we needed to. Now, in the case of Linux, the public key will be added to the .ssh authorized key file. And so that would allow us to authenticate into that Linux operating system using public-private key pair authentication. We would use that private key that exists locally in order to authenticate into that Linux machine. In the case of Windows, the administrator password is automatically encrypted by AWS. And they use the public key to do the encryption. We can then use the private key to do the decryption. So keep that in mind that if you need remote access to an EC2 instance, we need a key pair. Whether it's Linux or Windows, we need a key pair in order to enable that remote access to our EC2 instances. Now let's take a look at a demo of launching a Linux instance.
From the AWS Management Console, we can go to EC2. And again, we want to verify the region that we are operating in. Whatever region is selected here is where our instance will live. And so we're currently in Ohio, where we created our VPC. And you can see we currently have no instances running. So let's go ahead and click here to launch an instance. And for Linux, we have our choice. We could choose Amazon Linux, we could choose Red Hat or SUSE, we have Ubuntu. And you can see that all of these do offer a free tier, that they're eligible for the free tier. And then, of course, we want to look to the type of virtualization, which we generally prefer HVM with SSD boot volumes. So I'm going to go ahead and choose the latest version of Amazon Linux 2 with SSD-based root volume. This would be based on EBS, the Elastic Block Store. And you can see here that this one supports both x86 and the new ARM processors. So for now, we're going to stick with x86. And now once we've chosen the machine image, now we choose the instance type. And you can see here that we get this long list of all kinds of different instances, and we can choose, by general purpose, by compute optimized GPU, memory storage, and so on. We can also filter out by the current generations or all generations. So if we wanted to go back and look at T1s or C3s, then we could look at all generations. You can also notice here that the T2 Micro is eligible for the free tier. So again, what that means is, there's really no such thing as a free tier account. All accounts are identical. It just means that for the first 12 months of that account, after you sign up with your email address and you put in your billing information, 12 months from that day, you have access to a certain set of resources that are deemed to be a part of the free tier. In the case of EC2, the T2 Micro is given to you for free. So you can run one of these instances. It'll say here, you get up to 750 hours of micro instances each month, right? So that means you could run one machine all month long, all day, every day, for the entire year and not pay anything for that machine. So then, of course, from there, we could just go ahead and review and launch if we wanted to. Otherwise, we could go on and configure more things. So let's take a look at what comes next. So here, I want to launch one instance. You could launch 10 or 100 or 1,000 if that number is within your current account limits. There are initial soft limits around the number of machines that we can launch. In terms of the network, we do have to choose a VPC. And so in this case, I'm going to choose the web apps VPC that we created earlier, and I'm going to launch this into the applications subnet. This is the private subnet that we created earlier, and then, of course, I will access that over my VPN connection. I have a VPN connection established here from the office into the VPC. Now, you'll see here that the subnet setting for auto-assign public IP, the subnet setting is to disable, and that's because if you remember what we did back in VPC demos, when we created the applications A, it was meant to be private and not accessible to the internet. And so because there is no route between the application subnet and the internet, then we don't really need public IPs. We'll just go ahead and use the private IP. We'll scroll down here. We could attach an IAM role if we wanted to, provide some way of gaining access to temporary credentials. But for now, since this is just a simple demo of launching a Linux instance, we'll go ahead and skip that. We could say protect against accidental termination. And so it says here that if you turn this on, this is sort of like a safety switch. Or before you can terminate this instance, you have to turn the protection off. So it just helps, prevent accidental termination. If we were to turn on detailed CloudWatch then that would bring our default monitoring intervals from 5 minutes to 1 minute, and we would pay an additional charge for that. All right, so let's scroll down here. We don't really need to worry about any of the other stuff. You'll see here under network interfaces, ETH0 is the default network interface. And we could add others if we wanted to have multiple network interfaces. Let's go ahead and go to add storage. And you'll see here that this instance does come with an 8 gig general purpose SSD volume. And so it will operate at about, 100 IOPS or so, maybe less. We could add an additional volume if we wanted to store data somewhere else other than the root volume. We could also change the size. If we wanted just a larger root volume, we could specify 20 or whatever. I'm just going to leave that at 8. And it says here, free tier eligible customers can get up to 30 gigs of general purpose storage. So this even this volume is free within that free tier period. Going on to tags, it is a good idea to form some kind of consistent tagging strategy so that you can keep your AWS environments organized and use those tags to attribute cost. And it doesn't really matter if what key values we use, as long as we are consistent and we continue to use those same keys and values, right? So I could say, what application this is for, and might be for some kind of a web API. You name the application, and we might add, a cost center, right? The ID of a cost center, and we might add owners and other kinds of tags. Going on to the security group, generally we create security groups. You saw earlier in the VPC demos that we created a security group, and here we have the option of selecting one. So far we only created the load balancer and the web app, so we could choose that one. And you'll see here that it's only currently that security group is only allowing communication between the load balancer and the web app instance. Of course, we could create a new one if we wanted to, but for now, let's go ahead and use one that we created earlier. We will need to modify the security group rules to allow SSH from our local address. So let's go ahead and review and launch that. And again, it's giving us a warning. It says you will not be able to connect to this because it requires port 22 to be open. And your security group doesn't have port 22 open. And that's okay. We're going to fix that here in just a moment. So let's go ahead and continue. Review this. We're using Amazon Linux 2 on a T2 Micro. We have the web app security group. And then, of course, we could take a look at storage and other things. We have an 8 gig root volume, and we have all of the necessary tags. Let's go ahead and launch that. And we'll also need to choose a key pair. We could choose an existing one. We could create a new key pair, or we could proceed without one. If you go without one, then it says it wants you to acknowledge that you will not be able to connect to this instance unless you already know the password built into the image. But this image does not have one. This particular image requires key pair authentication. So I'm going to choose an existing key pair that I have for US East 2. Well, you know what? Let's go ahead and create a new key pair. And we'll call this one Fundamentals. And I just want to show you what happens here. It says here you have to download the private key before you can continue, stored in a secure and accessible location. You will not be able to download that again after it's created, right? So when you create key pairs, you only have this one opportunity to download that key pair. So I'm going to go ahead and download that, and you can see here it's asking me to save this. I'm going to go ahead and save this under my downloads folder, and then I'll go ahead and say launch instances. And then of course you can see now it's telling us that this particular instance is launching. If we go there, you can see that it's currently pending. while that instance is being created and booting, let's go to the security group. You can see down here we have applied the web app security group. And if we click on that, it will take us to a panel in which we can modify the security group rules. So I'm going to say edit this. I will add a rule, and I'm going to allow port SSH on port TCP on port 22. And the way that my current VPN works is through network address translation. And so even though my local machine would be a part of the 10.255 network, but my address is being routed through my VPC using network address translation. And so the IP address would appear to come from the VPC itself. So I'm going to put in 10.000/16, and I'm going to say SSH over the AWS client VPN. And we'll go ahead and save that. And so now that we've gotten port 22 open, let's go back and see if this instance has launched. And there it is. You can see I have one for another use case that is currently in a stopped state, and then this one here is in a running state. And so in terms of states, we could stop the machine, which means that it still exists, just like this other one here in the list, but it's not running. We're not paying an hourly charge for it. We're still paying for the EBS volume, the root volume, but we're not paying the hourly CPU time feed. Stop hibernate means, this is something we would have had to enable at launch, which we did not do, but stop hibernate is basically the same as stop. It puts it into a state where it's not running, we're not paying the hourly fee, but the contents of memory are preserved, so that when you restart that instance from a hibernate state, then all of the contents of RAM are put back. So that's very useful for having applications pick up immediately where they left off without having to wait for processes to start and then data to be pulled from disk. So now that this one is running, we can also see that the status checks, the hypervisor status checks, have all returned everything is okay. So if we look at the status checks, we have the system and then we have the instance. And so the system says from the AWS systems point of view, everything is fine. And this one here says, as far as the hypervisor and the instance goes, everything else is fine. Okay, so now that this one is running, let's take a look at the description. You'll see that we did receive a private IP address. We did not receive a public because we opted out of that. We could assign a public IP from Elastic IPs, but we don't really need to. If this is meant to be a private application server, inaccessible directly from the internet, if it's meant to be behind a load balancer, then it doesn't need a public IP. It doesn't need to communicate with the internet directly. And so with our VPN that I have here at the office, I can still connect to that private IP. So let's go ahead and copy that, and then I will switch over to the terminal. So before we actually SSH, first I want to point out about this particular key. You'll notice here that the fundamentals.pem key that we downloaded, for Linux instances, this key will be used to provide authentication against the operating system. So we will use it during our SSH shell into the machine. For Windows, this key will be used, the public part that Amazon has will be used to encrypt the Windows administrator password, and this private part that we have will be used to decrypt the Windows administrator password. And so you'll notice here that for Linux, that the permissions are way too lenient, right? We're giving essentially everyone read, write, and execute. We don't want that. And so before SSH will allow us to use that key, we need to do a chmod on that and go chmod 400 which will then remove those. If we do a list again, you'll see now that only the Richard user is allowed to read that key. That is the level of permissions that SSH prefers for SSH keys. Right? Otherwise, we would get an error. If we tried to SSH with these kinds of permissions up here, we would get an error in using that key. And so now that we have made the permissions much more restrictive, now we can SSH. We should be able to say SSH -i /fundamentals, and then for Amazon Linux, the user would be ec2-user @ and then we'll paste the IP address, and we'll go ahead and try to connect. And there we go. It says, again, now we're connecting to a private IP address, in my case over the VPN. In your case, if you don't have a VPN, then you may need to use either public IP addresses to gain access to publicly available instances, or use a bastion host. And so now it says, are you sure? Yes. And there we go. Now we have a shell into Amazon Linux 2 AMI, and you can see here we are indeed at ec2user at that particular address. And so we can see that we are now logged into that particular machine, and we will continue to explore this in an upcoming demo. Right, so just like that, in just a few minutes, we have launched a Linux-based EC2 instance and gained remote access to it by way of SSH.
Okay, so now let's talk about the instance metadata service. The instance metadata service is a very special URL available to us that we can query in order to get information about an EC2 instance. And that URL looks something like this: http 169.254.169.254/latest/meta-data. And of course, if we were to query that URL, we would get back a list of other URLs that we can reach. And what this does is that from within an EC2 instance, we can use this URL to retrieve information about that instance. Right? So an EC2 instance can use this to get information about itself. We cannot access this URL from outside an instance, and we cannot use this URL in order for one instance to get information about another. It's always so that one EC2 instance can get information about itself. And so this is very useful when it comes to bootstrapping EC2 instances, or doing some type of programmatic response to the environment, so that when a machine comes to life, it can go and find out what type of machine is it supposed to be, what type of job is it supposed to perform. What is my IP address? What type of volumes do I have attached? Those kinds of things are available, right? And so there's all kinds of information that we can retrieve through the instance metadata service. We can retrieve the machine image ID. We can retrieve the DNS host name, the instance ID, the instance type, the private IP address, and of course, again, this is often used with different types of scripts for instance-specific configuration. So one of the really powerful and beautiful things about AWS is the level of automation. And as we will talk more about later, the only way to truly realize the power of AWS, the cost savings, the flexibility, the agility, is through leveraging automation. And this is one of the critical or key components to enabling automation, is when we have instances come to life through autoscaling, which we'll talk about later, ideally that instance is able to configure itself, ensure that whatever software is needed is installed, configured, and whatever processes are needed are running, so that that machine can come to life and get to work doing what it's supposed to do. And so the instance metadata service provides a very rich API, so that machine has all of the information that it could possibly need at its disposal in order to programmatically essentially become what it's supposed to become and get to work doing what it's supposed to do. And so we will take a closer look at the instance metadata service in upcoming lessons. Now let's take a look at a demo of querying the instance metadata service.
Okay, so I'm at my terminal, and I'm going to shell back into the instance that we launched and shelled into earlier. There we go. So now we have a shell into our Amazon Linux instance. Now the instance metadata service is available at a very particular URL. So we can visit that by doing a curl to http 169.254.169.254/latest/meta-data. And by curling that, we will get a list of other resources, different pieces of information that we can retrieve. And so again, this particular URL is only available from within an instance. And so I can only use this from within an instance to gain information about this one instance. From this instance, I cannot gain information about other instances using instance metadata. And so, for example, let's replay that, and then we can go with the first one. All of these would then just be additions to that URL. So we could say meta-data/AMI ID, and it would give us back the machine image ID that is currently in use on this instance. We could do the same thing with something like host name, and you'll see here is the host name. We could go with instance ID as well. Let's try instance ID. And there you go. There is the instance ID. And notice it's returned as plain text. And so we can use the instance metadata service to write automated scripts, CLI scripts, that can be used to bootstrap this instance on boot. So we could do something like this. We could say instance ID equals, and we could copy that URL and paste it here. And by playing that, and now we can echo the instance ID, and there you go. So now we can do things like that. We can capture things in environment variables and use those in our scripts. So there's a lot of information here. There's more information about the network, for example. Let's take a look here at the network, and you'll see there's another level to that. So we have to go network interfaces, and we keep on going, right? Sometimes it keeps going until finally you reach some information. So there we go. Now we have information about the MAC address, and we could take a look at placement. I believe placement would show us. Let's see what that shows us. Then placement availability zone, right? So let's copy that and then try that one. And there you go. Now it's showing us the availability zone. So we could capture that, say, in a script, and then use that information somewhere else in that script, right? So we may want to, for example, capture the instance ID and the particular availability zone, and then use the availability zone to determine maybe if there's an EBS volume available, and then use the instance ID as a call to attach an EBS volume, or to update routing tables. We can use information about the network to say update, automatically update route tables or firewall rules or things like that, right? So there, again, a lot of information available in this particular list of possibilities to run with the instance metadata service. And the primary use case for the instance metadata service is to automate the bootstrapping of this machine. So this machine can, boot and then say, all right, who am I and where am I and what am I supposed to be doing, right? So we can use those scripts to pull the instance ID and any other information that we need about this instance in order to then go on and configure other things.
Now let's review bootstrapping with user data. Within EC2, user data are scripts that would allow an instance to configure itself. So remember that earlier we talked about how with the on-demand nature of EC2, we can launch a machine at any time. And when that machine comes to life, we need that machine to perhaps start certain processes, perhaps download different pieces of code, or call home to a configuration management service. And so the user data allows us to do that. It is one of the keys to high availability and self-healing, right? When we think about an environment in which, due to the disposable nature of EC2 instances, they really can come and go at any time. And so, as we'll talk about later, when we get into auto-scaling, you can imagine that if we were to create a system where, with very little manual intervention, and we have a machine come to life, we need a way for this machine to configure itself. And in doing so, in creating that kind of thing with auto-scaling and automatic bootstrapping, we can create self-healing environments. It's a very, very powerful pattern for enabling fault tolerance and high availability and efficiency in our processes. And so the user data that we do have a limit of 16K, and these scripts are executed on the first boot, at launch on the first boot. And so if we were to reboot that machine, no matter how many times, that script would never be executed a second time. It's only executed during the first boot, right? Now, it doesn't have to be a script. It can be a list of environment variables as well. So for different operating systems, on Linux, we have the ability to create simple bash scripts, or it could be Node.js or Python, or pretty much any executable binary that we can list, right? And basically any other executable. For Windows, we can use a batch script or a PowerShell script. So either way, we have this really powerful ability to give our EC2 instance enough information to get itself up and running, doing what it's supposed to do without manual intervention. And so when we combine user data with the instance metadata service with custom private Amazon machine images, that gives us a very powerful tool for creating a very efficient, automated, self-healing, and fault-tolerant environment. All right, so now let's review a demo of launching a Windows instance.
From the EC2 dashboard, we can go ahead and click on Launch an Instance. And for Windows, we can scroll down. You'll see that below the Linux stuff, you'll see Windows here. We could also go up here and search for an AMI based on different terms, right? So if we search for Windows, then it would give us a number of Windows instances. And here you can see we have Server 2019 base, and then of course Server 2019 with other things. So we have base with containers, with SQL Server Standard, SQL Server Enterprise, and so on. So let's just go ahead and keep it simple. We'll start with the 2019 base. We'll select that one. Just like earlier, we do have some free tier eligible, so we'll go ahead and choose that one. But if we wanted, if we wanted to go with a general purpose, something like, well, let's just choose like a compute optimized. We could go with a C5 D large, for example, or a C5 large. So, just for the sake of showing that, let's go ahead and choose a different instance type. So perhaps we feel like, 2 cores and 4 gigs of memory would be better than, if we go back to and compare that, 1 core and 1 gig of memory probably, won't run Windows all that well. So by going with the C5 large, 2 vCPUs, 4 gigs of memory, that will probably serve us a lot better. So we'll go ahead and configure the instance details. Again, one instance. We'll go ahead and choose our web apps. We'll choose our applications private subnet. And so, in one case, we might run a Linux-based application on one instance, like we saw earlier, and we may run Windows applications on this machine. Nothing wrong with those 2 operating systems, living side by side in the same network. And again, we don't need a public IP. In fact, if we were to enable this, it would not be able to receive one simply because we don't have a route to the internet, right? So I can choose disable. We don't need a public IP for a private application server. We can still gain remote access over our VPN connection. All right, so let's go ahead. And then, of course, you can see for Windows machines, we have the ability to join a particular domain, right? I don't have a directory, but if you have a directory set up with AWS Directory Services, then we could choose that directory. Now, in terms of shutdown behavior, it says here, what is the behavior when you perform an OS level shutdown, right? So if within Windows we say shut down, then what happens? Do we stop the machine, meaning that that it still exists, but we're no longer paying for the hourly fee, or do we just terminate it and get rid of it? So the default behavior, and what I'm going to select here is to stop. And we might also want to enable the accidental termination protection. So we'll go ahead and go to storage. You'll see here that the Windows machine comes with a 30 gig root volume, as opposed to a Linux machine came with an 8 gig root volume, right? And again, we could increase that one. We could increase the size of that one, or we could add a new volume, but we'll take a look at EBS volumes later on. Let's go ahead and add tags. And again, tags, like I've mentioned earlier, I'll probably say this again throughout the course because it's an important point, is that tags allow us to organize our environment. They allow us to attribute cost. And whether you use env or environment, whether you use dev or development, it doesn't really matter. The name of the key and the values are arbitrary. It's up to you. What matters is that you are consistent. So let's go ahead and configure the security group. We will go ahead and create, for this one, let's just create a new one, and we'll call this one Windows App, and we'll call this one Windows Application Server. And you can see here that it is defaulting to RDP on port 3389, and this would be all IP addresses, including those from the internet. Even though we don't have routing, it would be fairly trivial for someone to enable routing, and then once that was enabled, then because this rule exists, they would be able to gain remote access, right? But I want to limit that from within our current VPC. So the VPN connection that I'm using for AWS Client VPN allows us to essentially perform network address translation so that our connections appear to come from within the VPC. So I'll go ahead and put a note here, VPN connection. and I'll review and launch that. And it says not eligible for the free tier, mainly because I'm using that C5 large. And that's okay. So we've created a new security group. We have that 30 gig root volume. We have some tags. Let's go ahead and launch that one. And earlier we created a key pair called fundamentals, and I will go ahead and continue to use that one. And for Windows, the public key that AWS stores will be used to encrypt the Windows administrator password. That password will be randomly generated for us. It will be encrypted by that public key, and then we will use our private key that I have stored locally to decrypt the Windows administrator password. All right, so let's go ahead and launch that. And we can go back here, click on that, and see that it's pending. And we can take a look at information down here. We can see the availability zone that it's in, the private IP address that it has. I can go ahead and copy that. And we can see the security group rules, right? If I view those rules, it'll show me 3389 from within our VPC. We can see the AMI that we're using, Windows Server 2019. Lots of very useful information down here, and there it is. Now it's already running. All right, so let me open up RDP. So before we open RDP, I need to get the Windows password. So I can go here to Actions, Get Windows Password, and it says here, please wait 4 minutes after launching an instance. Right, so we're going to have to wait a few minutes, and we'll go ahead and fast forward until that point. Okay, so now that we've waited a few minutes, we should be able to get that password. There we go. And so now Amazon is essentially saying, hey, you associated the fundamentals key pair with this, so go ahead and essentially upload or select the private key. So I'm going to browse and go to downloads, fundamentals, choose my fundamentals key pair, and open that. And you'll see here that it is essentially grabbing the contents of that private key. And we will go ahead and say decrypt. And now the decrypt is successful. And so an important point here about Windows passwords, it says that we recommend that you change your password. If you change it, it cannot be retrieved through this tool. So changing the password within Windows does not change the password that Amazon has on file. Right? So if you change the password within the Windows instance, it will be up to you to remember it. So now we can use this information to RDP into that instance. Okay, so let me open up my RDP, and we'll go ahead and put in the IP address 10.0.1.87. You will be asked for credentials when you connect, so let's go ahead and try to connect to that. And then the password, let's go with more choices. We'll use a different account. And of course, it's because I'm on a Windows machine, it's asking if I want to use my existing Microsoft account, but I don't. I want to use a different account because this particular instance is not really associated with any kind of domain. So I'm going to go with administrator for the username and this particular password. So let's go with administrator. Copy that paste that password in, and I'll go ahead and remember that, hit OK. And then of course this happens almost every time. It says the identity can't be verified, basically because Windows is not trusting the certificate. The certificate was automatically created, and it says it's not from a trusted certifying authority, but that's okay. Right, we don't really need to worry about it. We know that this machine was created by AWS, and at least for now, we don't really need to worry about that. So yes, I want to connect. And there we go. right? Now we've logged into a Windows 2019 server. Of course, my viewport's a little bit small here in my RDP window, but that's okay. You can see we have access to the Windows desktop, and then we have access to the Start menu. And from here, we could go on to Server Manager or PowerShell, whatever else we need to do, File Explorer, and so on, right? Install whatever we need to install and configure what we need to configure, and continue to use this Windows machine.
Now let's review a demo of stopping and terminating EC2 instances.
Now, from the EC2 dashboard, we can go to Instances, and you'll see we have the Linux instance that we created earlier. We have a Windows instance that we launched earlier, and then I took the liberty of duplicating a Linux instance just so we had something to terminate. So if we were to look at the actions that we can take, we can start an instance, stop an instance, we can do stop hibernate, we can reboot, and we can terminate. So in many cases, rebooting may be, a viable option. It may be appropriate for that particular application in that particular scenario. And so you can do that right here from the console, just to simply cause that machine to reboot. And perhaps, there's an issue that could be resolved by simply rebooting the machine. Or perhaps you're doing something with a machine that just requires rebooting, like maybe installing something in Windows, and you can do that. Otherwise, rebooting simply, like, the machine doesn't go away and come back. It's there, but it's just like a machine on your desk. If you hit the reboot button, or you go to your start menu or whatever, and you just say reboot, that's essentially what it's doing. The instance doesn't go anywhere. Now, in other cases, we may decide, we don't actually need this machine anymore. So we could just say terminate. If we were to terminate, then it will say, are you sure you want to terminate? These will be gone, right? Any storage on any local volumes will be gone. The EBS volume that's attached will also be deleted. And of course, this one says it has termination protection and will not be terminated. So before I can terminate it, I have to go to instance settings, change termination protection, and say yes, disable, right? So it's a safety mechanism. I'm going to go ahead, now that I've disabled that, now I can say terminate. And it says this is an EBS-backed instance, meaning that the root volume is backed by an EBS volume, and that volume will also be deleted. Are you sure you want to do that? Yes, let's go ahead and terminate that instance. And so then it goes into a shutting down state, and then it will go into a terminated state. And so that ID we will never see again, because that instance, now that we've terminated, it's completely gone, and it's a part of our history. You'll notice down here that we have an instance that is currently in a stopped state, which means that it's not actively running like the other two are, but it still exists. It hasn't been terminated, but it's not running either. And so the volume, if you scroll down here, we should see that the root volume still exists. We still have some type of EBS root volume that's still there. So we're not paying the hourly fees for running this machine, but we are paying the monthly storage fees for that EBS root volume. And so there we go, that other one is now terminated. And so it will remain here in our console list for some time, and we can also filter out. If we wanted to filter by instant state, we could say, you know what, I don't want to worry about those that are currently terminated or stopped, just show me the ones that are running, right? And so now we have this Linux instance and the Windows instance. So let's go ahead and stop our Linux machine. Now, before we do that, I just want to point out the difference between stop and stop hibernate. Stop hibernate is currently not available simply because we need to enable that ability when we launch the instance. If you don't enable that ability at the time you launch it, then it's just not available. right? So we did not opt into that at the time we launched the instance. But what that means is, again, stopping it just means that it still exists, but we can get it back. We can restart it, right? So, but stop hibernate, the critical difference between stop and stop hibernate is that hibernate maintains the contents of memory. So when you stop it and then restart it again, whatever was in RAM gets put back. And so the machine can immediately pick up where it left off rather than having to wait for processes to start and pull information off of disk. So let's go ahead and stop it, and you'll notice here it's saying that any data on the ephemeral storage will be lost. This instance doesn't really have an ephemeral storage, but if we had storage that came with the instance, not an EBS volume, but a volume that was an intrinsic part of the instance, and any data on that would be ephemeral and would be lost. So I'll go ahead and stop that. And then it goes into a stopping state. And now any time the state ends in ing, like we're still paying for this instance. The seconds that it is within this stopping state, we're still paying for it. So again, any instance state that ends in ing, we are paying for. So as soon as it goes into a stopped state or a terminated state, then that's when we stop paying for it, right? So now it's stopped. If I go ahead and clear this filter, you'll see here that here's the instance that we just stopped. And now I am no longer paying for those hourly charges. I have a Windows machine that is still running, and I am paying those hourly charges, all right? So the great thing about stopped instances is that they're already there. You have applications are installed and configured, and they're much faster, generally much faster to become available than launching an instance from scratch. So if I wanted to get this back and pick up where my application and work left off, then all I would have to do is say instance state start and say yes, start that instance. And then it goes into a pending state. And now I start to pay those hourly charges again. And it doesn't take very long at all for that instance to go from pending to running, usually somewhere around, depending on whether it's Linux or Windows, some may take longer than others. But there we go. Just in less than a minute, it went from a stop state to a running state, right? And then, like I said earlier, if we determined that we no longer needed these and we were never going to use them again, then of course I could go back here and go to terminate. But these two particular machines we will continue to use in future demos, right? So that is how we can stop, terminate, and start instances.
Now let's talk about single versus multi-tenant instances. Within AWS, within EC2, we have the ability to achieve either a single tenant or multi-tenant environment, at least when it comes within the context of our actual instance. Keep in mind that the rack and the data center, those will always be multi-tenant. There will always be more than one customer using the actual rack and the data center. But the actual compute, we do have the ability to limit that to a single tenant environment. So in this particular diagram, we have a physical host that's running EC2 instances, right? So within AWS, we have here the physical host, right? The rack, the chassis, the motherboard, the processor being Intel Xeons, memory and network cards, and all those things that make up that physical server. And then, of course, we have the hypervisor. Now, all of these things are Amazon's responsibility. In terms of the shared responsibility model, AWS is responsible for building and supplying and maintaining and securing this physical host. When it comes to launching EC2 instances, AWS is responsible for installing the operating system on these instances, but once it's running, we as customers are responsible for maintaining that operating system. And so the default environment for these EC2 instances, if we don't choose something else, the default environment would be that each one of these may very well be a different customer, right? So we may have customer 1, over here we may have customer 2, and over here we may have customer 3, right? So the default behavior might be that we have different customers all running and essentially sharing the same underlying physical host. And for many cases, that's perfectly fine. In fact, PCI and HIPAA recently, within the last, I'm not sure exactly when, but within the last year or two, PCI and HIPAA both updated their policies to allow multi-tenant environments in many cases, right? So if you do need a single tenant environment, we have two options. If you need to be the only customer that is essentially running across this physical host, if you need to be, the only customer with these, managing any instances on this host, then we could leverage what we call dedicated instances. And dedicated instances simply means that even though we're running a virtual instance on that physical host, we are the only customer. In some other cases, we may need to actually have some type of affinity with the physical host. And so, especially for enterprises who need to migrate applications whose licenses are somehow tied to the physical host, we gain access to that as well. And so with a dedicated host, right, I'm just going to write DH here for dedicated host. With a dedicated host, AWS essentially assigns one of these physical hosts to us. And they give us the IDs, they give us the core counts, and any information we would need about that host in order to satisfy the licensing requirements for our software that we're migrating. And then later, when we go to launch EC2 instances, we can choose an affinity. If we had multiple dedicated hosts, we could choose which host we wanted that virtual machine to be launched on, right? So let's keep that in mind. For those of us who may have a need to run in a single tenant environment, within EC2, the default behavior is multi-tenant. We have the option to go to single tenant with either dedicated instances or dedicated hosts. Now let's review Amazon EC2 billing options. Within Amazon EC2, we have a number of different billing options to choose from. In this particular table, as we can see, we have the on-demand billing model. And on-demand essentially says that it follows, what we might call the MSRP. If AWS advertises a particular type of machine to cost, say, 20 cents an hour, then launching it with the on-demand billing model, we will pay the 20 cents an hour, or per second if we're using per second billing. Now, if we needed discount, if we wanted to be able to run applications and lower our cost and gain access to discounts, then we have the reserved instance billing model, and we also have spot instance billing model. And we're going to talk about those in detail here in just a moment. Now, the biggest thing that I want to draw your attention to on this table, you can always pause the video and review this, but the biggest thing that I want to draw your attention to is the availability. And I want to highlight the fact that with on-demand and with the spot market, availability is not guaranteed. And so AWS, we have to keep in mind that AWS does have an unimaginably large capacity for compute power. In fact, at one time, Gartner reported that AWS had several times the amount of compute power as the other cloud providers combined. And so I think we would have a hard time even imagining how much compute capacity AWS has, and it's constantly growing. AWS is constantly adding machines to that and growing that capacity in any particular region. But at any one time, at the time we launch an instance, in that moment, there is a finite capacity. And so it is possible that using the on-demand or the spot billing models, it is possible that we could ask for a particular type of EC2 instance, and then the API come back and say, sorry, we don't have capacity for that type machine in that availability zone. Please try again later, or try a different size machine, or try a different availability zone, right? So keep that in mind. And of course, I've been using AWS for almost 10 years, and have only ever seen that happen maybe 4 times. So it is rare, but it is possible. Now with reserved instances, there may or may not be an upfront payment. It all depends on how we want to approach it. Generally, the more we pay up front, the more discount we get. And so we can choose to purchase a reserved instance by making no upfront payment. That means that there's no capital expenditure. We get to keep more money in our pocket, but we are getting the least amount of discount, right? So the more we pay up front, the more discount we get. We could choose to pay a little bit. We could choose to make a full upfront payment, right? So by making a full upfront payment, what we are essentially doing is saying that for the term, they're available in either a 1 or a 3-year term. For that term, if I make a full upfront payment, I am paying for every hour of every month for that 1 or 3-year term. And in doing so, and making a full payment up front, I get the most discount on that particular instance. And so the thing to keep in mind with a reserved instance is that, and this may be a little bit challenging to understand at first, but it will become clear as you actually get in there and start using it. With reserved instances, it's one thing to purchase a reserved instance, and it's another thing to actually launch an instance, right? Purchasing a reserved instance and launching an instance are 2 completely different things. Just because you purchased a reserved instance doesn't mean you launched one. And just because you launch one doesn't mean it qualifies for the discount of the reserved instance, right? And so if you were to purchase a reserved instance with no upfront payment or a partial upfront payment, then you are essentially committing to paying every hour of every month, even if you don't actually launch an instance, right? You're going to pay that fee regardless of how many instances you're running. And so when you purchase a reserved instance, and then what that does is create a billing reconciliation model. It creates a line in the billing that says you qualify for a discount on any instances that you run, right? And then when you launch an instance, they have to match, right? So if you purchase a reserved instance for a particular type of machine in a particular availability zone, if you launch that same thing, that same size machine in that same AZ, the billing reconciliation will apply to the instance that you launch. And so it's possible to gain a guaranteed availability. This is one of the options. You don't have to. If when you purchase the reserved instance, if we choose the availability zone, then AWS will reserve availability for us. And that's partly why we call it a reserved instance, because capacity is being reserved. It means that when we actually launch the instance, we have a guarantee that we will get one. And of course, the benefit of reserved instances are that we gain a significant discount versus the on-demand price. So reserved instances are generally best for constant applications or databases. When you look at the application that's running, and if you determine that that application it will be running for more than 55 to 60% of the month, then that's generally where the threshold is. Beyond 55 to 60% of the month is when you would see a savings by using reserved instances as opposed to using on-demand. The other billing model that we have would be spot instances. Now, with the spot, what we call the spot market, the fee is based on supply and demand. I mentioned earlier that AWS has an enormous, unimaginable capacity for generally any type of machine in any given availability zone. And so what AWS does is they look at the supply that they have, the capacity that they have for a particular size machine, and the actual demand for that machine. And the spot market is essentially a way of selling unused capacity, or giving us the ability to gain those resources at a lower price. And so we can see with the spot market our hourly fees be an absolute fraction of the on-demand price. We can save upwards of 80, maybe even 90% as opposed to on-demand. And so the way that we approach the spot market is that when we launch an EC2 instance and we say, I want to use a spot instance, keep in mind that there's no functional difference between on-demand, reserved, and spot. These are all EC2 instances. There's no functional difference between them. The only difference is how we actually pay for them, how we are charged, right? And so when we launch an EC2 instance, and if we want to gain access to the spot market discounts, we choose that we want it as a spot instance, and we specify our maximum spend. How much are we willing to spend on that particular instance? Now, if the current market rate, according to supply and demand, if the current market rate rises above our maximum spend, then the instance can be terminated by AWS and essentially given to someone who's willing to spend more money. Now, of course, we do get a 2-minute warning, and that's made available to the instance. Our application can poll for that and query the instance metadata service looking for that warning. And when it sees that warning, it can record some kind of a checkpoint, save its work. That way it can come back and resume that work later when the market price lowers. And so the spot market is generally best for temporary work that can be interrupted, right? Batch processing, testing and experimentation, billing and sales reports, right? Any kind of work that can be done quickly and work that is easy to essentially checkpoint and save and come back to later. The really important thing about the spot instances, and I think I've already mentioned this, is that apps need to tolerate interruption. If your application cannot tolerate interruption whatsoever, then the spot market is the wrong choice. We would definitely want to look to either on-demand or reserved, right? So let's keep those billing models in mind as we move forward using EC2. And if we want to create, an environment that is cost-effective, it's very important that we be aware of the billing models that are available, on-demand, reserved, and spot, and determine which one is most appropriate for that particular type of work that we're doing. Now let's review an introduction to AWS Lambda. With AWS Lambda, we gain access to serverless computing. Now, of course, serverless is a hot topic these days, and let's keep in mind that there's much more to serverless than just Lambda. Lambda is just one small part of the serverless sort of movement, and Lambda would give us what we might call functions as a service. And so by serverless, what we mean is that even though we know somewhere out there in an AWS data center, we know that there's a server running this code, from our perspective as a customer, as an organization, there is no server for us to manage. We're just writing code and allowing AWS to essentially execute that code. And so Lambda is great for all kinds of different use cases. We could run scheduled tasks, microservices, event handlers, all kinds of different things we can run on AWS Lambda. Anything that can be decomposed into small targeted functions could be written to use Lambda. Now, one of the things that I'd like to point out is that I see a lot of folks coming to Lambda or coming to AWS looking to use Lambda, but still in a mindset of like traditional enterprise computing where you're creating these very large applications, right? So we're not going to take, say, this large enterprise Java application comprised of thousands of functions across hundreds of classes and objects and squeeze that into Lambda. That's not what we're talking about. With Lambda, we create functions, and we call them functions because that's what they are. Just like we might write a piece of software is a collection of functions or classes and objects, the same is true with Lambda. So we might decompose those enterprise applications into various functions, and then our software becomes a collection of functions. And so with Lambda, we pay for compute time per 100 milliseconds. Now, of course, the more memory we use, the more we pay. So there is a relationship between the amount of memory that we use and the length of time that an application runs for, right? So we can create functions in several different ways. We can use the inline editor, which is available to us in the AWS console. And by using the inline editor, we have a pretty quick and easy way of writing out a particular function. But probably the more common way is to upload a zip file. And so our function needs, if our function needs, say, other dependencies, other packages, then those need to be included with our code. And the only way to do that is by uploading a zip file. And so with Lambda, once we create a function, we then invoke those functions. And we can invoke them programmatically or even manually through the CLI tools or the SDK, or perhaps the most common way and perhaps one of the most powerful ways is to leverage events. Events can come from all kinds of different places within AWS. A classic example of an event might be to leverage Amazon S3 event notifications. So with S3, we have a bucket that we can store objects in, and we'll talk more about S3 later on. But as we upload things to that bucket, that would be an event. As we delete something, that would be an event. And so whatever is happening in that bucket, those events can each be used to trigger Lambda functions in response. And the Lambda function could then retrieve that data from S3 and go on to perform some type of processing. And once these functions are invoked and they start to execute, AWS handles all of the underlying infrastructure. Again, we know that there's a server somewhere that is actually executing, the CPU cycles responsible for making our function work, but we don't have to manage it. AWS manages that actual underlying machines. AWS handles the deployment of our code. And so getting our code to that machine in order to be executed, Amazon handles that. And Amazon handles the scaling. And so we could launch, or we could invoke one function one time. We could invoke two functions, each of them thousands of times, right? So we could have the default soft limit for Lambda is 1,000 concurrent executions, right? And if you were to lift that to, say, 2,000 or 3,000 or 4,000 concurrent executions, AWS will handle and do all that's necessary to handle the scaling to make that happen. And so here in this particular example, we have a piece of Python code, a short piece of Python code that we might write to be, let's say, a hello world or a simple example of a Lambda function. And within there, I just wanted to point out that within that code, you can see that we are defining a handler, right? That's a function that we need to tell the Lambda service the name of that handler function. And that handler receives a couple of different arguments, in this case, event and context. And that's how our Lambda function can receive data in order to do its processing and how using the context parameter is how we can communicate back to the Lambda service that our function was either successful or our function failed. And so we take our code and we give our code to the Lambda service, and in doing so we specify the runtime, be it Python, Node.js, Java, or C#. We specify the memory that we might need, anywhere from 128 megs all the way up to 3 gigs. And we also specify the execution timeout, anywhere from a few seconds all the way up to 300 seconds or 5 minutes. So that's another thing to keep in mind, that Lambda does have those limitations, up to 3 gigs of memory, up to 5 minutes of execution time. So if your application needs more memory or more time, then Lambda is probably not an option. And so once we have our code, we have our runtime, memory limit, and execution timeout set, that gives us a Lambda function. And we can then invoke that Lambda function. Again, either programmatically, manually, or through events. And we can invoke that function pretty much as many times as we want. And Amazon, every time it's invoked, Amazon handles the deployment of our code, the execution of the code, and the collection of logs. And we're going to talk about log collection later on. But in this scenario with AWS Lambda, the beautiful thing is that all we have to do is write code. Give the code to AWS, configure a few things, and then allow AWS to handle the rest. Now let's take a look at a demo of writing a hello world in AWS Lambda.
From the AWS Management Console dashboard, we can go to Lambda, of course, by searching here. We'll go ahead and take a look at the Lambda dashboard. You can see if we go to the dashboard, it gives us a summary of what's happening within Lambda in this particular account in this region. So currently in my account, I only have one function so far. We can also see account level metrics across all Lambda functions in that particular region. You know, errors, invocations, total duration, concurrent executions, all of those kinds of things. And then, of course, we have access to all of our functions here. You can see I only have one, and we can go ahead and from here we can create a function. We could also create a function from the dashboard as well. So if we create a function here in the management console, then we're kind of limited, because if we're authoring from scratch right here in the console, then we're essentially going to be typing code in the console, which means that we won't really be able to include any dependencies. So if we need dependencies, other libraries, so for example, if you're writing in Node.js and you wanted to include NPM modules, then you would have to do all of that locally, wrap all of that up in a zip file, and then upload the zip file. So here we're just going to keep it simple and write a very simple hello world. We'll call that. And I'm going to use the Python 2.7. And of course you can see that it supports quite a few different languages, .NET, Go, Java, different runtimes of Node.js, different runtimes of Python, Ruby, and so on. You can also use a custom runtime. So we'll go ahead and choose Python. And then, of course, now that we have the runtime selected, we also need the role to be selected. So we're going to choose an existing role. We could also create a new role from a template or create a custom role, but I already have one. And I have one here called Hello World Lambda. So let me show you that real quick. Before we actually get to the function, let me show you that role, because it is really important to understand that, you know, what this says here is that Lambda must be able to assume this role, and the role must have Amazon CloudWatch Logs permissions. So we are using roles to delegate permissions to the Lambda service so that this function is capable of communicating with other AWS resources essentially on our behalf. So I'm going to open IAM here in a new tab, and I'll go to roles. I just want to show you this real quick. It's already created. Let me search for my Hello World role. There it is. And you'll just see here that I have this role, which is specifically for Lambda. If we look at what we call the trust relationship, you'll see that this one is for the Lambda service. So we're saying that the Lambda service is able to assume this role, not any other service, not any other account, but specifically the Lambda service. And so the permissions that we've granted would be, one, we have a policy called AWS Lambda S3, where we're essentially allowing this particular Lambda function to essentially download anything from S3. Now, you'll notice that what's lacking here is the ability to list objects in the bucket. So the function would not be able to explore S3 and just go and find things to download. The function would have to know the URL to begin with. And then down here, we have the Lambda basic execution. Lambda basic execution role essentially allows this function to create a log group within CloudWatch logs, create log streams, and then put log events. And you can see here it's specifically for this particular function, Hello World. So now that we have the role chosen and that particular role has the right permissions, now we can go ahead and create the function. And we'll go ahead and we're going to skip over the designer for now. Let's go down to function code. And again, right here it's saying edit code inline. And again, the runtime is Python 2.7. And now before we actually make any changes to this, let's just first take a look at what they've given us. You can see that they've already given us a bit of a hello world. But let's just take a minute to understand what's going on here. You'll see that whether or not you know Python, it's pretty easy to see that we are essentially defining a function here. So all Lambda functions, regardless of the language that you write it in, have to have a handler. And you'll see here that we are calling this one Lambda function dot Lambda handler. So this right here, Lambda function py, you'll notice that this is essentially the name of the file. So it's essentially name of the file dot Lambda handler, and you'll see up here Lambda handler is the name of this function, right? So we're telling the Python, or excuse me, we're informing the Lambda service that when our function is to be executed, it is to execute this particular function. Now we could, if we wanted to, we could define other functions up here, right? That would essentially be private. That would, we could define my function here and some other function down below, and all of those would be essentially included in here. But we're saying out of all of the functions that might be defined, this is the one that needs to be executed when our Lambda function is invoked. And then, of course, that particular handler will always receive two objects, the event object. And remember that Lambda can be triggered by events from a number of different places, from API Gateway, from S3, DynamoDB, Simple Queue Service, Kinesis. So, for example, if you were to leverage S3 event notifications and you upload a file to S3, once that object is written and that upload has finished, then S3 will send an event notification to Lambda. And all of the information about that event, where it came from, any other pertinent metadata will be included in that event object. And then the context object is essentially it can be used to indicate a success or a failure. You can see here that we don't necessarily have to do that. We can just return, but you can gain more control over the execution of this function by leveraging the context object. So before we actually run this, I just want to make one small change. I'm going to import one more thing, the print function. And here we're going to say print loading so that we can we can see these things in the logs. So remember that Lambda will always write logs to CloudWatch logs, and anything that we print to standard out or to the console will be captured by CloudWatch logs. And so we can leave ourselves some debugging information by essentially printing here. All of that will be captured by CloudWatch logs. We could echo this particular event here, right? We could do something like this. We could say receive that event and then essentially use the JSON library to dump that out so that we can see the contents of that event object in our logs, right? And so we'll go ahead. We can also, down here, we can also assign environment variables. And then, of course, just like most resources, we can set tags for that. And then if we needed to change the role, we could down here. If we wanted to update the role to something else, then we could do that there. We can also define how much memory this needs. So also, it's worth noting that your function is allocated CPU proportional to the memory. So if your function needs more CPU, then you have to give it more memory. The two of them are not separated. There is an intrinsic relationship between the amount of memory you use and the CPU that you get, right? So remember that the more memory you use and the more time you use, the more you pay. So it's important, like not every function needs 3 gigs worth of memory, right? And not every function needs 5 minutes worth of a timeout, right? So if you just end up doing those kinds of things by default, you could very significantly end up artificially inflating your bill. And I've seen that happen with clients I've worked with who had kind of they just didn't realize what was going on, and they had a habit of just always setting the timeout to 5 minutes, but then not forcing their function to exit when it could earlier. And so it meant that their functions were just always running for 5 minutes, even though the processing may have completed in 1 second. And so by doing that, they were spending a lot more money than they needed to, right? So really take time to understand, we may not need 5 minutes worth of execution. We may only need 3 seconds, or maybe we need 10, right? Now, it doesn't mean that you're going to be charged for 10 seconds. You are charged for what actually runs. So it's important that our function, right, if we go back up to our function, it's important that our function either return or call the context fail as soon as it can. And so here, a hello world certainly doesn't need 3 gigs worth of memory. We'll go all the way down. So 128 megs is still more than enough, but it's the lowest limit. We could give Lambda functions access to our VPC, right? If we wanted Lambda to communicate with EC2 instances in our VPC, we could do that as well, and we could choose a subnet, such as our application servers, right? We could do that if we wanted to, and we could give it a security group. Well, I'll just go ahead and close all of that for now, right? So that can be really helpful when you want Lambda to communicate with something, perhaps an application server or a load balancer or a relational database from the RDS service. And then, of course, we could also say, we want to reserve a certain amount of concurrency for this function. So remember that right here, what this is showing is that I have an account limit of 1,000 concurrent executions of functions, and that's across all functions. And so if I felt like this particular function needed more concurrency than other functions, then I could reserve that and say, well, I want to reserve a certain amount of concurrency, right? And then you can always lift, this is a soft limit, you can lift this number by submitting a ticket to Amazon support, right? So, if you have a very busy application, you may very well need 2,000 or maybe even 10,000 concurrent executions, right? Amazon does these kind of soft limits to limit resource consumption, all right? So let's go ahead and save that. And then now that it's saved, we can actually go ahead and test that, and we can select a test event. So remember that the event will come from whatever is triggering this function. So when you're testing, you need a test event. So I can go ahead and configure one And I'm just going to go ahead here and get rid of all of these things and say message hello. And I'll call that one hello. So we've created this new test event, and we can use this to mock other events. So if we wanted to test against, like an S3 notification or a DynamoDB notification, then we can take, one of those notifications, we can generate one and then take that data and put it in here as something to continually test against, right? So I'll go ahead and create that. And now we have, if we go back up here to test, we can use the hello test event to say test, and of course it failed. So let's see, this happens, right? This is, we're not always perfect. So again, it's saying it has a syntax error, and then now we get access to the log output, syntax error on line 2. So let's come back down here. I think I might need to put this up here. Let me try that. All right, so we can save that again very quickly and easily. We can make a change to our function. We can save it, and we could also, you'll notice here that it's giving us a link to the logs, right? We could also go to CloudWatch logs. We'll come back to that. All right, so let's go ahead and we'll close this and try that again. And there we go. It said result succeeded. So it was just a matter of I ended up putting that from in the wrong place. And again, that happens. You just learn from the error and move on. So this is what was returned. And then down here, you can see here's where we printed our loading, and here's where we said received event message hello. So this is our test event. And then it also tells us in the logs how long the function actually ran for. So it only ran for 0.52 milliseconds, but we were billed, right? It says here billed for 100 milliseconds using 128 megs worth of memory. So again, the greater these two numbers combined, the more we pay. So if we wanted to take a look at the logs, we could click here, and that would take us directly to CloudWatch logs. And then you can see this is the streams for Hello World. And you'll see it's ordered here by last event time. So if we were to take a look, let's go back to this one here. I think we'll see the error. Nope, nothing in that one. Let's go back. Maybe it was this one here. That was something else. Let's take a look here. There we go. So here is the same information that we saw earlier, where it's saying, loading, received event, and so on. All right, so we'll go back to Lambda, and we can close that, and then of course we could say, let's go back to our functions, and there we go. We've in just a few minutes we've created a hello world, and we created a by choosing our runtime being Python 2.7. We specified memory and a timeout. We added some code. And we created a test object, a test event, and then we tested the code and verified that the code was working through the logs that the Lambda service gave us, right? So that's how we can write functions in AWS Lambda.
Now let's review another use case of image processing with AWS Lambda.
Okay, so we have our users, and those users are leveraging devices like phones and tablets and laptops and whatever else. And we want to allow them to upload images. And so we can leverage S3, and we're going to talk more about S3 later on, but we can leverage the simple storage service to allow our users to upload content directly. We don't need our own backend API. We can bypass that by allowing our users to upload their images or video, whatever file it happens to be, directly to S3. And we can do that, if you remember, we talked back in lesson 2 about federation and how we can leverage temporary keys, temporary credentials, by federating our web and mobile application users and giving them temporary credentials, then we can very easily allow them to upload directly to S3 without interfering with any other user's data. And then once that image has finished uploading, we can then use S3 events or event notifications to trigger Lambda functions directly. And then that Lambda function could then execute and, perform thumbnailing, watermarking, whatever kind of processing it's doing. And of course, all of the invocations and, continue the execution, the deployment of that function is fully managed by the Lambda service. All of the scaling and infrastructure necessary to make it happen is totally handled by AWS. Now, the thing to keep in mind here is that within AWS Lambda, we do have a concurrency limit. There are limits around the number of functions that are allowed to execute concurrently. And so one of the issues with having S3 trigger Lambda directly is that it would be possible for the number of incoming images to overwhelm that limit. And so we don't have to do that. We have options, right? We don't have to have S3 trigger Lambda directly. We could leverage queues so that the images are going into the queue, and if there comes a time when there are more images coming in than what it can be supported by our concurrency limits, then those messages would just stack up in the queue. And of course, then as the events come into the queue, we would then call them messages, and those messages could then trigger the Lambda function. And then, of course, that Lambda function could store its result in another S3 bucket. And now the benefit of using queues is that it would allow us to by leveraging multiple queues, we could leverage multiple functions for doing different kinds of processing, right? So we might have one function that's doing the actual processing, thumbnailing and watermarking, transcoding, and we might have another function that's dedicated to doing metadata extraction, just pulling metadata out, storing it somewhere. Perhaps another function that's dedicated to doing some kind of analysis, like maybe all it does, it could be something so super simple as, taking the size of that file and then adding that to the user's current period's worth of allocated bandwidth or allocated storage, right? And so the thing about these Lambda functions is that they are precise, they are targeted and small. We're not wrapping up all the functionality that we will ever think of in one function. We call them functions for a reason, because they are targeted. They do one thing. And if you need to do another thing, you create another function. And then of course, those functions could store their results in some kind of data store, and perhaps you use several different data stores. You could store certain types of information in a relational database, other information in a NoSQL or a search engine like Elasticsearch. And we have a lot of options in regards to data stores that we will talk about later, like the relational database service, DynamoDB, Elasticsearch, Elasticache. So plenty of options to choose from here in order to send this information and store some kind of a result. And then, of course, just like our incoming messages used events to trigger Lambda functions, our processed images bucket could do the same thing. So as the final result is stored here, that could then trigger another Lambda function that's dedicated to sending notifications, letting the user know that their image has been fully processed. And of course, we have options in regards to this notification service. We have that we will talk more about later as well. We have the simple notification service. We have Pinpoint as managed services to help us with the logic and the tracking around did the user see that notification? Did they respond to it? And then, of course, our users could view those processed images directly from S3. They don't need to go through our own, back-end services that might be running on EC2, right? Our users can pull them directly from S3. And using temporary credentials, again, we could allow this mobile application or web application to read directly from a data store, depending on what it is. DynamoDB, for example, makes that very easy. And so with an architecture like this, we could very easily create asynchronous event-driven architectures and allow the user to gain real-time notifications into that process and real-time insight into the actual data as it's being processed by viewing, results in the data stores from the data store. And so again, this particular use case is specific to image processing, but you could replace image with just about anything. We could use this to process, large CSV files, and that those CSV files could be related to real estate. They could be related to some kind of financial data. And as they come in, the same pattern applies. They get processed in different ways by different functions, and their results get stored in different services. And we will continue to explore these things, such as queues with the simple queue service, notifications, and data stores as the course continues.
Now let's review an introduction to Amazon Elastic Container Service, or ECS. With ECS, we have the ability to manage containers. So ECS is ultimately a container management service, or essentially a scheduler. And it does support Docker containers, and it's basically analogous to Kubernetes. If you are already familiar with containers, if you've done any deployments with containers, then you're probably familiar with schedulers like Kubernetes or Docker Swarm or Mesos. And so Elastic Container Service is essentially the same thing. It's fulfilling that same need in that we have a collection of hosts, perhaps EC2 instances, and we want to deploy containers to that cluster of hosts. And so we need something that can track the state of those instances, of those hosts, track the available resources such as CPU and memory and disk I/O or network I/O, and help us keep track of what containers are running on what instances, and help us to handle all of the low-level minutia of getting a container running on a particular instance within that cluster. So that's what a scheduler does. That's what ECS does. And so we can use this to essentially schedule or ensure that containers are running for perhaps long-running applications. So if you are deploying microservices for an API, services that need to run for a long period of time, listening for incoming connections, those are well suited for containers, as are other applications like batch jobs, right? So you can have one cluster of instances that run all kinds of different applications side by side. And the isolation between those processes is achieved through containers. So again, long-running applications for APIs, batch jobs, all kinds of different things we can use containers for. ECS does integrate very well with Elastic Load Balancing, with Elastic Block Store, with Amazon VPC, and with the Identity and Access Management Service. And so I suppose that would be the nice thing, the great thing about ECS, as opposed to running Docker Swarm or Kubernetes on EC2, is that we have a native inherent integration with other native Amazon services. Now, when we take a look at this diagram, a few things I want to point out here would be, one, you'll notice that we have here an auto-scaled fleet of EC2 instances. And of course, we will talk about auto-scaling in more detail later on. But for now, the idea here is that if any one of these instances were to fail for whatever reason, become unhealthy or unusable, then auto-scaling could simply replace it. And if we needed to add more machines, then we could do that with auto-scaling as well. Now up here we have the cluster, and a cluster in this regard is within ECS a logical grouping of EC2 instances or hosts that allow us to deploy a grouping of services. So A cluster is a collection of EC2 instances that are being managed, and it is also a collection of services that we deploy to that cluster. And so we create the cluster as its own sort of resource within ECS, and then as these EC2 instances come to life, using custom Amazon machine images, using user data bootstrapping scripts, these instances can then communicate to the ECS service in order to join the cluster and then be managed by as essentially a single pool of resources, right? And so now that all of these machines are essentially a part of the same cluster, we can now use ECS to manage those machines and deploy containers to those machines. So taking a closer look at, or perhaps a different look at this diagram, you can see here that we have our cluster, and that cluster is essentially managing, in this example, a couple of EC2 instances. And within those instances, we have containers that are running. Right? So each one of these is a container. And those containers are deployed by the ECS service. The ECS service is able to create those containers by pulling container images from ECR, the Elastic Container Registry. So very much like virtual machines, containers are also based on an image. The primary difference being that a container image does not need the operating system. All of these containers that are running on a host, they all share the same underlying operating system. And so the benefit to containers is that if we are deploying containers as our deployment artifact, then the container image, in many cases, I've seen many container images be far less than 100 meg, whereas virtual machine images could be upwards of 8 gigs or more, right? So that's a pretty good difference, a very notable difference between the size of the actual artifact. And so by having small artifacts, it means that they can upload faster, they can download faster, and they can deploy faster. So again, we have our registry where we would publish our container images. We have the ECS service, and so in our deployments, we essentially tell ECS, hey, I want this particular image to be used for this particular service. So ECS will pull the image from the container registry. ECS will then instruct this cluster. It will choose a particular instance to launch that container on. Now, when we launch what we call a service, we may say that we want a certain number of containers to be replicated, meaning that we're going to take the same image and replicate it some number of times across a different number of containers for the sake of fault tolerance and high availability. If one container fails, we still have another 2 or 3 or however many containers we need. And so, again, ECS is responsible for ensuring tracking the state of the EC2 instances that are within this cluster and knowing how much CPU and memory and disk and network I/O are available, so that when we go to deploy more containers, it knows where those containers can be placed, where the resource requirements can be fulfilled. Another thing that we can do with ECS that's really powerful, especially for microservices, is that if we wanted to create, microservices and offer, different services at different URLs, we can leverage the application load balancer. So here we have a form of the Elastic Load Balancer called the application load balancer. And what we can do with this is both hostname and path-based routing. We could say if we had a series of microservices, we might say that perhaps this container, and this container belong to a particular service, and that a certain URL should be routed to those particular containers like so, in order to satisfy the routing for a particular service. And so we could group containers, essentially container replicas for a particular service. We can group them as what we call targets within target groups. And so again, we can use path-based routing from the application load balancer to get us to the containers for a particular service. And so in this example, we may have 3 containers running for a microservice available through the load balancer. We may have several other containers doing some type of background processing or batch processing. Either way, the deployment, the underlying, all of the steps it takes to get that container running on those instances is all managed by ECS. And we will take a closer look at that and how that all works in an upcoming lesson. Now let's review an introduction to Amazon ECS for Kubernetes, or EKS. With Amazon ECS for Kubernetes, we gain a fully managed control plane for Kubernetes. And so AWS will create and manage the master nodes that make up that control plane for Kubernetes. And so keep in mind that with Kubernetes, you have all of the Kubernetes specific software, and you also have etcd. So the Kubernetes control plane relies on etcd, which is a distributed key value store. And so it's really important to maintain high availability of that service and durability in the data, because the values in etcd are back to disk. And so while AWS creates and manages those master nodes, ensuring constant durability and high availability for the Kubernetes control plane, the customer, will manage the worker nodes. And we will take a look at a diagram on this here in just a moment. And so ECS for Kubernetes is certified to be Kubernetes conformant. It is compatible with applications designed for standard Kubernetes. It essentially is standard Kubernetes, except that AWS is managing the master nodes for us. So let's take a look here at a diagram showing the architecture. So what you can notice here is that as a customer, we will have our own VPC, right? So we would create our own VPC, and in that VPC, we are then responsible for the worker nodes. AWS, Amazon is creating another VPC specifically for the master nodes, right? So AWS is managing those master nodes. We know that they are there, but they are they're pretty well opaque to us. We don't really get to see exactly what's going on behind the scenes. We're just trusting that AWS is managing the Kubernetes worker nodes in a highly available, fault-tolerant, secure, and durable way. And so as far as the worker nodes go, these instances here, these are up to us to launch and put in place. AWS does provide a machine image that includes the Kubernetes software and allows us to connect the worker nodes to the master nodes. And as you can see here, these worker nodes will all essentially communicate with the master nodes once they are up and running. But it is our responsibility to ensure that we're using the right machine image for the worker nodes, that we are using the right security groups. And then, of course, we do have complete freedom to use just about any EC2 instance we feel is appropriate. We could use C5 larges, we could use M5 8 extra larges, we could use R5 machines. We could put a blend of different machines in as worker nodes if our applications have the ability to run on different types of machines, right? So what we do with the worker nodes is totally up to us, but they are our responsibility. And then, of course, as we deploy containers to Kubernetes, those containers will be launched and run here on the worker nodes. And then our users, if we are running any kind of application that's accessible over the internet, such as APIs or WebSocket applications, then of course our users will come in through the internet gateway, through a load balancer, and then the load balancer could load balance to the containers running on these worker nodes. Right, so that's EKS, Elastic Container Service for Kubernetes, giving us a fully managed Kubernetes control plane. So now let's review a use case of running container-based microservices.
Okay, so we have in a particular region here, in this particular example, we're using US East 2 in the Ohio region, and we have a couple of availability zones, and we will be leveraging the Amazon Elastic Container Service. And so the first thing that we do is we go to the ECS service and we create a cluster. Within ECS, a cluster is really a logical grouping of applications that will be deployed together, that will run alongside one another. And you can have multiple clusters. Now, it is possible to use Fargate, which is a service that allows us to deploy containers to that cluster without managing any EC2 instances whatsoever. And for many applications, that might be perfectly fine. There are times, though, when you want access to technologies that are only available on EC2 instances, such as high-performing CPUs, GPUs, FPGAs, or high-performance networking, or more than 30 gigs worth of memory. And so if we decided to run EC2 instances within the cluster, then we could deploy those, and you'll see here that we're deploying those across multiple availability zones for the sake of high availability, fault tolerance, being resilient to the loss of an availability zone. And now these instances, we can configure these instances to essentially join this cluster, and now all of these instances, however many we have, whether it's 2 or 20 or 200, they are essentially through the cluster, they become a single pool of resources. And we don't need to worry about, all of the fine logic and steps necessary to actually get a container running on an individual instance. All of that is abstracted away by the ECS service, which is essentially a scheduler. And so we deploy to the cluster. ECS handles the fine details of determining which instance is currently capable of supporting the resources that we need for that container, be it CPU, memory, volumes, and so on. And then, of course, if we're running EC2 instances, then we would probably want to wrap those in an auto-scaling group. We will talk much more about auto-scaling later on in Lesson 7. But for now, suffice it to say that autoscaling is, in the least, a way for us to maintain a fixed number of machines. We can do much more with it, but in this particular scenario, we may say, well, we only want 2 EC2 instances in this cluster, and if one were to fail, then autoscaling could terminate it and then replace it with a new one. And then, of course, as we deploy containers to the cluster, the scheduler will then determine which instance those containers run on, right? So our containers will be deployed to these instances. And so we would go to ECS and we would configure a service or a task and say, hey, we want this container to be running, and ECS will then do all of the underlying logic in order to deploy that to a particular instance, right? So we as developers, we worry about deploying to the cluster. ECS handles what it takes to actually get that container running on an instance. In this particular scenario, as it looks right now, we have one container running. So we have one instance of one application. And there are plenty of times when that's appropriate. You may have a background task that does something very quickly, and then it goes away. But you may have, in other situations, you may want to run replicas of that application. So you're running the same exact application in 2 different containers, And so by doing that, we can configure ECS to make that happen and say, well, hey, I want 2 or 4 or 8 containers or replicas of this application running. ECS is also aware of availability zones, and so it will make its best attempt to maintain a balance of those containers across those availability zones, while also being aware of the capabilities and the available resources of our EC2 instances. And so again, this could be 2 replicas of an application doing background processing, or it could be 2 replicas of a web API, some kind of a web application that's meant to run for a long period of time, listening for requests and handling web requests. And so in that regard, if these were part of some kind of an API, a web application, then we would probably want to put them behind a load balancer so that we can point our users to the load balancer, and then it would distribute traffic among those backend containers. We will talk much more about load balancing later on as well. And then, of course, we need a way for the load balancer to be aware of these containers. And so by leveraging load balancing in combination with ECS, we can configure the Elastic Container Service to coordinate not only the placement of containers, but also the registering of those containers with the load balancer. So ECS will tell the load balancer, hey, you have these 2 containers available on this port and for this particular application. And then once that registration has happened, then those containers become what we would call targets for the load balancer. Requests coming in could then be distributed among those 2 containers. And of course, we could keep going and add other applications that are also registered with the load balancer. So we can run just about any number of applications in this same cluster. And so we have multiple replicas of multiple applications all running side by side within the same cluster. And then, of course, at some point we may experience a failure, some kind of an error within our application. It could be a race condition that caused the application to just fail and the process to exit. It could be the fact that the process used more memory than what we allocated, and then that process was killed. And so either way, regardless of how, if our application were to exit, then the container essentially goes away. And now we have a discrepancy here. We have configured, in this case, we've configured the Elastic Container Service to maintain, say, 2 containers, but now we only have 1. So ECS will say, all right, let's replace that one with a new one. It will notice that one has failed and then replace it with a new one. And so ECS is maintaining the containers. If one fails, it replaces it. We can also scale the number of containers by updating the service within ECS. And then auto-scaling is doing that same thing for our EC2 instances. And then, of course, as far as EC2 instances go, they don't have to be the same instances. They could be a blend of several different types of instances. You could have a cluster that's comprised of a C5 large, an M5 extra large, an R5 triple extra large, right? So you don't necessarily have to have the same kind of EC2 instances, and there are a lot of advantages to that, and we can talk more about billing later on, but the effects on billing could be that you can always get the cheapest instance, and we'll talk more about ways of saving money on EC2 later on as well. And then, of course, we have developers that are writing code, and we need to get that code deployed as a container into this environment. And so that would probably first start with some kind of version control system. We will talk more about code commit later on as an Amazon service that solves this. And then the pushing to this version control, or the merging of a pull request, that action could then trigger a CI/CD pipeline. And we have a lot of options here. We could use Jenkins. We could use third-party subscription services like Travis CI, Circle CI, Bamboo. The list goes on. We also have an Amazon native service called Code Pipeline, which we will talk in detail about later on as well. And then, of course, so the end result of that CI/CD pipeline would be deploying a container into this cluster. And so essentially the CI/CD pipeline goes to ECS and updates an existing service with a new image. So we're saying ECS, hey, here's a new image. Replace the existing containers with new containers that are running my new version based on this new image. And so the benefit of containers is that we can get a very fast deployments. Another benefit is that we could even run, not only can we run multiple applications side by side, we can run multiple versions of the same application side by side. So if we wanted to support older browsers or older clients for a longer period of time, then we could very easily run multiple versions of the same application. And then, of course, our CI/CD pipeline is generating events. At life cycles along the way, things are happening. Things are passing, things are failing, right? We might have tests that are running, and they pass, they fail. We have builds that are happening, and they pass and they fail. And we have deployments, and they fail or they succeed. And so we want to know exactly what's happening along the way. And the same with ECS. Once the CI/CD pipeline passes and then ECS attempts to deploy that process could fail or it could succeed. And so there are all these lifecycle events that are happening within these two services, and we would want some kind of a way of getting those notifications back to our developer. So if our tests failed, get that information back to the developer so they can write their code, get it back into version control, and push it through the process again. If tests pass but the build failed, notify the developer so they can start it all over again. And then, of course, if the CI/CD pipeline was a success, it would also be possible for ECS to fail. But either way, by piping in all of these notifications, then we enable our developers to see in pretty much real time exactly what's happening along the way. And so as far as these notifications go, we will talk more later about the simple notification service as a way of collecting these kinds of notifications from different Amazon services and then getting them to a single or even multiple endpoints, whether it be a developer or an HTTP endpoint that might be running in a third party or on premises. And so we have a lot of options in running container-based microservices within AWS. We don't have to use ECS. We could use, ultimately ECS is a scheduler, and there are other schedulers. We could run Apache Mesos on EC2. We could run Docker Swarm on EC2 or Kubernetes on EC2. What I like about Amazon ECS is that it's a fully managed service. But then we also have ECS for Kubernetes, which is also a fully managed service, right? So you have a lot of options. If you would prefer Kubernetes as opposed to ECS, then we can very easily do that as well. And this process is basically the same. Not a whole lot would change. The only thing that would change would be essentially the syntax by which we inform ECS versus EKS on how to do what we're trying to do, right? And so I've been in situations, in production scenarios, where we could go from developer pushing, merging a pull request, testing, building, publishing the Docker image to a repo, and then deploying a container into production. I've seen that whole thing take less than 10 minutes. And it's really a beautiful thing when you get to a point like this where you can deploy to production at will, at any time, and get those notifications in real time, allowing your developers to iterate very quickly. So for anyone looking to deploy microservices within AWS, and especially if you're looking at containers, I would highly encourage you to look at all of the options around containers such as ECS and ECS for Kubernetes.
Now let's talk about VMware Cloud on AWS. With VMware Cloud on AWS, we have the ability to access an integrated solution developed by AWS and VMware. So AWS and VMware got together and said, hey, there's some synergy here. There's a lot of people still using VMware, a lot of people that still want to continue using it, but at the same time want to leverage the extensibility or the ability to expand into AWS and gain the benefits of AWS as well. And so this allows us to either migrate our vSphere-based environments to AWS or simply extend those existing vSphere environments that we already have. And so by doing that, by extending our existing environment into AWS, we still get a single pane of glass across both on-premises and AWS, allowing us to manage those existing vSphere-based environments. And now it is worth noting that this is sold, delivered, and supported by VMware. So in order for us to sign up for this and to start using this, we go directly to VMware in order to make this happen. And so when we provision VMware on AWS, this is launched on bare metal single-tenant environments. And so it means that we can continue using all of the tools that we've come to rely on, such as vSphere, vSAN, NSX, and vCenter Server. So for those of us who have significant environments that are already based on vSphere and we want to continue using those, VMware Cloud on AWS is a really great option. In this lesson, we will cover the wide variety of storage options, review demos of creating and using services like Amazon Simple Storage Service and Amazon Elastic Block Store. We will review backups, snapshots, archiving, and more. Now let's discuss an overview of AWS storage options. Within AWS, we have a number of different storage options, such from block storage to object storage and so on, all kinds of different things. So let's start with block storage options, and first, the EC2 instant store volumes. So with EC2 instant stores, these volumes, these block level volumes are built into the instance. We're already paying for them. The price of this storage is already included in the hourly price of the machine. So we're essentially paying for instance store volumes whether we use them or not, simply because they're included with the EC2 instance. And so the great benefit of using an instant store volume is that we get an incredibly high degree of IOPS. So for those of us who have intensive applications that need a high degree of random I/O or a very high degree of sequential I/O in certain cases, then instant store volumes may be the right solution. Now, it is important to keep in mind that instant store volumes are considered to be ephemeral. What that means is that if the machine goes away, if we terminate it, if we stop it, if it fails for some other reason, then the data on those volumes is lost. There is no inherent durability to that data. There's no inherent persistence to that data. And there's no ability to perform snapshots. So if we did need some type of a durability in that data, we would have to leverage something else, some type of third-party tool or a home-brewed script that would perform perhaps some type of a file-level backup on that data. And plenty of AWS customers use instant store volumes to run very high-performing databases or enterprise applications that need the high-speed access that we get using those instant store volumes. And the reason we can get those high IOPS is because the underlying storage mechanism is powered by the physical host. And so there's no network in the way. We go straight through the hypervisor and to the hardware, and that's how we're able to get those high IOPS. And that's also the reason why these volumes are ephemeral, because if we stop an instance, if we terminate the instance, then the relationship between our EC2 instance and that machine, that particular physical host, is severed. The other option is the Amazon Elastic Block Store. So these particular volumes are independent of the EC2 instance. They exist physically somewhere else in the same availability zone. Now, for these volumes, we will pay an additional fee per gig per month in addition to what we pay for the EC2 instance. And it's possible that we could have the EBS volume and live independently from our instance. So if the instance goes away, the EBS volume can remain. There is an inherent persistence in the data because the volume can remain independently from the EC2 instance. We do have a limit of up to 16 terabytes on these EBS volumes. They are inherently durable. The underlying storage mechanism that powers EBS is a clustered service. So when we write our data to EBS, there are numerous copies across numerous devices in one availability zone. We also do get the ability to create snapshots, and this is a very powerful feature so that as we are writing data to this volume, we can take regular snapshots, and those snapshots are stored yet somewhere else. Those snapshots are independent from that volume. And so if the volume were to be perhaps accidentally deleted, then we could always restore that volume from a snapshot. And we'll talk more about the details of that later on. Now, with file storage options, we have the Elastic File System. The Elastic File System provides shared file access using NFS version 4. So with EFS, we have the ability to mount these volumes to EC2. We can mount EFS volumes to on-premises servers. And the nice thing about EFS is that it automatically scales. So there's no provisioning or re-provisioning or resizing that we have to do. As we store data to EFS volumes, the underlying storage mechanism just continually grows on its own. There's nothing for us to do to make that happen other than to write data to the volume. And as we write data, it automatically grows out, and as we delete things, it automatically shrinks. The other nice benefit of EFS is that as we write data to an EFS volume, that data is automatically stored redundantly across availability zones. So if we were to compare EFS with EBS, we would see that EBS is really meant to be used with a single instance at a time. And so if we have a use case where we need multiple EC2 instances and or on-premises servers to share the same volume, then we would look to EFS. The other difference between EFS and EBS is that, as we just talked about, EFS stores data redundantly across availability zones. But EBS, the Elastic Block Store, stores data in a single availability zone. And the instance and the volume have to reside in the same AZ. We'll talk more about the details of these kinds of things as we go along. The other options would be object and archival storage options. So we have Amazon Simple Storage Service, or S3. This gives us object storage. The transfers to S3 are all done over HTTP. So that's something to keep in mind, that when we talk about using EBS or EFS or instant store volumes, those will use a protocol that's very, very efficient for that type of storage, for block level storage. But S3 essentially uses HTTP. And HTTP is okay for sequential access, but it's not at all a protocol that will give us any amount of random I/O worth talking about. So keep that in mind. There's some other details about object storage that we'll talk about later as well. S3 also scales automatically. As we write data to it, it automatically grows. And S3 is really great for things like static assets, CSS, JavaScript, images, PDFs, software downloads. It's also really great for logs, and S3 has a very sort of a keystone role within AWS in that it gives us a very great place to store data centrally so that it can then be made available to other services. And logs is a great example of that. Data lakes is also a great example of that. Then we have Glacier. And so there's plenty of data that we may need to store for very long periods of time, maybe 7 years, 10 years. I remember working with a company at one time that had a requirement to store data for 99 years. So we may have certain types of data that we need to store for a really long period of time, even if we never look at it. Because of compliance or regulatory needs, we're just simply required to store it, even if we don't actually look at it. So that would be archival storage, and Glacier is the option for that. And so it is possible for us to store, say, logs or certain types of data in S3, and then after some time, if we feel like we're not really going to do anything with it, but we have to keep it, we can transition that data from S3 to Glacier automatically. And we'll talk about the details of that here coming up. It is worth noting that Glacier typically has a slow retrieval, right? So the process of getting data into and out of Glacier is asynchronous. So we put data in, and then if we want to get data out, we have to ask for that. The next option that we want to talk about here would be the AWS Storage Gateway. The Storage Gateway allows us to run storage volumes on premises and have those storage volumes essentially back up and connect with the cloud. And so this is generally installed as a virtual machine published by the machine images published by AWS, and we can install this virtual machine on our existing VMware ESXi or Microsoft Hyper-V hypervisors. And so in some cases, we are responsible for providing the hardware and the hypervisor that this machine runs on. And it does support industry standard storage protocols such as iSCSI. All the data that's stored on the storage gateway is encrypted, and it's either shipped to S3 or to Glacier, depending on the option that we choose. And so Storage Gateway gives us several different options, different configurations. We could run this as a gateway cached volume, where the frequently accessed data is stored locally on the machine that you provide on premises. And so infrequently, all data is stored also in S3, but frequently accessed data is kept cached locally. We have the gateway stored volumes, so all of the primary data is stored locally, but regular snapshots are stored in S3. And so if your local storage volumes were to fail, you could recover those volumes by pulling the snapshot back out of S3. Another option would be the Gateway Virtual Tape Library. And this exposes an iSCSI interface so that we can essentially replace current tape drives with the virtual tape library, and each tape is stored in S3 or in Glacier. The last option that we'll talk about here is the Storage Gateway Hardware Appliance. This is a relatively new thing, having been just announced here at the time of this video. And this is an actual server, a Blade server, available for purchase from Amazon.com. And this is essentially a Dell EMC PowerEdge server with the software or the Storage Gateway software already preloaded, right? So for organizations who don't necessarily have the means to procure and deploy and manage the hardware, this can greatly simplify that by allowing you to simply purchase hardware that's already ready to go. You just simply configure the software that's already on there to connect with your Amazon account, and it's pretty much ready to go. So those are our storage options, and each one of these, object storage, block storage, file storage, we will be taking a closer look at as this lesson continues. Before we get to the details of different services, let's first take a look at the difference between object versus block storage. So when we think about the difference of object and block storage, it's helpful to think about, what does it mean? How do we go about updating, say, a few characters, a few bytes in a 1 gigabyte file, right? So let's say that we have a 1 gigabyte file locally, and it's a file locally. When we upload that to, say, S3 or Glacier, it becomes an object or an archive, and the whole thing goes. When we make changes to that file locally, we're only changing a small part of that actual file. So if we were to look here at this diagram, and again, considering that we're going to make a change to a 1 gigabyte file. With block storage, you could see this, we're just changing a little bit of data, just maybe a few bytes. And with block storage, the reason we call it block storage is because we could essentially map wherever these bytes are in the file, those bytes can be addressed to the blocks on the disk. So with block storage, we can simply make an update to the blocks where those bytes exist. We don't necessarily have to worry about or do anything else with the other blocks that contain other data. And so this is partly how, databases that store, you take MySQL that stores, an NODB table in one file. There could be millions and millions of records in that one file. And the way that we're able to pull one record out of that so fast is by leveraging indexing and knowing where to find the blocks, so we can go directly to those blocks. And that's the benefit of block storage, is that that's how block storage is able to give us such high-speed access, is because we have access to the blocks. With object storage, in order for us to make any changes, no matter how large or small, even changing one character, even 8 bytes, we would have to upload the entire object all over again, right? And so, again, with object storage, the main difference here is that we upload the entire 1 gig as opposed to updating just the blocks with only a few bits or bytes. Another major difference is the transfer. With object storage such as S3, we are using HTTP for transfer. And HTTP, it does okay for sequential access, but it's not at all a protocol that will give us any kind of random I/O. And so with block storage, we have a much more efficient protocol that will enable us to communicate with the disk very rapidly. Object storage cannot be mounted, at least not truly. Block storage can be mounted. Now, when I say not truly, what I mean is that I'm going to put an asterisk here, a little star, because I want you to keep in mind that with object storage, there are pieces of software out there that will say, give you the ability to mount an S3 bucket to an EC2 instance or to your local machine, what have you. But it's kind of an illusion. It's not mounted in the same way that block store is. It's really, when you mount something like S3, in the background, there's a stream wrapper. And anytime you write to what appears to be a volume, anytime you write, the entire object is being uploaded. You're not just writing the changes that you made. You're not just writing deltas like you would with block store. You're uploading the entire object. And as we will talk about later, there are costs to S3 associated with the requests that you make, right? So if you mount something and treat it like a volume and constantly read and write to it, you could end up artificially inflating your S3 bill unnecessarily. Another major difference here, again, like I think I've mentioned this, is that with S3, there really is no random I/O. It is possible to do a get ranges and download a range of bytes from a particular object, but that's not really the same as random I/O. So the big consideration here is if you need a high degree of random I/O, block storage is the answer. If your data changes rapidly, block storage is the answer. If you need a file system so that you have access to files in the way that files work, then block storage is the answer. If your data doesn't change very often at all, if your data is relatively static for long periods of time, and your data needs to be accessible by other services within Amazon and or accessible to places out or hosts out on the internet, then object storage with S3 is probably the answer. And again, we will take a closer look at object storage solutions such as S3 and block store solutions such as EBS as the course progresses. Now let's review an introduction to Amazon Simple Storage Service, or S3. So with Amazon S3, we gain access to object storage. And object storage is a perfect place for relatively static type of data. You know, if your data doesn't change very often at all, then S3 is an ideal storage. When we think about static assets for websites, for example, those are classic examples. CSS, JavaScript, images, PDF documents, those things, some of those may update, you know, once a day or a couple of times a day, but oftentimes when they do, you want them to get a new name anyway. You're not necessarily reusing the existing name due to caching, right? So with object storage, storing these things in S3, S3 makes a really great central place for other things to access. And those other things could be, other services within AWS. They could be your end users out there on the web downloading CSS and JavaScript. And so with S3, when we store data there, and whether it's static assets or even keep in mind that snapshots are also stored in S3, that S3 is a distributed system. When we write data to it in the standard storage class, and we'll talk more about storage classes later, but the standard storage class replicates that data across numerous devices in numerous availability zones. So there's inherently a very high degree of durability in our data. Now, there is no file system within S3. There's basically a flat structure inside the bucket. So if we look here, within the S3 service, we can create buckets, and we may create a different bucket for different types of data. You might have a bucket for web assets, a bucket for logs, maybe a bucket for a data lake. And then once we have a bucket, we can store objects in that bucket. And so again, objects exists inside the bucket. And so that's as flat as it goes. There's no more hierarchy than that, just objects in a bucket. It's also worth noting that buckets are private by default. The only credentials that can be used to access a bucket would be the master credentials, those credentials that own the account. And any other IAM user, or any other user for that matter, would have to be granted explicit permissions in order to access that bucket. And we'll talk about more ways to do that in a later lesson. Now, when we do upload files to a bucket, every bucket has its own URL. And you'll notice here that the URL in this particular case, we have there are several different types of URLs that we can get. This is one option where we have the region. You'll notice here that in this particular case, this bucket in this example would exist in the US West 2 region. So this is a regional endpoint. There are other ways of getting to that bucket. Now, in this kind of URL, we have you'll see here that we have the bucket name. That's a part of the URL. And then we'll have a slash, and then you'll notice here the key here is images/logo.png. And so we can create the illusion of a file system by including slashes and periods in the name. But ultimately, there is no folder called images. There's no file called logo.png. There is an object that contains a slash and a period in its name. And so we can use that kind of pattern to organize our buckets. And so when we do that, if we had, a number of different objects back here, a number of different images back here, all with the same, all under images slash, then in that regard, images slash becomes a common prefix. And we can use that common prefix to help find things in a bucket. So there is no limit to the size of a bucket. We can store as many objects as we want in a bucket, and we can store as much data as we want in a bucket, far into the petabytes or beyond if we need to. There is a limit per object, so any one object can be up to 5 terabytes in size. There is also an upload limit of 5 gigs per put operation. And so a common question is, well, if you can only upload 5 gigs at a time, how do you possibly get an object that's 5 terabytes? And the answer to that is multi-part upload. S3 does support multi-part upload, and Amazon recommends that for any objects greater than 100 meg or so, that multi-part upload can be a faster way of getting that object to S3, simply because, especially if you're running in a multi-threaded environment where you can dedicate multiple threads to multiple parts. That way you have multiple parts of this file being uploaded essentially in parallel. S3 also supports server-side encryption using AES 256, the advanced encryption standard. And when S3 performs that server-side encryption, we have a number of options in regards to where the keys come from and where the encryption keys are managed. But either way, wherever the key is actually managed, S3 uses a key per object. Every object gets its own encryption key. That way, if any one key were compromised, only that one object would be compromised and not an entire bucket, right? So that's S3. And keep in mind, again, the takeaway from this lesson is that S3 provides object storage, and it's really great for relatively static types of data like static assets, log files, data lakes, and so on. And we will take a closer look at S3 and its relationship to other services and how we can use S3 in the bigger picture as the course goes on. Now, a few other features that are worth knowing about Amazon S3 would be, one, versioning. With versioning, you can, as you write objects with the same name, with the same object key, every time you do that, you get a new version. And by having versioning turned on, you can always roll back to a previous version. So if you were to accidentally update something and needed to get back, you can roll back to a previous version. If you delete something and wanted to get it back, you can undo a deletion with versioning. Another feature would be what we would call query in place using a feature called S3 Select. With S3 Select, you can actually extract ranges or subsets of data from an object in S3. And so that would obviate the need for you to use your own compute resources to perform some type of extract, transform, load, and query operation. You can perform that kind of SQL query operation directly on an object in S3 using S3 Select. Another useful feature is cross-region replication. So if you turn on cross-region replication and you specify the 2 different buckets in 2 different regions, any changes you make to one bucket will be reflected in that other region. So that's very useful for disaster recovery. Another useful feature would be event notifications. And so with event notifications, as things happen in your S3 buckets. For example, if you upload a new object, or you update an object, or delete an object, each one of those actions would be an event notification. And you can subscribe to those notifications in a number of different ways. A common use for these is to subscribe Lambda functions to those notifications so that AWS Lambda can programmatically respond to, say, the addition of a new object and perform some type of an analysis on that object. Another feature would be S3 transfer acceleration. So when you are moving data between regions or from large physical distances, it's worth noting that AWS has their own backbone. The fiber that connects Amazon regions, much of that is owned by AWS, and so they operate essentially their own backbone. And with S3 transfer acceleration, AWS is able to optimize the network paths to enable us to accelerate a connection over long distances that might ordinarily incur a much higher degree of latency. And so the thing to keep in mind about S3 transfer acceleration is that the longer the distance, the greater benefit you actually get. And so if we were to go from, say, the east coast of the US over to, somewhere in Eastern Europe, then we would see a significant improvement in the latencies during that transfer acceleration. If we were to go from, say, the northern US to southern US, we would see a less improvement because it's a shorter distance. And the last feature I'll leave you with here is static websites. S3 can also be configured to simply host a static website directly from that bucket. And that can be very useful in many cases. For example, I've worked with clients who have a dynamic API, but the marketing component of their domain, the www, is relatively static. And so I've configured this for clients where their api.domain.com runs from an elastic load balancer, is dynamic, but www.theirdomain.com is served directly from an S3 bucket. And one of the benefits of doing that is that you could potentially run, something like WordPress, for example, on a machine on premises. And by making the updates there and publishing that content as static HTML, you could greatly lower your costs simply by serving it from a static website in S3 rather than running WordPress on EC2, right? So that's Amazon S3, and we will take a closer look at some of these things through demos and use cases as the course progresses. Now let's review a demo of creating buckets and objects within Amazon S3.
All right, from the AWS Management Console dashboard, we will go to S3. Go ahead and select that. Now, before we get into creating a bucket, I want to point out that up here it'll say that S3 does not require region selection like most services. Like, if you recall from EC2 and other services that we've looked at, we've always ensured that we were in a particular region. But with S3, at least in the console, we can view all of our buckets across all regions in one place. Now, even though the console allows us to act globally, you'll notice here that as we scroll down, each bucket is, it lives in a particular region, right? And you can see I have several buckets related to my company, Cerulean Systems. And then, of course, this one here, Cerulean.Systems, serves the website for that domain, Cerulean.Systems. And then I have a number of other buckets related to automated processes, which, we don't really need to worry about. But the point here, again, is that I have buckets across several regions, right? Ohio, Virginia, Oregon, and so on. So let's go ahead and create a bucket. And you'll see here that all we need to do is enter a bucket name, and it has to be DNS compliant. And if you hover over this I here, it says that the bucket name must be unique across all existing bucket names in Amazon S3 across all accounts, all regions, right? And so, if we were to try something like my bucket, of course that's not going to work. Someone took that bucket name a long, long time ago. So we do need to choose a bucket name that is globally unique, right? So for now, I might call this one Fundamentals Second Edition, right? And that bucket name should be available. So we'll go ahead and choose which region do we want that to be in, and you might choose, of course, you would choose a region if you had EC2 instances, if you were going to launch, other infrastructure there that needed fast access to that data. You might choose a region if you were serving static content out to end users, then you might choose a region that was closest to them. But if you were planning on using something like CloudFront, then it doesn't really matter because CloudFront would handle the latency issue, right? So being based out of Colorado, I typically do a lot of things either in Oregon or Ohio, right? So I'm just going to leave that as Ohio. And we could copy settings from an existing bucket. If we had another bucket that had different types of policies and options related to it, we could copy those, but I'm going to leave that for now. So that's really all we need to do there. Go ahead and say next, and then now we have the ability to turn on versioning, right? So if I turned on versioning, then it would say every time we upload an object with the same name. Let's say that we were storing static HTML or PDFs, and if we made an update to an HTML page or a PDF document, as we made those changes, S3 would continue to keep previous versions, so that it makes it really easy for us to roll back to a previous version. You can also use versioning to help prevent things like accidental deletion, right? So even deleting an object is not a true delete. It's like a soft delete, and you could still go back to a previous version. We could also turn on server access logging. This is very similar to Apache-style access, so especially if you're serving static content directly from that, then you would probably want to be aware of what kind of access patterns you're seeing. And just like most resources, we can use this to tag, right? Again, we could say environment dev, we can add a project, cost centers, and so on. Again, using those to organize our environment and attribute cost. We could also turn on default encryption. So by default, nothing in S3 will leverage server-side encryption unless you opt into it on an object-by-object basis or an upload-by-upload basis. But if we were to do this and turn on default encryption, then everything we upload would be just automatically encrypted without us having to opt into anything. And we could say, well, we want S3 to manage the keys, or we could choose KMS to manage the keys. And we'll talk more about server-side encryption and key management service later on. So let's go ahead and go to next. And we'll go ahead and what it's saying is that it's giving us the option to manage public access control list and manage public bucket policies. These are things that are put in place because a number of organizations over the years have really kind of gotten themselves in trouble by leveraging access control list and bucket policies that ended up making sensitive data publicly readable. And so Amazon has done, even though it was, not Amazon's fault, the customer was ultimately responsible for making that happen. Amazon has done a great job of helping us recognize that we have made something publicly available. And so what this is saying is that we can say, well, I want to block someone's ability to make new public ACLs, right? I want to and I want to remove any public access granted through public ACLs. And then down here, the same thing applies to policies. And so if we were to leave these checked, then we would not be able to make anything in this bucket publicly accessible. And so, which is something we're going to do later on in a later demo. So I'm going to remove these for now. In your particular case, it all depends on if you plan on storing any kind of sensitive data in that bucket, then you'll definitely want to leave these checked. All right, so we'll go to next. We'll review that. Again, so AWS Fundamental 2nd Edition, versioning disabled. We have a tag. Default encryption is disabled right now. And then, of course, we've removed the blocking of public access because that's something we're going to do later on. So we'll go ahead and say create bucket. And it says here, objects can be public. And so now if we were to go there, you'll see now this bucket is empty. Upload new objects to get started. So we could say upload, and we could choose the files, or we can drag and drop. So I'm going to drag this particular lesson here, and then of course it's saying we're uploading a little less than 500K. We'll go next, set the permissions, and then it's showing here that the owner of the account is the only person who has any kind of access to this particular object. And so right down here, then of course I could use ACLs to grant public access to that object, but we're going to do that later on. So we'll leave that as do not grant public access for now. And I'll go next. And then of course we can choose the storage class. So as you move down this list, the storage gets cheaper and cheaper. So standard infrequent access means that it's really for long-lived data. If you need to get to it, you want to get to it exactly then. And you want it exactly then when you ask for it, but you might not ask for it very often. One zone IA, the difference between these two is that you'll notice here the number of availability zones that stores the data. And so standard IA stores multiple copies across at least 3 availability zones, whereas one zone, as the name suggests, stores copies in 1 availability zone. And so again, you can lower your price by using one zone infrequent access, but the idea there is that you have a much lower degree of durability in that data because you're storing data essentially in one data center rather than 3 data centers. And so one zone IA is ideal for data that can be either easily recreated or data that you have stored somewhere else, like on premises, that you can just re-upload if for some reason it happens to be lost. And then, of course, Glacier is for data archiving, and you'll notice here with retrieval times from minutes to hours. So while the cost is very, very low, the retrieval time is an asynchronous process, and you will not get it when you ask for it. You will get it sometime later, right? So in this particular object, I'm just going to choose standard. And then we'll go ahead and say upload. And there we go. We've uploaded an object. And that's about it. You create buckets with S3, and then you upload objects to that bucket. And now this object I can make accessible to other systems. If this were some type of large collection of log files, or if I was doing some large data lake in this bucket, then this would be a central place to which I could publish things, and a central place from which I could download that data and use it in some other way, like with EC2 or EMR and so on. Now, another thing that I want to point out here is that the web console gives us the ability to create a folder. And so if I were to go here, then I could create a folder called, logs or images or whatever. I might just call one images. And then if I go there, now it kind of appears as if I have a hierarchy. If you notice up here, it goes AWS Fundamental, 2nd Edition, and then images, and then I could create another folder, like this. And then if we go in there, then of course now we're seeing what appears to be a hierarchy. And that's a total illusion. As far as S3 is concerned, there is no hierarchy, there's no file system, it's completely flat. And so the console allows us to create that, and really what it's creating is like some kind of a placeholder as a common prefix. So there really is no, if we go back up here, there's no folder called images. What this would mean, if you see what appears to be a folder, then it's just a number of files with a common prefix, right? We don't have a whole lot of files here, so let me just go switch over to a different bucket real quick. We'll take a look at cerulean.systems. And so this bucket houses the domain, the static HTML for that particular website. So if we were to take a look at the CSS quote-unquote folder, you would see that there are two objects here, and they simply share CSS as a common prefix. If we were to look at this and look at the object, the key, right? So you'll notice that the key is css/agency.css. And so the key, essentially the name of the object, contains a slash and a period in the name. And there is no folder, there is no file, right? It's all flat. And so again, when we see what appears to be a folder, we're really looking at sort of an illusion within the console. It's all things based on a common prefix. All right, so if we go back to our file here and we take a look at this object that we uploaded, again, the key is just lesson 5 storage in AWS. There's no common prefix there, but there could be, right? We could use, again, we can use slashes to create the semblance of a file system if we wanted to, some kind of predictable ordering and organization to the objects in that bucket. All right, so that's about all there is to it. Again, we very easily create a bucket and then upload objects to that bucket. We will continue to explore these kinds of things, especially around permissions, as the course continues.
Now let's take a look at bucket security with resource policies and ACLs. Many resources in AWS support what we would call resource-based policies. Earlier in this series, we talked about policies within IAM, policies that grant permissions to access, perform certain actions on certain resources. Policies like that in many cases can and should be applied to users and groups, but in other cases we may want to apply or need to apply the policy directly to the resource. And so here's an example where we are applying a policy directly to an S3 bucket. And the reason that we're applying the policy to the bucket in this particular case is because if we notice here, if we take a look at the principal you'll see is, in this particular case, an asterisk. And the asterisk in this case means that we are allowing anyone and everyone, even people who don't have an account with AWS, even anonymous users, people who are not authenticating. And so by placing an asterisk here, we are essentially enabling this bucket to be read by the public, anonymous users. So what we're saying here is that essentially asterisk, anyone and everyone is allowed to download using the S3 get object action from anywhere in this particular bucket, this bucket being cerulean.systems. So in this particular case, if you were to visit that domain, cerulean.systems, then you would see a website, and it would be static content, a static website being served directly from that particular bucket. Now we can do a number of different things with resource policies. Resource policies will also allow us to share buckets between different accounts. And so in this example, you'll notice that we are specifying again the principal, but we are saying, using the AWS key here, we're saying that we want to share this account, or at least allow these particular actions with this particular account, right? So we're specifying this particular account number, and this particular action, the S3 put object action, is then essentially delegated to that account, to the root of that account. And the root user of that account can then further delegate that permission to their users. And so essentially what we're saying here is this some other account is allowed to upload, perform the S3 put object action to anywhere in this particular bucket. And so resource-based policies allow us to do several key things. One, either generally making them publicly accessible or sharing them with another account. And S3 is one example of resource-based policy usage. Simple Queue Service and other resources also support resource-based policies. Now, another thing that we can do with S3 in terms of making a bucket or objects publicly readable or sharing or granting access is either using a policy, like we just saw. We can use a policy where if we specify an asterisk for the principal, then we are sharing that or granting access to anyone and everyone. Another way that we can grant access is by using ACLs, or access control lists. And so a resource-based policy, a bucket policy, allows us to be very, very fine-grained and specify conditions and all kinds of things to really target the different actions under, and different resources under different conditions. But ACLs are more coarse-grained. And so if we were to specify read operations or write operations, those would actually end up including a number of different actions that we might specify in a policy. So personally, I prefer to use policies because they are fine-grained, and I only generally use ACLs in very certain circumstances when that's the only option. And so in terms of making data publicly readable, I want to spend some time here because over the last few years, a number of organizations have kind of gotten themselves in trouble by exposing sensitive information in publicly available S3 buckets. And I think mainly that comes down to a lack of education and or a lack of communication. That perhaps the person who created or put that policy or ACL into place didn't realize what they were doing. Or they did, but didn't communicate that that was a publicly accessible bucket to people who were writing data, right? So as an organization, we need to keep in mind that the security of our data within these S3 buckets is our responsibility. And so it's the onus of knowing the consequences of using these kinds of things is on us. We have to be aware of these kinds of things, and we have to educate ourselves, educate our team, and communicate that this particular bucket is publicly accessible, and it should only be made that way if it needs to be that way. And so there are several canned ACLs that we can use to make certain objects or buckets publicly readable. One of them, as the name suggests, public read. So that one's very straightforward. If you apply that ACL to an object or a bucket, it will be accessible by the public. Another one would be public read-write, meaning that now it's not only readable by the public, but it's also writable, that people can write to it. Anonymous users can write to that. Another one that is kind of perhaps anti-intuitive, counterintuitive, is the authenticated read. I want to draw your attention to this one and kind of make sure that you remember this. If you take away anything, take away this, that the authenticated read ACL applies to anyone who authenticates to the AWS API, even those users outside of your organization. And so keep in mind that anyone in the world with a valid credit card can sign up for an AWS account, even people with potentially malicious intent, right? So, some random person out there could sign up for an AWS account, and if your data has the ACL, authenticated read, this person could access it, right? So this is This is really one that I would recommend avoiding. I'm really not sure exactly why that's in there, but I would recommend avoiding that. There are plenty of other ways to grant access to your users rather than using the authenticated read canned ACL. Right, so those are some things to keep in mind as you move forward and continue to work with S3. Keep in mind that the security of that bucket is your responsibility, and you can leverage these kinds of things, bucket-based policies and ACLs, to help manage the permissions of that bucket when it comes to allowing access to that bucket from the public or from other accounts. Now let's review a demo of creating a bucket policy for public read access.
Okay, so we're back in S3, taking a look at the AWS Fundamental Second Edition bucket that we created earlier. Here's an object that we uploaded earlier. And so if we needed this bucket to be publicly accessible, right? If this bucket were meant to house, some type of information that you wanted to disseminate to the public at large, to anonymous users, then there are a couple of ways to go about that, right? If we were to go to permissions, we could use access control lists, and we could say that, everyone is allowed to do certain things, right? We could say everyone is allowed to list and everyone is allowed, to read, and those are fairly coarse-grained, right? They actually provide a number of different operations within those. And I typically don't like using access control lists because they are very coarsely grained. If we were to use a policy, I'm going to go ahead and cancel that, because if we were to use a policy, then the bucket policy allows us to be much more granular, and we can specify exactly which permissions we want people to have. And so going back here to access control, for example, the read gives, like I said, the read bucket gives quite a few different permissions, but maybe we only want them to have some but not others. And we can do that with bucket policies. And so with a bucket policy, it's very similar to policies that we might apply to our users and groups. It's written in the same kind of language. So I'm going to go ahead and paste one here, one that I've already prepared, and then we'll just talk through it. And you can see that we have a policy that includes a version and a statement. The version is not our version. This is the version of the policy language, and so this is the date on which that version of that policy language was last published, back in 2012. So again, when you see versions within policies, whether it's an S3 bucket policy or a policy applied to a user, that version is pulled from the AWS documentation. And so then, of course, statement is really a collection of statements, and we really only need one right here. So we have one statement here, and that statement says that we are going to allow, this is the most important part of this whole thing right here. The principal, meaning we're using an asterisk here, we're allowing anyone and everyone, including anonymous users, people who are not authenticated against the AWS API. So essentially the asterisk here means public. And then we're allowing anyone and everyone the ability to perform the S3 get object action, which means to download from anywhere in this particular bucket. So another important part of this is the resource. And so we have the name of the bucket here, and then /* means all objects in the bucket. And so we could grant access only to a limited prefix, right? We could say, well, you're allowed to download, but only objects with a common prefix, right? Or if we remove that again, then we're saying every object in the bucket. And then of course we could list other actions, right? We could say get object version. We could say list bucket. There's a number of other actions that we could grant access to. If we wanted the public at large, anyone and everyone, to upload, then we could also add the put object, right? Using put object would allow people to upload right? So we don't need to do that, right? So again, by allowing an asterisk here for the principal, we're allowing everyone to download objects from that bucket. I'm going to save that, and now the console is warning me, right? The Amazon has done a really good job of highlighting buckets that provide public permission. And so keep in mind that, it is the customer's responsibility to configure these policies appropriately. It is then your responsibility to communicate with members of your team. Hey, this particular bucket is public. Don't put sensitive information there. Now, it says this bucket has public access. We highly recommend that you never grant any kind of public access to your S3 bucket, but I think that's a little heavy-handed, because there are times when you need to do that. If we were to go back, we looked at this bucket earlier, and then of course, up here it shows that this is public as well. It's highlighting the fact that it's public. But if we were to take a look at Cerulean.systems, we looked at this earlier. The reason it needs to be public is because if we go to properties, this bucket is configured for static website hosting. If it weren't publicly readable, then we would not be able to serve the website from the bucket, right? So I don't know if I necessarily agree with that statement. Never make them, public. There are times and places when you need to do that. My recommendation would be aware of what it means and communicate to your team that information in that bucket is now publicly available. All right. So again, just as a recap there, if you had a need to make certain buckets publicly available, you could do that through access control lists or through bucket policies.
Now let's review an introduction to Amazon Glacier. For a number of organizations, we may very well have certain types of data that we are required to keep for long periods of time. And it could be some type of regulatory compliance need. It could be a disaster recovery need according to business policy, that certain types of data, even if we don't look at it, we just want to put it away somewhere so that we have it in case we need it. And that putting it away may mean leaving it there for years on end. And in doing so, we would like to be able to save money by putting it into a system designed for low-cost storage, and that is exactly what Amazon Glacier is for. So Amazon Glacier gives us archival storage. It is designed for long-term storage. It is not designed for fast retrieval like S3. And so with Glacier, within the Glacier service, we can create vaults. Very similar to S3 creating buckets, in Glacier we create vaults. And then we add archives to those vaults, right? So archives live within a vault. And we can store any number of archives in a vault. So when it comes to getting those archives to Glacier, we can write those archives, either we can transition things from S3. So if we already have data in S3 that we simply want to keep but not necessarily look at for a while, we can very easily transition that into Glacier. We could also directly upload to Glacier. The thing to keep in mind about that, though, and it gets a little complex, is that if we upload an archive directly to Glacier, then we go directly to Glacier to get it back. If we first upload data to S3 and then we transition it to Glacier, we go to S3 to get it back, right? And we're going to talk about that mechanism in an upcoming lesson. Now, the way that we get data out of Glacier is through a retrieval request. So it becomes an asynchronous process. Generally, the standard retrieval time is 3 to 5 hours. And so with S3, you can upload and then immediately download. It's a synchronous thing. So you can download things out of S3 at will at any time. But with Glacier, you create a request. You say, hey, I want to be able to I want to download this particular archive, and Glacier will come back and say, all right, I hear you. Give me some time to go and find it and pull it out and make it available, right? So again, the standard retrieval time is 3 to 5 hours, but we can pay an additional fee to gain an expedited retrieval. So if we pay that additional fee, we could potentially get those retrievals down to closer to 10 minutes rather than 3 to 5 hours. It's also worth keeping in mind that while the storage of Glacier is really inexpensive, at least here in the US, for US-based regions, the storage for Glacier could be less than 1 cent per gig per month. It's incredibly low cost. But it can become expensive if we're doing a lot of retrievals, because you will pay an additional fee on top of the storage. There's an additional fee for actually retrieving the data, and that's charged for every 1,000 pulls that we do. So if you find yourself pulling the same data out of Glacier regularly, then it may actually benefit you to move it back to S3 in order to save money, right? So keep that in mind, that if you find that you have certain types of data that you want to keep for a long period of time, that you don't access very often at all, if ever, then archival storage with Amazon Glacier may very well be the solution. Now let's talk about storage class management with lifecycle rules. When we're storing data in S3, we need to keep in mind that there are several different storage classes to choose from, and those storage classes will affect what we end up paying for that storage over time. The default storage class is called the standard storage class, and this will store upwards of 6 copies of our data redundantly across numerous availability zones. So we get a very high degree of durability in that data. And it's stored redundantly, but it's stored in a way that enables very fast access, so that when we do want to read that data, it's available to us to get very quickly. We can lower our costs by looking at the other storage classes. Now, another storage class would be the standard infrequent access. Now, with standard infrequent access, we can lower our cost for data that we just don't look at quite as often. Now, the thing about infrequent access is that we still get the same amount of durability, but it's just stored in a different way. And it's written to storage that is optimized for infrequent access. So there may be data that we don't read very often, but when we do read it, we want to be able to get it synchronously at will. Another storage class would be the one-zone infrequent access. And in this regard, we get a lower degree of durability because remember that with standard and standard infrequent access, the data is stored across numerous availability zones. With one zone infrequent access, as the name suggests, the data is being stored in one zone. And so we get less resiliency, but we also get a much lower cost. And then lastly, as we've already talked about, we have Glacier. And when data is transitioned to the Glacier storage class, the data is moved into the Glacier service. But keep in mind that if you write data to S3 and then you transition that data to Glacier, you have to go to S3 to get it out. You can't get the data directly from Glacier. You have to go to S3 and manage that data from within S3 because that's where that data essentially originated from, right? So keep these storage classes in mind that as you move forward using S3, we can lower our bill by optimizing the storage class for the particular types of data. Now, another thing that we can take advantage of is what we call lifecycle rules. And so within S3, we have, remember that within S3, we're writing objects into buckets. And so we might have certain types of data, and we might say for a particular type of data, after 7 days, then let's automatically transition that to standard infrequent access. So it could be maybe a log file, for example. A log file gets wrapped up and rotated, and that log file gets shipped to S3, and perhaps sometime during that first 7 days, you may do a lot of analysis on that log file. And then after 7 days, you may continue to do some analysis, but maybe not as often or not as much. And so you want to lower your cost by transitioning it to standard or infrequent access, but still have it available for when you do actually need it. And so we may put another lifecycle rule in place and say after 30 days, transition to Glacier. And so sometime in that first month, you may perform different types of analysis and pull that data in and do some type of processing on it. But then after those 30 days, you still need to keep it due to perhaps regulatory needs, but you're probably not going to do anything with it. And so by transitioning it to Glacier, what this particular object then essentially becomes an archive in a vault within Glacier automatically. Just by putting these lifecycle rules in place, the S3 and Glacier systems work together to move that data around in order to satisfy these rules. And so the really great thing about that is that, we don't have to write scripts and worry about the management on our own. All we have to do is put the rules in place and rely on AWS to transition that data for us. And then, of course, we could also say, we could do one more thing here and say, perhaps after 2,600 days or, about 7 years, permanently delete that data. And so once we put these lifecycle rules in place, as time goes on, as objects are written and transitioned and deleted, we can rest assured knowing that we've optimized our usage of these different storage classes in order to optimize our costs for storing large amounts of data within AWS. All right, so now let's take a look at a demo of adding lifecycle rules to our S3 bucket.
All right, so we're back at the S3 dashboard, and you can see here's the S3 bucket that we created earlier, and of course it's highlighted as being public. So now what we want to do is take a look at adding lifecycle rules, and lifecycle rules are really great for things like logs, where you have these files piling up in S3, and maybe for some reason you have to keep them, but you may not do anything with them, right? So you can see here I've created a bucket called Cerulean Logs, and of course I can filter everything according by name. So if I do a search for Cerulean, then we'll see all of my buckets related to that. And so what I want to do here, before we actually get into adding lifecycle rules, let's just take a look at where one of the places where logs can come from. So if we go to the Cerulean Systems bucket, then of course, like we looked at earlier, this particular bucket is configured for static website hosting. And so the cerulean.systems domain is served directly from this bucket. And currently, I do not have server access logging turned on. And so if I want to turn that on, I'll go ahead and do that. And then if I say enable logging, then it asks me to choose a bucket into which those log files will be delivered. I don't really want it to be the same bucket. So I'm going to choose Cerulean Logs. So that's a bucket that I created specifically for logs. And of course, logs can come from a number of different places. They could come from the load balancer, from CloudFront. They could be generated by our application. We could have logs coming in from CloudWatch logs through Kinesis into S3. And so in that regard, I might use this one bucket to collect logs from a lot of different services, and I want to organize those. And so what the target prefix means, if we hover over this I, it says it's optional, and it's a prefix that S3 can assign to all object keys so that you can quickly locate the log objects, right? So I'm saying that, yeah, this bucket will be used for logs from a number of services, but I'm going to use the prefix as a way to organize that by service, so that I don't just have a whole bunch of logs across everything in one in one place. I have all of my S3 website logs in one prefix, my load balancer logs in another, my CloudFront logs under another prefix, and so on. And of course, that's just one way of doing things, right? That's the way that I like to organize things. But it's all up to you. You may decide that you want a completely different bucket for each of those services, and that's okay too. So now that we have server access logging on, any visits to this domain for the static HTML that's being served from here will be logged to that particular bucket. Okay, so now let's go back to that Cerulean logs, and we'll go here to Cerulean logs. And it's currently empty. Nothing has been written yet. And of course, it will happen. It just takes a little bit of time. And we're going to go to, let's see here, Management Lifecycle. So the idea here is that at some point, perhaps once these logs are delivered, I may run some kind of analysis on them. I might pull them into Amazon EMR and use the Apache Big Data tools to do some kind of analysis. I could look at them with Lambda, all kinds of possibilities that we could do. But then at some point, I've already done my analysis, and then I don't really need to. I don't need to keep them in S3. I may need to keep them stored for compliance reasons, right? So I'm going to go ahead and add a lifecycle rule, and say here it says you can add a filter, and I'm going to say S3 website, right? So you can prefix. Oh, this is the rule name. Let me get rid of that one. So we'll call this one, we can use the same thing, but then here we want to add the slash to that prefix S3 website. And so the rule name is the S3 website, but then the prefix actually has a slash in it. All right, so now that we've named the rule, we've given it a prefix, we might apply different lifecycle rules to different logs, right? Some logs for different services may remain in S3 for longer or for less time. So we'll go ahead and say next. And what I'm really interested in right now, I don't have versioning turned on for the logs bucket, so there are no previous versions. So what I'm really looking at here is the current version, right? So for current versions of objects, let's add a transition. And we'll say transition to, after object creation, we're going to transition to Amazon Glacier after, let's say, 30 days. We could even say, 7 days. It's all up to you, right? How long will it take you to do what you need to do with those files and before you want them over into Glacier? So it could be that all of the processing that I'm probably ever do will happen in that first week, right? So I'll go ahead and say next. Now, you could also set up an expiration. You could say, essentially, for the current version, I want to expire that object, right? And so expiration allows us to just automatically delete that after a certain period of time. So let's say if I do some math here, 365 times 7 is about 2,500 days, right? 2,600 days or so. Right, so I could say expire the current version after 2,600 days, which is about 7 years. Right, so after 7 days it goes to Glacier. After 7 years, it gets deleted. We could also say clean up incomplete multi-part uploads. So multi-part uploads, there could be a case where we start one, and then for some reason that multi-part upload it fails to complete, and then we might have to restart it later. But if we don't restart it after a certain period of time, then we just want to clean it up so that these uncompleted parts aren't just lying around in our S3 bucket taking up space that we're paying for, right? So that this is also a good idea to clean up incomplete multi-part uploads. And so generally, I mean, you could imagine that if you haven't resumed that upload, within a week, then you're probably either not going to do it, or you can just come back to it and try it again. All right, so let's go ahead and say next, and we can review this again. So the name of the rule is S3 website. The scope is for anything in that particular prefix, and we're saying for current versions. We're not worried about past versions simply because we don't have For logs, there really won't be versions. So we're going to say for the current version, transition to Glacier after 7 days, completely expire, delete after 7 years, and then clean up multi-part uploads after 7 days. So we'll go ahead and save that. And now for the logs, we have a lifecycle rule, and that only applies to objects with the S3 website prefix. And so again, you might have logs coming in from the load balancers or CloudFront or API Gateway or a number of different services, and you could use these kinds of patterns, prefixes and whatnot, to apply specialized rules specifically to those kinds of logs, right? And so by doing this, by automatically shifting our data. You can imagine if you have terabytes and terabytes worth of data, maybe even petabytes worth of data, then transitioning from S3 to Glacier could drastically reduce your costs for those long-term storage, right? If you are under some type of compliance and you have to store those files, right? If you have to store these files for some period of time, like 7 years, maybe 10 years or more, then over that period of time, we're talking about a very significant cost savings, especially when you are operating at terabytes or petabytes worth of data, right? So that's how we can leverage lifecycle rules to automatically, save money in the long term when we're using S3.
Now let's talk about instance store volumes. With EC2, some EC2 instances include instance store volumes, right? So it's worth noting that not every instance type does include instance-based volumes. There are several different instance types that only use EBS. But for those that do include instance volumes, they are included with the instance. And again, they are powered by the physical host. So remember that when we get an instance on EC2, this is a virtual machine, usually a virtual machine, and that virtual machine is powered by a physical host. And so for those instance types that include instance store volumes, those volumes are powered by the physical host. It goes straight through the hypervisor to the actual disk that's right there in the same, in the same chassis. There's no network latency. It's straight through. And so as a result, we can see a very, very high degree of IOPS, in many cases beyond 100,000 IOPS. So if you have, very intensive applications that need a very high degree of IOPS, then you can look to instance store volumes to solve that. But keep in mind, again, they are ephemeral. And so EC2 instances, they can be stopped and then started again later. They could be terminated and then relaunched anew. And either way, it's very likely that an instance that is stopped and started will come back to life on a different host. And because it's on a different host, the storage volume is not there. And so there's also no ability to perform snapshots. So between the ephemeral nature and no snapshots, there is really no durability built in. There is absolutely no inherent durability to that storage volume. So the trade-off is that we get really high IOPS with no durability. If durability is important, if you need persistence in your data, if you need some inherent durability, then we would look to EBS. But there are plenty of use cases where ephemeral storage may make sense. One example might be that you are performing some type of extract, transform, and load operation. Maybe you are extracting data from some data source, and now you have this very large data set, and you're doing some type of a transform or an analysis on it that requires a lot of random I/O before shipping it somewhere else. You could have some type of high-performing database such as Mongo or Cassandra running on EC2, and you want access to that high IOPS instance store volume. In that regard, you could achieve durability by leveraging replication. And by replicating those data sets between, 2 or 3 different machines, then you could solve the durability issue, and that if you lost one machine, you would still have some number of machines, 2 or 3 or whatever. So let's take a look at a few instance store volume examples here. And you'll notice here, and this is by no means an exhaustive list, this is just a small sample to give you an idea of what's possible. With certain instances, let's say the M3 large, for example, some instances may come with only one volume. And so here the M3 large comes with one 32 gig SSD volume. Other instances may come with 2 volumes. So the C3 large comes with 2 16 gig SSD volumes. And in that regard, you could treat them as 2 separate volumes and use them for 2 different purposes. Or you could include them in a RAID configuration or include them within a logical volume manager and use them as a single volume. Some of the other instances that are available, you'll notice here that we have the D2 8 extra large. This particular instance comes with 24 2 terabyte volumes. So if you were to RAID those, you could end up with 48 terabytes worth of storage. And of course, in that instance, that is using hard disks rather than SSDs. Now, the later ones, the ones that I'm most excited about recently, would be the 5D instances. The C5D, M5D, and R5D series generally come with some number of volumes. Some come with 1, some come with 2 or 4, but they're all, the D series come with NVMe SSDs. So these are going to be the fastest, most highly performing volumes that you can get for instance store volumes, right? So the takeaway here is that if you do have an application or some type of a use case or workload that needs a very high degree of IOPS, and you're willing to make the trade-off in durability, then take a look at the instance store volumes. Now let's review an introduction to Amazon Elastic Block Store. There are plenty of cases, plenty of situations where we have the data that we're collecting needs to be durable, that we want that data for the sake of high availability and durability, disaster recovery. We want the data to be independent of the machine that it's being accessed by. And so with EBS, that's exactly what we get. We get volumes that are independent from the EC2 instance. Therefore, the data is independent. And that particular mechanism, speaking from personal experience, has saved my life many times. I've been in situations where I've run databases on EC2, and through no fault of my own, the machine simply stopped working because perhaps there was some issue with the underlying physical host. And as a result, my instance was no longer usable. And so the only choice in that scenario was to terminate the instance and replace it with a new one. And the fact that my data was independent on a separate volume allowed me to reattach that volume to the new instance and then pick up where I left off without losing data. So with EBS, we can create a volume, again, independent from an instance. We can attach it to an instance, and we pay for provision storage. This is different from instance store volumes where the price of that is already included in the price of the machine. And it's different from S3 where we are paying for purely pay-as-you-go. With EBS, when we create a volume, we have to choose and specify the size of the volume. And so if we were to create, let's say, a 16 terabyte volume, then no matter how much data we write to that volume, we will pay for 16 terabytes. So again, keep that in mind. You are paying for the provision storage. So one of the keys to cost savings in Amazon is, I think I've mentioned this before, I'll probably mention it again, one of the keys to saving money in Amazon is to use what we really need. And so when it comes to storage, a common best practice is to always evaluate what you are paying for versus what you are actually using. So you might look through your account and find that you have these really large volumes without a whole lot of data being written to them. So you might want to really, always be reconsidering your choices and looking and saying, do I really need that 16 terabytes? Am I actually getting something out of the money that I'm spending? Do I need to be spending that money? So with Elastic Block Store, when we create these volumes, they are created in and they exist in a single availability zone. The EC2 instance and the volume need to be in the same availability zone, right? So there's no way for us to create an EBS volume in one AZ and attach it to an instance in another AZ. That's not possible. Now, EBS volumes do support server-side encryption, so we can encrypt that volume using AES 256. They are connected over the network. EBS volumes, I suppose in the broader sense of the term, they are a part of you could consider them network-attached storage, but not in the traditional sense. Usually when we think of network-attached storage, we think of something using NFS where a volume is shared. And we're going to talk about that later on. But with EBS volumes are always one-to-one. Only one volume can be attached to one instance at a time. So if we take a look here at this diagram, a closer look here, you'll see that this instance has one volume attached. And we have another instance with two volumes attached. But any one volume here is only attached to one EC2 instance at a time. It is not possible for multiple instances to share one volume concurrently. So doing something like this, if we were to try to attach this volume to a second instance over here, that kind of thing is not possible. So we can detach a volume from an instance, and then we could attach it to a different instance, right? So it's very similar to, say, a USB drive, right? Maybe you have a little, I know at home I have a 2.5-inch external drive for doing backups and whatnot. And so I could unplug that from my machine and plug it into a different machine. And so the same thing applies to EBS volumes. EBS volumes can also be used in a RAID configuration or with a logical volume manager. Now, it is worth noting a number of folks over the years have done a lot of testing around this in terms of performance. And keep in mind that the EBS, the underlying storage mechanism for EBS, is already redundant at a device level, right? It's already being written to numerous devices in a cluster within that one AZ. And so doing things like RAID 1 and RAID 5, you're not really getting anything more than what EBS is already giving you. In fact, plenty of organizations have found that certain types of RAID will end up degrading performance to the point that it's just not worth using. Now, in other cases, RAID 0 can improve performance, at least for reads. So keep that in mind. So if you find that you have a particular workload and you need durability, you need inherent persistence in that data, take a look at EBS volumes. Now let's review Amazon EBS volume types and performance. Taking a look at this table here, you can see that when it comes to EBS volumes, we have our choice of either SSD volumes or hard disk volume. And so it really depends on the use case, how we are accessing that data. If we are doing a lot of random I/O, then SSD may be more appropriate. If we're doing more sequential throughput, then the hard disk might be more appropriate. But taking a look over here at the SSDs, we have two different flavors. We have the general purpose and we have provisioned IOPS. And so general purpose volumes, you can see here, they have a different minimum. General purpose volumes allow us to start as low as 1 gig as opposed to the provisioned IOPS allowing us only 4 gig minimum. And so the big difference there is that with a general purpose volume, it will operate at a baseline performance that is relational to its or proportional to its size. And so that baseline performance is essentially 3 IOPS per gig. So if we had a 100 gig general purpose SSD volume, we could expect that to operate at about 300 IOPS. And for certain use cases, that may be perfectly fine. For a root volume, that may be perfectly fine. But for a data volume attached to a high-performing database, that wouldn't be enough, right? So when we have the need for a sustained level of IOPS beyond what the baseline will give us, then we might look to provisioned IOPS. And so you can see here that with provisioned IOPS, we have the ability to go upwards of 64,000 maximum IOPS on that volume. And of course, that is related to the size. There's still a relationship to the maximum IOPS and the size of the volume. There's also a relationship to the generation of EC2 instance that we're using. Keep in mind that the 64,000 max IOPS is only available on later generations that are using the Nitro hypervisor. If you are using older generations that are still using the Zen hypervisor, then we would be limited to 32,000 max IOPS. You can also see that we can achieve a notable throughput, but there's a very large difference between the general purpose and the provision IOPS in terms of total throughput. Now, if our workload were more geared towards sequential I/O, where we were perhaps constantly appending to files or streaming data off sequentially rather than doing a lot of random inserts and updates and deletions and whatnot, then we might look to the hard disks. And so you can see here that we have two different flavors. The throughput optimized is geared towards doing a higher degree of throughput simply because it can do a higher maximum IOPS. And of course, the 500 max IOPS is very low, but we still get a large throughput simply because the hard disks use a larger block size, right, or a larger I/O size, 1 meg versus 16K. And so the throughput optimized, again, might be ideal for doing sequential operations on large files. With cold storage, the cold volumes are ideal for sequentially accessed data that is not accessed very often, right? So cold storage or cold volumes will give us the lowest cost, but also the lowest performance. So again, in terms of EBS volumes, we have again these two different flavors, the SSDs and the hard disks, and then we have different flavors within those. And again, it all comes down to your particular workload for your particular application. So now let's take a look at a demo of creating an EBS volume.
From the AWS Management Console dashboard, we can find EBS volumes underneath EC2, right? So let's go ahead and go there to EC2. And of course, you can see the instances that we were working with earlier. We have our Windows instance and our Linux instance. And let's go ahead and give those a name real quick so that we know later we're going to create an EBS volume now, but we need to mount it to our instances later, right? So let's call this one Windows, and then we'll call this other one Linux. And I know that based on the instance type, right? We went with the T2 micro for Linux and then a C5 large for Windows just because it has more memory. All right, and so we're going to be coming back to these instances later in order to actually make use of these volumes. All right, so let's go down here to underneath Elastic Block Store, and we'll choose volumes. And you can see that we have a few here, but these are the root volumes. if we were to look over here, and you'll see that they say in use. And if we were to take a look at the attachment information, you can see that they are indeed attached to instances. So we know that these are the root volumes for those instances. So I can pretty easily pick out that the two 8 gigs are in use by Linux machines, and then the 30 gig root volume, of course, would belong to Windows. All right, so let's go ahead and create a volume. And here we get to choose, what type of volume is it? Are we choosing a general purpose SSD, a provisioned IOPS SSD, or, some other kind of hard disk for cold storage or throughput optimized or magnetic? I generally, for many things, I'll use SSD. For most things, my use cases typically go with SSD because a lot of the work that I do needs more random I/O. You may have use cases where you're wanting, more sequential access where hard disks are more appropriate. So for now, we can just keep it simple and go with general purpose. And then let's say that we go, all right, 100 gigs. How much data are you going to be storing? How much space do you need to provision? And this is a really important thing to think about because you are paying for this number here, a 1 terabyte volume. I will pay for a 1 terabyte volume. Even if I never write any data to it, if that volume sits there completely empty, then I will still be paying for that terabyte of space because that's what we are provisioning here, right? So we want to be, take some time to really think about how much space do we really need. We can keep it simple and choose, a 100 gig volume. And then you'll see here that it has a baseline of 3 IOPS per gig. So we're going to operate generally at around 300 IOPS, but we will be able to burst at times. We can burst up to 3,000. We will never be able to sustain 3,000 IOPS with a general purpose volume. At some point, we will run out of credits and we will be throttled back to 300. If we did need a sustained, IOP throughput, more than 300 IOPS, then we would go with a provisioned IOPS. And so with provisioned IOPS, we could say, well, I want 100 gigs, but I want a guarantee of sustaining up to 1,000 IOPS, right? So we could do that. You will pay an additional fee for these provisioned IOPS. So for this particular demo, we don't really need that, but in some use cases, you might. Now, another thing to keep in mind is let's take if you only needed 1,000 IOPS. Then watch what happens if we go back to general purpose and we say 400. Then 400, at a baseline of 3 IOPS gives us 1,200 IOPS, and this actually could be cheaper depending on the region you're running in, because the provisioned IOPS tend to be where most of the cost comes from. When we're working with EBS volumes, the provisioning of IOPS will cost you more than the storage. Right, so I have found that this kind of thing in the past has actually saved me money, where I had applications that needed more than the baseline, but I found that just by increasing the size, so what, that I have a little bit more size than I need, it was cheaper than going with provisioned IOPS, right? So that's one thing to just keep in mind. And so our instances that we launched, we know that those were in the US East 2A availability zone. In order for us to be able to attach these volumes to an instance, the instance and the volume have to be in the same availability zone, right? So I want to make sure that I'm choosing the same AZ. Now we could restore, if I were to choose a snapshot, then that would allow us to restore data to this volume from that snapshot. We don't really need to do that right now, but we could. We could also enable encryption if we wanted to. And so we don't really need to do that either. And then again, we could say, tag. We could put environment, right? Environment could be dev or development. Again, be consistent. And cost centers and so on, right? I'm going to tag this one for a purpose. And for this one, I'm going to use this one for Linux. And we'll go ahead and create the volume. We'll do this one more time for Windows because later we're going to attach these, mount these to our Linux and our Windows instances, right? So here is our volume, and then notice that even though we tagged it, if we look at the tags down here, even though we tagged it, it still doesn't have a name, right? So I'm going to call this one Linux so that later we know. And we'll go ahead and create one more, do the same thing. We'll go ahead and do a 400 gig volume. You know what? Let's just go with 100, and just for the sake of showing this, let's go with provision IOPS and say 1,000, or maybe even 2,000. You know, maybe you have some kind of high-performing application. Maybe it's a database that's not storing a lot, but it's doing a lot of random I/O. And so maybe you have that use case where you need a consistent, sustained level of IOPS above, you know, the 100 IOPS or 300 IOPS baseline. Again, the US East 2A availability zone, no snapshot, no encryption. Again, we'll add those same tags, you know, being consistent in what we're doing. And here I'm going to call this one purpose, Windows. And of course, you know, the tags are totally arbitrary. They're up to you. But the important thing is to really make use of them. You know, apply all of the key value pairs that can help you organize and attribute cost. You've heard me say it before, and I'll probably say it again because it is a really, really important thing. And for automation as well, helping you find what you're looking for, you know, when you need it. All right, so we've created that volume, and let's go back to, where is that volume? Here it is. Here's our 100 gig volume, and you can see that the volume type is slightly different. These are general purpose, and IO1 is provision IOPS, and you can see here's the 2000 IOPS, and we'll go ahead and name this one again Windows. And this is just for the demo. You know, I would encourage you to name them for your particular use case. In your environment, name them in a way that makes sense. All right, so that's all there is to it. To create an EBS volume, specify the size, the type, you know, what kind of IOPS you might need, apply the appropriate tags, and we will continue to explore this in an upcoming demo.
Now let's take a look at a demo of mounting an EBS volume on a Linux instance.
All right, from the EC2 dashboard, we can see here we have the two running instances, and we have our volumes. If we go back here to volumes, you can see here are the two that we created, and we're going to mount, before we can mount that volume to our instance, we first have to attach it, right? So we're going to start with Linux here, the Linux volume, and we're going to say actions attach volume. And now we can do a search, right? Or even if we click in that field, it gives us an option to choose which one we're going to mount it to. And so here we're going to choose the Linux instance. And you'll see here that it's giving us the ability to choose, you know, which device do we want that to. And so from the AWS side, it's saying that the device name will be dev SDF through SDP. So it's up to us, whichever, you know, where we want that to be. If we have an application expecting it to be somewhere, then we might want to mount it exactly in that same place. So, you know, if we have automation tools that are expecting, you know, a volume at SDF to be used for a particular region, a volume at SDG for another region and for another reason, and so on, then, you know, we can use this to guarantee that if we need to, for example, restore a volume from a snapshot and get that volume back in place available to an instance, then the automated tools on that instance know that if we're applying this volume to SDF or SDG or so on, then it's being used for a particular purpose, right? So for now, we'll just go with SDF. And then you'll also note here that some Linux kernels may rename your devices to XVDF rather than SD, right? So we'll have to look at that. right? We'll go ahead and attach that, and we can scroll over here and see that our Linux volume is now in use and our Windows volume is still available. So available means that the volume is not currently attached to anything. And so this is an important thing that your ongoing day-to-day constant evaluation of your Amazon environment is to look for things like this. If you see volumes that are just available, sitting there, not attached, then you're spending money on provisioned storage that is not being used. So now our Linux volume is attached. So if we go back to our instances and we take a look at our Linux, what I want to do here is make sure that I've copied the private IP address so that I can shell into that instance, and from there, then we can mount that volume, right? So we created the volume, then we attached the volume. Now we need to make sure that the operating system can mount it, and then we can format it and so on. All right, so let's go ahead and use this private IP to shell in to that instance. Now from the terminal, we're going to replay the same SSH that we ran earlier. That kind of sets us up to use the same key, but I just want to use the different IP address. We'll go ahead and SSH, yes. All right, and there we go. We have our shell into our Amazon Linux EC2 instance. And from here, we can do an ls block and list our block devices. And then you'll see here that we have our 8 gig volume as a disk, and then it's mounted to XVDA1, and of course it's mounted to slash. So this is our 8 gig root volume, right? And then we can see here's our 400 gigabyte disk that is attached at XVDF, right? And so now we want to make sure that we don't have any kind of file system on there. So let's do a sudo file -s slash device slash, and you can see here it did rename. This Linux kernel did rename it from SD to XV, right? So that's one thing to keep in mind in your automation scripts. On the Amazon side, it could be SDF, and from within Linux, it could be XV, right? So we're going to take a look at XVDF. And so here it just says data, right? If we were to do the same thing for XVDA, you'll see that it actually has a partition in its extended partition. So this one actually does have a file system, right? And so this one means that there's no file system yet. It has not been formatted. And so now, in order to format our disk, then we would run make file system sudo mkfs -t. We could use whatever, xfs, whatever you want, and we'll go /dev xvdf. We want to make sure if we were to do that, then we would end up formatting our root volume. We don't want to do that. We want to make sure that we are indeed formatting the right volume, xvdf. All right, so let's go ahead and do that. And there we go. Now if we were to replay our file -s on that volume again, there we go. Now we have a file system. All right, and so now we can actually mount that. And so now we get to choose where do we want to mount it, right? If we go to, we could put it under media or under mount. You know, if you wanted it more, closer to the top, then we could create a directory, right? We could say sudo mkdir /data, and then now we could mount that volume /dev /xvdf to /data, right? And now if we do an ls list block again, you'll see that we have our 400 gig volume mounted to /data, right? So if we were to go to cd /data, and if we were to touch Oh, I need to do a sudo on that one, right? And so now this particular file was written at 0 bytes, but this file is now on that particular volume, right? So we can go ahead and now that we've done that, we can log out, connection closed, and we can go back to our console. And from the instance's point of view, if we look at the instance, we can also see that we have 2 block devices mounted: XVDA, which is the root volume, and dev SDF, which is our 400 gig data volume. And then if we were to click on that, it would give us, some information that it's attached. Delete on termination is false. So this is also an important thing to keep in mind. So if the instance gets terminated, then this volume will stick around, and that's exactly what we want for a data volume, right? That very thing has saved my life numerous times, where an instance failed, but the fact that the volume stuck around meant that I could get my data back, right? I just replaced the instance with a new one, reattach that existing volume, and pick up where I left off, right? Now, in the case of, if we were to click on XVDA, you'll see here, of course, this is the root volume, and it says delete on termination is true. And so this means that when the instance gets terminated, that volume also gets deleted, and that's there to help ensure that you don't end up with a whole long list of orphaned EBS volumes that aren't being used. But you can always change that if there is some particular reason, and I haven't seen one, but there could be a reason that you might want to save that root volume. Actually, I can think of one. I do seem to recall at some time, over the years, that there was a time when we had done something very particular to an operating system. We had some kind of data that ended up on the root volume, but we needed the instance to be terminated, and we wanted to save that volume. So all we had to do was go in here, and you can change that. Delete on termination, you can change that to false. And then from there, you could go back to volumes, right? And we can go to the Linux volume, and we can find monitoring on that down here. You can see, once that volume has been attached and mounted and formatted, and it's being used by that operating system for whatever workload, then you can come here and look at the bandwidth, the throughput, and so on, average queue length, and all of these things. And these kinds of monitoring may very well help you to determine whether that volume is appropriate. You might find, according to these kinds of monitoring tools, that you may need more or less IOPS than what are being provided. So that's how we can attach and mount a volume to a Linux instance.
Okay, so now let's review a demo of mounting an EBS volume on Windows.
All right, from the EC2 dashboard, let's take a look at our volumes. We'll scroll down here under Elastic Block Store. And of course, here are the 2 that we created earlier, our Linux and our Windows volumes. And again, just like we saw earlier, that some of them are in use, means that they are attached, and our Windows volume here is available. And so again, before we can mount it and format it and use it, we have to attach it. So we'll go ahead and say attach volume, and then we will choose our Windows instance. And then, of course, in this particular case, unlike Linux, the Amazon side is attaching it as XVDF rather than SDF. All right, so we'll go ahead and attach that. And now you can see it changes pretty quickly. It changes to in use. So just like that, it's attached. Again, very, very similar to a USB drive that you might have on your desk. You plug it in, and just like that, it's ready to use. All right. And so now we'll go back to our instances, and here is our C5 large that we created in an earlier demo, and we are going to gain a remote desktop into that instance, and then from there we can mount and format that volume. So let me get my remote desktop in place here. All right, so we'll go ahead and use the existing connection just like we did earlier when we created that instance. And again, you may see these warnings saying that the certificate can't be trusted, but for now, that's okay. All right, so now we have a remote desktop, and we should be able to go to right-click on the Start menu and go to Disk Management. And from here, it says you must initialize a disk, right? So this is now, this disk is attached and, available for us to use, right? So we'll go ahead and say, okay, we can initialize that disk. And you can see here, this is our 30 gig root volume. And here is our disk, 100 gig disk that is unallocated. And we can take a look at the properties of that and see, this is an NVMe Amazon Elastic SCSI disk device, at least as far as, Windows is concerned. And so we can see all of the information we need to see about that. Here's, again, 100 meg. All right, so then all we really need to do is right-click on this unallocated space and say new simple volume. That will bring us to the wizard. We can then, of course, specify that volume size. If we wanted to create, multiple partitions, we could. And then we could go next, assign it, whatever drive letter we want. I think D is perfectly fine. And then we'll go next. Then, of course, we get to format it, right? XFAT, NTFS, whatever you feel is appropriate for your particular use case. And then the volume label, we might call this one data if we wanted to, have this as a store for SQL Server or SharePoint or anything else, right? And then, of course, we could also choose to perform a quick format, right? So we'll go next and finish that. And there we go. Just like that, we have a 100 gig volume that we attached to the Windows instance, and then we used the Disk Manager to create and format a partition with NTFS, right? And so here is that. And so then, of course, we could go to the Explorer, and we should be able to see here is our data disk now available for us to write to, right? So that's how we can attach and format a volume for Windows instances.
Now let's talk about Amazon EBS snapshots. So a really powerful feature of EBS is the ability to take snapshots. Like we talked about earlier, EBS volumes exist in a single availability zone, and they are durable to the loss of a device within that availability zone, but they are not durable to the loss of that availability zone. So if that availability zone is offline, your data is unavailable. If that availability zone is destroyed by natural disaster, the data that is on that volume will also be destroyed. And so volumes can be restored from snapshots, right? So to mitigate that kind of thing, by taking regular snapshots, we know that we have a backup of that volume somewhere, so that if the volume is accidentally deleted, if the availability zone were to be destroyed, then we still have a copy of that data somewhere in the form of a snapshot. When we take a snapshot of that volume, the data is stored, the snapshot is stored in S3. And so looking here, if we were to initiate a snapshot of this volume, then the data that comprises these snapshots all get stored over here within S3. Now, this is not to say that we have to create and manage an S3 bucket. AWS does that for us, right? So the management of S3, the creation of buckets and all of that, that's handled by AWS. We just know that snapshots, according to AWS documentation, we know that snapshots are stored within S3, and we know that S3 gives us numerous copies across numerous availability zones, so that S3 is durable to the loss of an availability zone, right? So if we're storing our data in the form of snapshots, if an availability zone is lost, we will still have a copy in the form of a snapshot. Another great benefit of snapshots is the ability to copy them to another region. So if we take a snapshot of a volume, that snapshot will be stored in the same region as that volume. We could then copy that snapshot to any other region. And by doing that, now we have multiple snapshots. Now we have some geographical diversity. We have backups of the data potentially thousands of miles apart, so that if an entire region were affected by natural disaster, then we would still have a copy of that data in another region. We can also share those snapshots. So again, it's common practice for organizations to leverage multiple accounts. And again, you may have an account for admin purposes, you may have an account for different environments or accounts for different business units, and it's possible that you can take a snapshot in one account and share that snapshot to other accounts. Now, the way that snapshots work, if we were to take a look at the mechanics, we take a look here at this particular slide. Let's say here we have a block level volume, right? And each one of these squares represents a block on that volume. If for, let's say, a fairly new volume, we have a lot of blocks, but only some of them have data, right? We've only written data to a number of blocks here. The first backup that we do will be a full backup that includes all the data on that volume, right? And so the first backup includes all the data that currently exists. When we perform subsequent backup or snapshots, those are incremental. That's only recording deltas. And so here, perhaps we've changed some data, right, in these blocks, and perhaps we've added some data in some other blocks. And so only the data that has changed or been added will be included in that subsequent snapshots. And so a common question here is, well, if you're only storing deltas, what happens if you go back and delete like an earlier snapshot? And the answer to that is that you may be taking regular snapshots and each one only recording deltas. If you go back and delete an earlier one or several dozen earlier ones, it doesn't matter, any later snapshot will maintain a reference to all of the data that it needs, right? So just because you delete an old snapshot doesn't mean that a later snapshot is now unusable, right? Any snapshot that you take will include all of the data necessary to restore that volume. Another feature that we have access to that we should keep in mind is the Data Lifecycle Manager. And this was released fairly recently in the latter part of 2018. And for a long time, people in my classes would ask me, or clients of mine would also ask me, hey, is there a way to automate snapshots? And I would say, yeah, we can write a script to do that. And this was a feature that we've been looking for a long time, and now it's finally here. The Data Lifecycle Manager allows us to automate these snapshots. So we can create a schedule here, right? We can create a timer that says every so often I want to automate these snapshots and regularly take a snapshot of that volume. So we as a customer, we define the backup and retention schedules. How often do we want those backups to be performed? How long do we want those backups to be maintained? And of course, we can create those rules with tags. We haven't really talked a whole lot about tags so far, but tags are a way of organizing our environment. And tags are essentially arbitrary key value pairs. And so we could tag something with, say, environment equals production, or project equals whatever, cost center and owner and so on. And so we could use those lifecycle rules to say, well, every volume that's tagged in a particular way should be, we should take a snapshot on a particular schedule. So for those of us who have data that is really important to us and we need to maintain a high degree of durability in that data, if we want to rest assured knowing that we have not only copies of the data live, but also multiple copies of the data in the form of backups, then we should take a look at EBS snapshots. All right, so now let's review a demo of creating a snapshot of an EBS volume.
From the EC2 dashboard, before we take a look at our volumes, we can notice here in the summary that, of course, we have 5 volumes. We know that some of those are root volumes, and 2 of those are volumes that we created for data, and we currently have no snapshots. So let's go to our volumes. And again, here's the 400 gig volume that we added to our Linux machine and the 100 gig volume that we added to our Windows machine. And so taking a snapshot is really just a matter of going here and saying create snapshot. Now, it is a good idea to quiesce that disk from the operating system point of view. So if you had, a database or some type of an application running that was performing writes, then you would probably want to pause those writes, initiate the snapshot, and then you could continue with your writes. And so we'll go ahead and say create snapshot, and then we'll call this one. We could say data backup, whatever, some kind of a description that helps you understand. And of course, the date and time that it was created will already be recorded for you. You don't necessarily need that in the name. Again, tags, right? Environment, those kinds of things. And what kind you might want to add tags that describe, the data that is on here, right? Does it belong to a particular database for a particular application, for a particular team or project, or so on? And then we'll go ahead and say create snapshot. And then, of course, whatever data was on that device at the time we clicked that button, that's what will be a part of the snapshot. So if we go back here to that, if we go over to snapshots, you'll see that it's currently pending, and any data that is being written to that volume now will not be a part of the snapshot. Only data that was written at the time we initiated the snapshot will be included in the snapshot, right? And of course, there really is no data here, so it really shouldn't take that long. And so you can see here the progress, and you can keep an eye out on the status up here, and you can always hit this little button. You don't need to necessarily refresh the entire browser window. Most AWS consoles give you this little refresh button up here that does a better job of refreshing the console. And so there you go. We have the snapshot is now completed, progress 100%. And of course, we hadn't written any data to it, but if in a real world scenario, if we had written data to that, then from here, we could say, well, let's create a volume. And by creating a volume, in this way from the snapshots, then that will create a volume from that snapshot. All of the data on that snapshot will then be available on the EBS volume that was created from it. And again, just as a reminder, this snapshot now, whatever data is a part of this snapshot, we know is stored in S3. And we don't necessarily have access directly to that area of S3 storage, but we do know that the data, all of the data that was a part of this particular snapshot is stored in S3, so we gain a much higher degree of durability in that data. And so pretty simple, right? Not a whole lot to do other than select your volume and create a snapshot.
Now let's review an introduction to Amazon Elastic File System, or EFS. In certain workloads, in certain situations, we may have a need for multiple instances to share a single file system. In those situations, the elastic file system may very well be the answer. And so EFS gives us a shared file system using NFS version 4. So you'll notice here in this diagram that we have a file system that we would create within EFS, and we have multiple instances attached to that same file system and sharing that same file system. And so a nice feature of EFS, aside from it being shared, is the fact that it scales automatically. With EBS, with the Elastic Block Store, we have to provision storage. We have to say, hey, I want a 1 gig or a 16 terabyte volume. And whereas with the Elastic File System, we don't have to provision anything. We simply create a file system, and then as we start writing data to it, it grows automatically. As we delete information, it shrinks automatically. So we are paying for what we use as we use it. It's also worth noting here that with the Elastic File System, data is stored redundantly across availability zones. So comparing that to the Elastic Block Store volumes exist in a single availability zone, where Elastic File System volumes are stored redundantly across AZs. And the instances that attach to the EFS storage volumes or file systems can access that from different AZs. So the takeaway here for any of us that have situations where we need multiple instances, whether it be EC2 instances within AWS or servers on premises, or a combination of the two, if we need multiple servers to access the same file system, the same shared file system, then take a look at EFS. Now let's talk about server-side encryption. A number of services within AWS offer server-side encryption. And generally, depending on the service, we have a number of options in terms of where those keys are managed. Probably the easiest thing to use is the Key Management Service, or KMS. And we will talk about KMS in more detail in a later lesson. For now, I simply want to highlight some of the services that offer server-side encryption. And so all of the services that perform server-side encryption will always do that with the Advanced Encryption Standard, or AES 256. And so you'll see here, this is, again, by no means an exhaustive list. These are just some examples, but S3, Glacier, EBS, those all support server-side encryption. Amazon EMR and Simple Queue Service supports server-side encryption, as does several different databases, DynamoDB, the relational database service, Redshift, and so on. So lots of different services support server-side encryption within AWS. And so when they do that, they might do it slightly differently. With S3, for example, we would get a key per object. So every single object that we upload to S3 would end up using its own encryption key. That way, if any key were compromised, only that one object was compromised rather than an entire bucket. With Glacier, we get a key per archive, very similar to per object in S3. With EBS, we get a key per volume. And with Redshift, this is an interesting one. Redshift uses what we call a 4-tier envelope encryption. And that may be a new term for some of us. Envelope encryption means that we use one key to encrypt another key to encrypt another key, and so on. And so with Redshift, that process happens 4 different times with a number of different keys. So Redshift can be incredibly secure by being encrypted at numerous levels. With RDS, the relational database service, because RDS is essentially built on EC2 using EBS, RDS essentially builds on top of EBS encryption using a key per volume. So For those of us who have sensitive data, data that we want to ensure is encrypted at rest, we can leverage server-side encryption across a number of different services within AWS to ensure that we are meeting compliance, meeting the requirement of compliance to have that data encrypted at rest. Now let's talk about AWS Snowball. Now there are many organizations out there that have very large amounts of data. I've been to a number of different organizations, either teaching classes or consulting, and I found it very common for folks to come and ask me, hey, how do I get 50 terabytes into AWS? Or how do I get, hundreds of terabytes or a petabyte into AWS? And a common answer to that is, well, depending on your networking solution, we might look at that first. But in some cases, the data set is so large that no amount of networking is going to solve that. And so in those cases, we would look to AWS Snowball. So AWS Snowball is a petabyte scale data transport solution, right? So when you sign up for Snowball and you request a Snowball, AWS will ship this device to you. And it is a very rugged, tamper-resistant enclosure. And so AWS will ship the device to you. You would plug it in to your local network, install the necessary drivers so that it's exposed as an available volume. And any data that you write to it is automatically encrypted using 256-bit encryption. So it is inherently secure in that we know by default, without opting into anything, our data is encrypted and it's being stored on a device that is tamper resistant. If anyone tries to open that device, it would be essentially rendered unusable. Then it also includes an e-ink shipping label that once you have finished loading the data and you're ready to send it back to Amazon, that label automatically updates. And then you ship it back to AWS. AWS will do the reverse. They will plug it into their high-speed network and move the data from that Snowball into S3 for you. So for those of us who have very large amounts of data volumes that are too large to move over the network, even with Direct Connect, then Snowball is probably the solution to take a look at.